convolution into a depthwise convolution followed by a pointwise convolution. A depthwise convolution applies a single convolutional filter to each input channel separately, while a pointwise convolution uses a one-by-one convolution to combine the outputs of the depthwise convolution. This factorization significantly reduces the number of parameters and computations compared to standard convolutions. Mobile nets also introduce two global hyperparameters, a width multiplier and a resolution multiplier. The width multiplier controls the number of channels in each layer, allowing for the creation of thinner models with fewer parameters. The resolution multiplier controls the input resolution, allowing for a trade-off between accuracy and computational cost. By adjusting these hyperparameters, mobile nets can be customized to meet different resource constraints and performance requirements. Shuffle nets, introduced by Zhang et al. In 2018, are another family of efficient CNN architectures that achieve high accuracy with limited computational resources. Shuffle nets use two main operations: pointwise group convolutions and channel shuffle. Pointwise group convolutions divide the input channels into multiple groups and apply separate one-by-one convolutions to each group. This reduces the number of parameters and computations compared to standard one-by-one convolutions. However, it also limits the flow of information between different channel groups. To address this limitation, shuffle nets introduce a channel shuffle operation that mixes the channels from different groups, allowing information to flow across groups and improving the representation power of the network. Shuffle nets have been shown to achieve a good balance between accuracy and efficiency, outperforming mobile nets and other efficient architectures on benchmark tasks. Squeeze nets, introduced by Ayandala et al. In 2016, are another notable efficient architecture that achieves AlexNet-level accuracy on ImageNet with 50x fewer parameters. Squeeze nets use a fire module that consists of a squeeze layer with 1x1 filters and an expand layer with a mix of 1x1 and 3x3 filters. The squeeze layer reduces the number of input channels to the 3x3 filters, significantly reducing the total number of parameters. Efficient nets, introduced by Tan and Lo in 2019, are a family of CNN architectures that are designed using Neural Architecture Search (NAS) and a compound scaling method. Efficient nets start with a small baseline network found by NAS and then uniformly scale up all dimensions of the network, depth, width, and resolution, using a fixed set of scaling coefficients. This compound scaling approach allows efficient nets to achieve state-of-the-art accuracy on ImageNet while being significantly smaller and faster than previous models. These efficient architectures have enabled the deployment of deep learning models on a wide range of resource-constrained devices, from smartphones and tablets to drones and robots. They have also inspired further research into techniques for model compression, such as pruning, quantization, and knowledge distillation, which can further reduce the size and computational cost of deep learning models. The development of efficient deep learning architectures is an active and rapidly evolving area of research. As deep learning continues to find applications in diverse domains and devices, the need for efficient and lightweight models will only become more important. Attention mechanisms in CNNs, focusing on relevant features. Attention mechanisms have emerged as a powerful technique in deep learning, allowing models to focus on the most relevant parts of the input when making predictions. While attention was initially introduced in the context of natural language processing, particularly for sequence-to-sequence models, it has also been successfully incorporated into convolutional neural networks, CNNs, to improve their performance and interpretability. In the context of CNNs, attention mechanisms can be used to selectively weight different spatial locations or channels of feature maps, allowing the network to focus on the most informative regions or features for a given task. This can be particularly useful when dealing with large images or complex scenes where only a small portion of the input is relevant for the task at hand. Squeeze-and excitation networks, SENETs, introduced by Hu et al. In 2018, are one of the first works to incorporate attention mechanisms into CNNs. SENETs introduce a squeeze-and excitation (SE) block that adaptively recalibrates channel-wise feature responses by explicitly modeling the interdependencies between channels. The SE block consists of two main operations, squeeze and excitation. In the squeeze operation, global average pooling is applied to each channel of the feature map to obtain a channel descriptor, which summarizes the global information for each channel. In the excitation operation, a small fully connected network with two layers is used to learn a set of channel-wise weights based on the channel descriptor. These weights are then used to rescale the original feature map, effectively emphasizing the most informative channels and suppressing less useful ones. SE blocks can be easily integrated into existing CNN architectures, such as ResNet and Inception, by inserting them after each convolutional block. CNNs have been shown to improve the performance of various CNN models on benchmark tasks, such as image classification and object detection, with a minimal increase in computational cost. Convolutional Block Attention Module, CBAM, introduced by Wu et al. In 2018, extends the idea of CNNs by incorporating both channel and spatial attention mechanisms. CBAM consists of two submodules, a channel attention module, which is similar to the SE block, and a spatial attention module, which focuses on the most informative spatial regions of the feature map. The channel attention module in CBAM computes channel-wise attention weights using both average pooled and max pooled features, followed by a shared multilayer perceptron, MLP. The spatial attention module computes spatial attention weights by applying average pooling and max pooling along the channel dimension and then using a convolutional layer to generate a spatial attention map. CBAM can be integrated into existing CNN architectures by inserting it after convolutional layers. It has been shown to improve the performance of various CNN models on tasks such as image classification, object detection, and instance segmentation. Other attention mechanisms have also been explored in the context of CNNs. For example, self-attention, which is a key component of the transformer architecture, has been adapted to CNNs to capture long-range dependencies between different spatial locations in the feature maps. Non-local neural networks, introduced by Wang et al. In 2018, use a self-attention mechanism to compute the response at a position as a weighted sum of the features at all positions, where the weights are determined by the pairwise similarity between the positions. Attention mechanisms in CNNs offer several advantages. They can improve the representation power of the network by allowing it to focus on the most relevant features for a given task. They can also enhance the interpretability of the model by providing insights into which parts of the input are most important for the prediction. Moreover, attention mechanisms can help to improve the robustness of CNNs to variations and perturbations in the input, such as occlusions or changes in viewpoint. The development of attention mechanisms for CNNs is an active area of research, and new techniques and architectures that incorporate attention are constantly being proposed. Adversarial training and robustness in CNNs, defending against attacks. Adversarial examples, which are inputs to machine learning models that are intentionally designed to cause misclassification, have exposed a significant vulnerability of deep learning models, including convolutional neural networks, CNNs. Adversarial training is one of the most effective techniques for improving the robustness of CNNs against such attacks. It involves augmenting the training data with adversarial examples during the training process, making the model more resilient to small, carefully crafted perturbations in the input. The basic idea behind adversarial training is to include adversarial examples in the training set along with the original, unperturbed examples. During each training iteration, adversarial examples are generated for the current mini-batch of training data, and the model is trained to correctly classify both the original and adversarial examples. This can be formulated as a min-max optimization problem, where the inner maximization aims to find the most effective adversarial perturbation for each input, and the outer minimization aims to minimize the loss on both the original and adversarial examples. One of the most widely used methods for generating adversarial examples during training is the fast gradient sign method, FGSM. FGSM computes the gradient of the loss function with respect to the input and then adds a small perturbation to the input in the direction of the sign of the gradient. The magnitude of the perturbation is controlled by a hyperparameter, typically denoted as epsilon, projected gradient descent, PGD, is a more powerful multi-step variant of FGSM, where the input is iteratively updated in the direction of the gradient of the loss function, and after each update, the perturbation is projected back into the epsilon ball around the original input to ensure that it remains small. Adversarial training can significantly improve the robustness of CNNs to adversarial attacks. Models trained with adversarial examples are more resistant to small perturbations in the input and can maintain high accuracy even in the presence of adversarial examples. However, adversarial training also has some limitations. It can reduce the accuracy of the model on clean, unperturbed examples, a phenomenon known as the accuracy-robustness trade-off. It is also computationally more expensive than standard training, as it requires generating adversarial examples at each training iteration. Moreover, adversarial training with a specific attack method, such as FGSM or PGD, may not generalize well to other types of attacks. A model trained with FGSM-generated adversarial examples may still be vulnerable to PGD attacks, and vice versa. To address these limitations, several variants and improvements to adversarial training have been proposed. One approach is to use an ensemble of different attack methods during training, which can improve the robustness to a wider range of attacks. Another approach is to incorporate regularization terms into the loss function that encourage the model to learn more robust features or to have smoother decision boundaries. Adversarial training can also be combined with other defense mechanisms, such as input transformations or model ensembling, to further improve robustness. For example, input transformations like random resizing and random cropping can make it more difficult for an attacker to craft effective adversarial examples. Model ensembling, where multiple models are trained and their predictions are combined, can also improve robustness by reducing the likelihood that all models are vulnerable to the same adversarial examples. Despite the progress in adversarial training and other defense mechanisms, developing robust and secure deep learning models remains an open challenge. New attack methods are constantly being developed, and it is difficult to guarantee robustness against all possible attacks. The study of adversarial examples and robustness in deep learning is an active and rapidly evolving research area. It has important implications not only for the security and reliability of deep learning systems but also for our understanding of the fundamental properties and limitations of these models. Lesson 12: Recurrent Neural Networks for Sequential Data. Introduction to RNNs. For sequential data. Recurrent neural networks, RNNs, are a class of neural networks specifically designed to process sequential data, where the order of the data points matters. Unlike feed-forward neural networks that process each input independently, RNNs maintain an internal state, or memory, that captures information about previous inputs in the sequence. This ability to retain and utilize information from past inputs makes RNNs well-suited for tasks involving sequential data, such as natural language processing, speech recognition, time series analysis, and video processing. The key feature of an RNN is its recurrent connection, which allows information to flow in a loop within the network. At each time step, the RNN receives an input and updates its internal state based on the current input and the previous state. The output of the RNN at each time step can be a function of the current state, the current input, or both. This recurrent process enables the network to learn temporal dependencies and patterns in sequential data. RNNs can handle sequences of arbitrary length, making them flexible for processing data with varying sequence lengths. The internal state of an RNN acts as a memory that summarizes the past information in the sequence. However, the basic RNN architecture has limitations in learning long-range dependencies, where relevant information might be separated by many time steps. This is due to the vanishing and exploding gradient problems, which can occur during the training process when gradients are backpropagated through many time steps. Despite these challenges, RNNs have been successfully applied to a wide range of tasks involving sequential data. In natural language processing, RNNs have been used for language modeling, machine translation, text classification, and sentiment analysis. In speech recognition, RNNs can transcribe spoken language into text. They are also used in handwriting recognition, video analysis, and music generation. The development of more advanced RNN architectures, such as long short-term memory, LSTM, networks and gated recurrent units, GRUs, has significantly improved the ability of RNNs to learn long-range dependencies. These architectures use specialized gating mechanisms to control the flow of information through the network, mitigating the vanishing and exploding gradient problems. Research on RNNs is ongoing, with new architectures and techniques being developed to further improve their performance, efficiency, and interpretability. RNNs have become an essential tool in the deep learning toolkit for modeling and understanding sequential data. LSTM networks, architecture and training long short-term memory, LSTM, networks are an advanced type of recurrent neural network, RNN, architecture that was specifically designed to address the vanishing gradient problem and learn long-range dependencies in sequential data. LSTMs were introduced by Hochreiter and Schmid-Huber in 1997 and have since become one of the most widely used and successful RNN architectures. The key innovation in LSTMs is the use of a memory cell and gating mechanisms that regulate the flow of information into and out of the cell. The memory cell, denoted as C sub T/sub, acts as an accumulator of information over time. It can maintain information over long periods, allowing the network to learn long-range dependencies. The gating mechanisms control which information is stored in the memory cell, which information is outputted, and which information is forgotten. An LSTM cell has three main gates: the input gate, the forget gate, and the output gate. Each gate is a neural network layer with a sigmoid activation function, which outputs values between 0 and 1. These values can be interpreted as the proportion of information that should be allowed to pass through the gate. The input gate, denoted as I sub T/sub, controls how much of the new input information should be stored in the memory cell. It takes as input the current input X sub T/sub and the previous hidden state H sub T1/sub and outputs a value between 0 and 1 for each element of the cell state. The forget gate, denoted as F sub T/sub, controls how much of the previous cell state C sub T1/sub should be forgotten. It also takes as input the current input X sub T/sub and the previous hidden state H sub T1/sub and outputs a value between 0 and 1 for each element of the cell state. The output gate, denoted as O sub T/sub, controls how much of the cell state should be outputted to the hidden state H sub T/sub. It takes as input the current input X sub T/sub and the previous hidden state H sub T1/sub and outputs a value between 0 and 1 for each element of the cell state. The cell state C sub T/sub is updated based on the input gate, the forget gate, and a candidate cell state C sub T/sub. The candidate cell state is computed similarly to the hidden state in a basic RNN, using the current input X sub T/sub and the previous hidden state H sub T1/sub, but with a tan activation function. The new cell state is computed as C sub T/sub equals F sub T/sub asterisk C sub T1/sub plus I sub T/sub asterisk C sub T/sub. This equation shows that the new cell state is a combination of the previous cell state, modulated by the forget gate, and the new candidate cell state, modulated by the input gate. The hidden state H sub T/sub is then computed based on the output gate and the updated cell state C sub T/sub H sub T/sub equals O sub T/sub asterisk tan, C sub T/sub. This shows that the hidden state is a filtered version of the cell state, determined by the output gate. LSTMs are trained using backpropagation through time, BPTT, similar to basic RNNs. However, the gating mechanisms in LSTMs help to mitigate the vanishing gradient problem by providing a more direct path for gradients to flow during backpropagation. The cell state, in particular, has a linear self-connection with a weight of 1, which allows gradients to flow unimpeded over many time steps. Despite their effectiveness, LSTMs are more complex and computationally expensive than basic RNNs due to the additional gates and parameters. They also require careful tuning of hyperparameters, such as the learning rate and the number of hidden units. Since their introduction, LSTMs have been successfully applied to a wide range of tasks involving sequential data, including machine translation, speech recognition, image captioning, and video analysis. They have become a fundamental building block in many state-of-the-art deep learning models for sequence processing. Researchers have proposed several variants and extensions of LSTMs to improve their performance and efficiency. Peephole connections, for example, allow the gates to inspect the cell state when making decisions, providing additional information for the gating mechanisms. Coupled input and forget gates tie the input and forget gates together, so that the network only forgets when it's going to input something new, and vice versa. This simplifies the LSTM architecture and reduces the number of parameters. Depth-gated LSTMs introduce gates that control the flow of information between different layers in a deep LSTM network, allowing for more efficient training of very deep LSTMs. These and other variants demonstrate the ongoing research efforts to improve and extend the capabilities of LSTM networks. GRU networks, architecture and training-gated recurrent units, GRUs, are a type of recurrent neural network, RNN, architecture that, like LSTMs, use gating mechanisms to control the flow of information and learn long-range dependencies in sequential data. GRUs were introduced by Cho et al. In 2014 as a simpler alternative to LSTMs, with fewer parameters and often comparable performance. A GRU cell has two main gates, the update gate and the reset gate. The update gate, denoted as Z sub T slash sub, controls how much of the previous hidden state H sub T1 slash sub should be retained and how much of the new candidate hidden state H sub T slash sub should be incorporated. It takes as input the current input X sub T slash sub and the previous hidden state H sub T1 slash sub and outputs a value between 0 and 1 for each element of the hidden state. The reset gate, denoted as R sub T slash sub, controls how much of the previous hidden state should be ignored when computing the candidate hidden state H sub T slash sub. It also takes as input the current input X sub T slash sub and the previous hidden state H sub T1 slash sub and outputs a value between 0 and 1 for each element of the hidden state. The candidate hidden state H sub T slash sub is computed similarly to the hidden state in a basic RNN, using the current input X sub T slash sub and the previous hidden state H sub T1 slash sub, but with the reset gate modulating the contribution of the previous hidden state, H sub T slash sub equals tan, W sub X sub T slash sub, plus U sub R slash sub T slash sub asterisk H sub T1 slash sub plus B, where W sub X slash sub and U sub R slash sub are weight matrices, B is a bias vector, and asterisk denotes element-wise multiplication. The hidden state H sub T slash sub is then updated as a linear interpolation between the previous hidden state H sub T1 slash sub and the candidate hidden state H sub T slash sub, controlled by the update gate Z sub T slash sub H sub T slash sub equals 1, Z sub T slash sub, asterisk H sub T1 slash sub plus Z sub T slash sub asterisk H sub T slash sub. This equation shows that the new hidden state is a convex combination of the previous hidden state and the candidate hidden state, with the update gate determining the weighting between them. GRUs have a simpler architecture compared to LSTMs, with only 2 gates instead of 3 and no separate memory cell. This makes them computationally more efficient and easier to implement. Despite their simplicity, GRUs have been shown to perform similarly to LSTMs on many tasks involving sequential data. GRUs, like LSTMs, are trained using backpropagation through time, BPTT. The gradients are computed with respect to the loss function and propagated back through the network across all time steps. The weights are then updated using an optimization algorithm, such as stochastic gradient descent, SGD, or ADAM. One of the key differences between GRUs and LSTMs is that GRUs do not have a separate memory cell. Instead, They use the hidden state to store and propagate information over time. This can make GRUs more prone to forgetting information compared to LSTMs, which have an explicit mechanism for preserving information in the memory cell. However, in practice, GRUs often perform just as well as LSTMs, and their simpler architecture can make them a more attractive choice in some cases. GRUs have been successfully applied to various applications, including machine translation, speech recognition, and music generation. They have also been used in combination with other types of neural networks, such as convolutional neural networks, CNNs, to create hybrid models for tasks that involve both sequential and spatial data, such as video analysis and image captioning. The choice between GRUs and LSTMs often depends on the specific task and dataset. Some studies have suggested that LSTMs may perform better on tasks that require learning very long-range dependencies, while GRUs may be sufficient for tasks with shorter dependencies. In practice, it is often a good idea to try both architectures and compare their performance using cross-validation. Both LSTMs and GRUs have significantly advanced the field of deep learning for sequential data. They have enabled the development of state-of-the-art models for a wide range of applications and have become essential tools for researchers and practitioners working with sequential data. Bidirectional RNNs, architecture and training bidirectional recurrent neural networks, BRNNs, are a type of RNN architecture that processes sequential data in both forward and backward directions. Unlike standard unidirectional RNNs, which only consider past context when making predictions, BRNNs also take into account future context. This can be particularly useful in tasks where the entire sequence is available and both past and future information are relevant for making accurate predictions. The key idea behind BRNNs is to use two separate RNN layers, one that processes the sequence from left to right, the forward layer, and another that processes the sequence from right to left, the backward layer. At each time step, the forward layer computes a hidden state based on the current input and the previous hidden state, just like a standard RNN. The backward layer, on the other hand, computes a hidden state based on the current input and the future hidden state, effectively processing the sequence in reverse. The outputs of the forward and backward layers at each time step are then concatenated or combined in some other way to produce the final output for that time step. This allows the network to capture information from both past and future context when making predictions. The architecture of a BRNN can be formalized as follows: forward layer, H sub f t slash sub equals f, w sub xf slash sub x sub t slash sub plus w sub ff slash sub h sub f t 1 slash sub plus b sub f slash sub, backward layer, H sub b t slash sub equals f, w sub xb slash sub x sub t slash sub plus w sub bb slash sub h sub b t plus 1 slash sub plus b slash sub, output layer, y sub t slash sub equals g, w sub yf slash sub h sub f t slash sub plus w sub yb slash sub h sub b t slash sub plus b sub y slash sub, where x sub t slash sub is the input at time step th, sub f t slash sub and h sub b t slash sub are the hidden states of the forward and backward layers at time step t, respectively. Y sub t slash sub is the output at time step t, w sub xf slash sub, w sub ff slash sub, w sub xb slash sub, w sub bb slash sub, w sub yf slash sub, and w sub yb slash sub are weight matrices. B sub f slash sub, b sub b slash sub, and b sub y slash sub are bias vectors. F and g are activation functions. The forward and backward layers can use any type of RNN cell, such as a basic RNN cell, an LSTM cell, or a GRU cell. BRNNs are trained using backpropagation through time, BPTT, similar to standard RNNs. However, since the backward layer processes the sequence in reverse, the gradients must be computed and propagated in the reverse direction as well. This requires storing the activations for both the forward and backward passes for the entire sequence before computing and applying the weight updates. One limitation of BRNNs is that they require the entire input sequence to be available before processing can begin. This makes them unsuitable for real-time applications where the input sequence is received incrementally. However, in many offline applications, such as text processing and video analysis, this is not a major constraint. BRNNs have been successfully applied to various tasks where considering both past and future context is beneficial. In natural language processing, BRNNs have been used for part-of-speech tagging, named entity recognition, and machine translation. For example, in part-of-speech tagging, knowing the words that come after a given word can help to disambiguate its part of speech. In speech recognition, BRNNs can improve the accuracy of phoneme classification by taking into account both past and future acoustic frames. This can help to resolve ambiguities that arise from co-articulation effects, where the pronunciation of a phoneme is influenced by the surrounding phonemes. BRNNs have also been used in bioinformatics for tasks such as protein secondary structure prediction and DNA sequence analysis, where considering both upstream and downstream context can improve prediction accuracy. Despite their effectiveness, BRNNs are computationally more expensive than unidirectional RNNs, as they require processing the input sequence twice, once in each direction. They also require storing the activations for the entire sequence, which can increase memory usage. However, the improved performance often justifies the additional computational cost. BRNNs are a powerful tool for modeling sequential data when both past and future context are informative for making predictions. Sequence-to-sequence, seek-to-seek, models, architecture and training sequence-to-sequence, seek-to-seek, models are a class of neural network architectures designed for tasks that involve mapping an input sequence to an output sequence, where the input and output sequences can have different lengths. Seek-to-seek models have been particularly successful in tasks such as machine translation, text summarization, and speech recognition. The basic seek-to-seek model consists of two main components, an encoder and a decoder. Both the encoder and the decoder are typically implemented using recurrent neural networks, RNNs, such as LSTMs or GRUs. The encoder processes the input sequence one element at a time and updates its hidden state at each time step. The final hidden state of the encoder, often referred to as the context vector or thought vector, is a fixed-length representation that summarizes the entire input sequence. The decoder then takes this context vector as its initial hidden state and generates the output sequence one element at a time. At each time step, the decoder produces an output element and updates its hidden state based on the previous output and the context vector. In machine translation, for example, the input sequence is a sentence in the source language, and the output sequence is the corresponding translation in the target language. The encoder processes the source sentence and produces a context vector that captures its meaning. The decoder then generates the target sentence based on this context vector. The training of a seek-to-seek model typically involves minimizing a loss function that measures the difference between the predicted output sequence and the true output sequence. For example, in machine translation, the loss function could be the cross-entropy between the predicted words and the true words in the target sentence. The model is trained end-to-end using backpropagation through time, BPTT, to compute the gradients of the loss function with respect to the model parameters. One of the key challenges in seek-to-seek models is how to effectively transfer information from the encoder to the decoder. The context vector needs to capture all the relevant information from the input sequence that is necessary to generate the output sequence. This can be particularly difficult when the input sequence is long. Attention mechanisms have been introduced to address this challenge. Attention allows the decoder to focus on different parts of the input sequence at each time step when generating the output sequence. Instead of relying solely on the final hidden state of the encoder, the decoder has access to all the hidden states of the encoder. At each time step, the decoder computes attention weights that determine how much attention to pay to each of the encoder hidden states. These attention weights are typically computed using a small neural network that takes as input the current hidden state of the decoder and each of the encoder hidden states. The attention weights are then used to compute a weighted sum of the encoder hidden states, which is used as an additional input to the decoder at that time step. Attention mechanisms have significantly improved the performance of seek-to-seek models, particularly for long sequences. They allow the decoder to selectively focus on the most relevant parts of the input sequence when generating each element of the output sequence. This has led to state-of-the-art results in various applications, including machine translation and text summarization. Seek-to-seek models can be extended in various ways to improve their performance and applicability to different tasks. One common extension is to use bidirectional RNNs in the encoder. This allows the encoder to capture information from both past and future context in the input sequence, which can be beneficial for tasks such as machine translation and text summarization. Another extension is to use deeper encoder and decoder networks, with multiple layers of RNN cells. This can allow the model to learn more complex and hierarchical representations of the input and output sequences. However, training very deep seek-to-seek models can be challenging due to the vanishing and exploding gradient problems. Techniques such as skip connections, gradient clipping, and careful initialization can help to mitigate these issues. Beam search is a widely used decoding strategy for seek-to-seek models that can improve the quality of the generated sequences. Instead of greedily selecting the most likely output element at each time step, beam search maintains a list of the k most likely partial sequences, where k is the beam size, and expands them at each time step. This allows the model to explore a larger portion of the search space and can lead to better overall sequence quality. Seek-to-seek models have been successfully applied to a wide range of tasks beyond machine translation. In text summarization, for example, the input sequence is a document, and the output sequence is a summary of the document. Seek-to-seek models with attention mechanisms have achieved state-of-the-art results in both extractive and abstractive summarization. In speech recognition, seek-to-seek models can be used to map a sequence of acoustic features to a sequence of words or characters. This approach, known as end-to-end speech recognition, has gained popularity in recent years as it eliminates the need for separate acoustic, pronunciation, and language models. Seek-to-seek models have also been applied to tasks such as image captioning, video captioning, and code generation. In image captioning, for example, a convolutional neural network, CNN, can be used as the encoder to extract visual features from an image, and an RNN can be used as the decoder to generate a caption based on these features. Despite their success, seek-to-seek models also have some limitations. One limitation is that they are typically trained using teacher forcing, where the ground truth output at each time step is fed as input to the decoder at the next time step. This can lead to a discrepancy between training and inference, where during inference the model has to rely on its own predictions. Another limitation is that seek-to-seek models can be sensitive to the length of the input sequence. They may perform poorly on sequences that are much longer or shorter than those seen during training. Developing more robust and efficient seek-to-seek models is an active area of research. Techniques such as reinforcement learning, adversarial training, and curriculum learning have been explored to improve the training and generalization of seek-to-seek models. Seek-to-seek models have become a fundamental building block in many natural language processing and sequence modeling tasks. Applications of RNNs in natural language processing, NLP language modeling, machine translation, and more recurrent neural networks, RNNs, have had a profound impact on the field of natural language processing, NLP, enabling significant advances in various tasks that involve understanding and generating human language. Their ability to process sequential data and capture long-range dependencies has made them a powerful tool for modeling the complexities of natural language. Language modeling is one of the most fundamental tasks in NLP and has been a major application area for RNNs. A language model is a probability distribution over sequences of words. Given a sequence of words, a language model assigns a probability to the entire sequence. Language models are used in various NLP applications, such as speech recognition, machine translation, and text generation. RNN-based language models, particularly those using LSTM or GRU cells, have achieved state-of-the-art results in language modeling. These models are typically trained to predict the next word in a sequence given the preceding words. At each time step, the RNN takes the current word as input and updates its hidden state. The output layer then produces a probability distribution over the vocabulary, representing the probabilities of the next word. RNN language models have been shown to capture complex linguistic phenomena, such as long-range dependencies, syntactic structure, and semantic coherence. They have also been used as a pre-training step for other NLP tasks, where a language model is first trained on a large text corpus and then fine-tuned for a specific task, such as text classification or question answering. Machine translation is another area where RNNs have had a major impact. RNN-based sequence-to-sequence, seek-to-seek, models, particularly those with attention mechanisms, have become the dominant approach for machine translation. These models can translate a sentence from a source language to a target language by encoding the source sentence into a fixed-length vector representation and then decoding it into the target sentence. Attention mechanisms have significantly improved the performance of seek-to-seek models for machine translation by allowing the decoder to focus on different parts of the source sentence when generating each word in the target sentence. This has led to state-of-the-art results on various machine translation benchmarks. RNNs have also been widely used for text classification tasks, such as sentiment analysis, topic classification, and spam detection. For these tasks, an RNN is used to process the input text sequence, and the final hidden state or a combination of hidden states is used as input to a classifier, typically a fully connected layer with a softmax activation. Bidirectional RNNs, which process the input sequence in both directions, are often used in text classification to capture both past and future context. Named entity recognition, NR, is another important NLP task where RNNs have been successfully applied. NER involves identifying and classifying named entities in text, such as person names, organizations, and locations. RNN-based models, particularly bidirectional LSTMs with a conditional random field, CRF, layer on top, have achieved state-of-the-art results on NER benchmarks. RNNs have also been used for other NLP tasks, such as part-of-speech tagging, parsing, and coreference resolution. They have been combined with other types of neural networks, such as convolutional neural networks, CNNs, to create hybrid models that can leverage both local and sequential information in text. Despite the success of RNNs in NLP, they have some limitations. One limitation is their sequential nature, which makes them difficult to parallelize and can lead to slow training and inference, especially for very long sequences. Another limitation is their difficulty in capturing very long-range dependencies, despite the improvements offered by LSTMs and GRUs. Transformers, which use self-attention mechanisms to capture relationships between all words in a sequence in parallel, have recently emerged as a powerful alternative to RNNs in many NLP tasks. However, RNNs remain an important tool in the NLP toolbox and continue to be an active area of research. Applications of RNNs in other domains, speech recognition, time series analysis, and more beyond natural language processing, recurrent neural networks, RNNs, have found applications in a variety of other domains that involve sequential data. Their ability to model temporal dependencies and learn from sequences of varying lengths makes them a versatile tool for many tasks. One prominent application area is speech recognition, which aims to convert spoken language into text. RNNs, particularly LSTMs and GRUs, have been a key component in state-of-the-art speech recognition systems. In acoustic modeling, RNNs are used to model the temporal dependencies between acoustic features extracted from the speech signal. They can map a sequence of acoustic feature vectors to a sequence of phonemes or words. Bidirectional RNNs are often used in speech recognition to capture both past and future context in the acoustic signal. This can help to improve the accuracy of phoneme recognition, especially in cases where the pronunciation of a phoneme is influenced by the surrounding phonemes. Connectionist temporal classification, CTC, is a popular technique used with RNNs for speech recognition. CTC allows the model to learn an alignment between the input acoustic sequence and the output label sequence, even when the lengths of the sequences are different. This is particularly useful in speech recognition, where the number of acoustic frames is typically much larger than the number of phonemes or words. End-to-end speech recognition systems, which directly map the raw audio waveform to text using a single neural network, often employ RNNs or a combination of CNNs and RNNs. These systems have achieved impressive results in recent years, rivaling or surpassing the performance of traditional systems that use separate acoustic, pronunciation, and language models. RNNs have also been successfully applied to time series analysis, which involves modeling and forecasting data that is collected over time. Applications of time series analysis include stock price prediction, weather forecasting, anomaly detection, and sales forecasting. RNNs can capture the temporal dependencies in time series data and learn to make predictions based on past observations. LSTMs and GRUs are particularly well suited for time series analysis due to their ability to learn long-range dependencies. In finance, for example, RNNs have been used to model and predict stock prices, volatility, and other financial indicators. They can capture complex patterns and nonlinear relationships in financial time series data that may be difficult to model using traditional statistical methods. In weather forecasting, RNNs can be used to model the temporal dynamics of meteorological variables, such as temperature, humidity, and wind speed. They can learn to make predictions based on past weather patterns and can incorporate data from multiple sources, such as weather stations and satellites. RNNs have also been used for anomaly detection in time series data. By learning the normal patterns in the data, RNNs can identify deviations from these patterns that may indicate anomalies or unusual events. This has applications in various domains, such as fraud detection, network intrusion detection, and industrial process monitoring. Beyond speech recognition and time series analysis, RNNs have found applications in other domains, such as video analysis, music generation, and robotics. In video analysis, RNNs can be used to model the temporal dynamics of video sequences, for tasks such as action recognition, video captioning, and object tracking. In music generation, RNNs can learn to generate new musical sequences based on the patterns and structures learned from existing music. They have been used to generate music in various styles and genres, often with impressive results. In robotics, RNNs can be used to model the temporal dependencies in sensor data and to learn control policies for robots. For example, RNNs can be used to process sequences of sensor readings from a robot's joints and actuators and to generate sequences of motor commands to control the robot's movements. The application of RNNs to these diverse domains demonstrates their versatility and power as a tool for modeling sequential data. Challenges and future directions in RNN research. Despite the significant progress in recurrent neural network (RNN) research and their successful application to various domains, several challenges remain, and new research directions are emerging. One of the main challenges in training RNNs is the vanishing and exploding gradient problems, which can make it difficult for the network to learn long-range dependencies. While LSTMs and GRUs have helped to mitigate these issues, they can still be a problem for very long sequences or complex architectures. Developing more effective architectures and training algorithms for capturing long-range dependencies is an ongoing area of research. Another challenge is the computational cost of training and deploying RNNs, particularly for long sequences. The sequential nature of RNNs makes them difficult to parallelize, and the need to process each element in the sequence one at a time can lead to slow training and inference. This is particularly problematic for applications that require real-time processing, such as speech recognition and online machine translation. Several approaches have been proposed to address the computational cost of RNNs. One approach is to use model compression techniques, such as pruning and quantization, to reduce the size and complexity of the network. Another approach is to develop more efficient RNN architectures, such as quasi-recurrent neural networks, QRNNs, which combine convolutional layers with a simplified form of recurrence to enable parallel computation across time steps. The development of specialized hardware for accelerating RNNs, such as custom ASICs and FPGAs, is also an active area of research. Another important research direction is the development of more interpretable and explainable RNNs. While RNNs can achieve impressive performance on various tasks, they are often considered black boxes due to their complex, nonlinear nature. Understanding how RNNs make decisions and what they have learned from the data is crucial for building trust in these models and for debugging and improving them. Techniques such as attention mechanisms, which allow the model to focus on specific parts of the input sequence when making predictions, can provide some degree of interpretability. Visualizing the hidden state activations and analyzing the learned weights can also provide insights into the model's behavior. Developing more formal methods for analyzing and interpreting RNNs, such as methods for extracting symbolic rules or finite state machines from trained RNNs, is an open research problem. Another area of active research is the development of RNN architectures that can handle structured data, such as graphs and trees. Recursive neural networks, which are a generalization of RNNs to tree structures, have been proposed for tasks such as natural language parsing and program analysis. Graph neural networks, which can operate on arbitrary graph-structured data, have also been combined with RNNs to model sequences of graphs or graphs with temporal dependencies. The intersection of RNNs with other areas of machine learning, such as reinforcement learning and unsupervised learning, is also an exciting research direction. RNNs have been used as a key component in deep reinforcement learning algorithms, particularly for tasks that involve partial observability or require memory of past events. They have also been used in unsupervised learning settings, such as in variational autoencoders and generative adversarial networks, to model sequences and generate new data. Finally, the application of RNNs to new domains and tasks is an ongoing area of exploration. As the capabilities of RNNs continue to improve and new architectures and algorithms are developed, we can expect to see them being applied to an even wider range of problems, potentially leading to new breakthroughs and discoveries. The field of recurrent neural networks is constantly evolving, driven by the need to address the limitations of current models and to expand their applicability to new and challenging problems. Lesson 13. Transfer Learning and Fine-Tuning. Introduction to Transfer Learning. Transfer learning is a powerful technique in deep learning that allows us to leverage knowledge learned from one task or domain to improve performance on a different, but related, task or domain. Instead of training a model from scratch for each new task, transfer learning enables us to reuse a pre-trained model as a starting point and adapt it to the specific task at hand. This can significantly reduce the amount of data and computational resources required to train a high-performing model, especially when the new task has limited labeled data available. The core idea behind transfer learning is that features learned for one task can often be useful for other related tasks. For example, a model trained to classify images of objects in a large dataset like ImageNet will learn a hierarchy of visual features, from simple edges and textures in the lower layers to complex object parts and shapes in the higher layers. These learned features can be transferred to other computer vision tasks, such as object detection, image segmentation, or even tasks in different domains, such as medical image analysis. The process of transfer learning typically involves two main steps: pre-training and fine-tuning. In the pre-training step, a model is trained on a large source task or dataset, often referred to as the pre-training task or dataset. This step allows the model to learn a rich set of features that are generally useful for the domain. In the fine-tuning step, the pre-trained model is adapted to the target task by continuing the training process on the target dataset. The weights of the pre-trained model are used as the initialization for the fine-tuning process, and some or all of the layers may be updated during training. Transfer learning is particularly useful when the target task has limited labeled data available. By leveraging the knowledge learned from a related task with abundant data, transfer learning can help to overcome the data scarcity problem and improve the performance of the model on the target task. Transfer learning has been successfully applied in various domains, including computer vision, natural language processing, and speech recognition. In computer vision, models pre-trained on ImageNet, such as VGG, ResNet, and Inception, have become widely used starting points for many tasks. In natural language processing, pre-trained language models, such as BERT and GPT, have revolutionized the field by capturing rich syntactic and semantic information about language from massive text corpora. These pre-trained models can be fine-tuned for various downstream tasks, often with significantly less labeled data than would be required to train a model from scratch. Despite its success, transfer learning also has some limitations. One potential issue is negative transfer, which can occur when the source and target tasks are too dissimilar, and the knowledge learned from the source task does not help or even hurts performance on the target task. Another challenge is determining which layers to freeze or fine-tune and how to set the learning rates for different layers during the fine-tuning process. Developing more principled and automated methods for transfer learning is an active area of research. Pre-training and fine-tuning, adapting models to new tasks. The process of transfer learning typically involves two main stages, pre-training and fine-tuning. Pre-training is the initial stage where a model is trained on a large source task or dataset. This task is often chosen to be a general task within the domain of interest, for which a large amount of labeled data is available. For example, in computer vision, the source task is often image classification on the ImageNet dataset, which contains millions of labeled images from thousands of categories. In natural language processing, the source task might be language modeling on a massive text corpus, such as Wikipedia or a large collection of books. During pre-training, the model learns to extract useful features from the input data. In the case of a convolutional neural network, CNN, pre-trained on ImageNet, the model learns a hierarchy of visual features, from simple edges and textures in the lower layers to complex object parts and shapes in the higher layers. In the case of a language model, the model learns to represent words and sentences in a way that captures their syntactic and semantic relationships. The pre-trained model can be seen as a good initialization point for other tasks in the same domain. The learned features are often general enough to be useful for a wide range of tasks, even if they are not exactly the same as the pre-training task. For example, features learned from classifying objects in ImageNet can be useful for tasks such as object detection, image segmentation, and even medical image analysis. Fine-tuning is the second stage of transfer learning, where the pre-trained model is adapted to the target task. This is done by continuing the training process on the target dataset, using the pre-trained weights as the starting point. During fine-tuning, the final layer or layers of the pre-trained model, which are specific to the source task, are typically replaced with new layers that are appropriate for the target task. For example, if the pre-trained model was trained to classify 1,000 categories in ImageNet, but the target task is to classify only 10 categories, the final fully connected layer would be replaced with a new layer that has 10 output units. The weights of the pre-trained layers can either be frozen or fine-tuned during this process. Freezing the weights means that they are not updated during training on the target task. This can be useful when the target dataset is very small, as it helps to prevent overfitting. Fine-tuning the pre-trained weights, on the other hand, allows the model to adapt the learned features to the target task. This can lead to better performance when the target dataset is larger or when the target task is significantly different from the source task. One common strategy is to use a smaller learning rate for the pre-trained layers compared to the newly added layers. This allows the pre-trained weights to be gently adapted to the target task while preserving the knowledge learned from the source task. Another important consideration during fine-tuning is the choice of which layers to freeze or fine-tune. In general, the lower layers of a deep neural network tend to learn more general features, while the higher layers learn more task-specific features. Therefore, when the target task is similar to the source task, it may be sufficient to fine-tune only the higher layers and freeze the lower layers. When the target task is very different from the source task, it may be necessary to fine-tune more layers or even all the layers of the pre-trained model. The process of fine-tuning often involves some experimentation and validation to determine the best strategy for a given task and dataset. Techniques such as cross-validation can be used to evaluate different fine-tuning strategies and select the best one. Transfer learning through pre-training and fine-tuning has become a standard practice in many areas of deep learning, enabling the development of high-performing models with significantly less data and computational resources than training from scratch. Feature extraction versus fine-tuning. Choosing the right approach when applying transfer learning, one important decision is whether to use the pre-trained model as a fixed feature extractor or to fine-tune some or all of its layers. The choice between these two approaches depends on several factors, including the similarity between the source and target tasks, the size of the target dataset, and the available computational resources. Using a pre-trained model as a fixed feature extractor involves removing the final classification layer, or layers, of the pre-trained model and treating the remaining layers as a fixed feature extraction pipeline. The output of these layers for a given input is treated as a fixed-length feature vector that represents the input. These feature vectors can then be used as input to a new classifier, such as a support vector machine or a simple neural network, which is trained from scratch on the target task. This approach can be particularly useful when the target dataset is very small and fine-tuning the entire network might lead to overfitting. By using the pre-trained model as a fixed feature extractor, we can leverage the powerful features learned from the large source dataset without the risk of overfitting to the small target dataset. This approach is also computationally efficient, as the features only need to be computed once for each input and can be stored for later use. However, using a pre-trained model as a fixed feature extractor has limitations. It assumes that the features learned on the source task are directly applicable to the target task without any modification. This may not be the case if the target task is significantly different from the source task or if the target domain has different characteristics than the source domain. In such cases, fine-tuning the pre-trained model can lead to better performance. Fine-tuning involves updating the weights of some or all of the layers of the pre-trained model during training on the target task. This allows the model to adapt the learned features to the specific characteristics of the target task and dataset. Fine-tuning can be particularly beneficial when the target dataset is larger or when the target task is moderately different from the source task. When fine-tuning, it is common to use a smaller learning rate for the pre-trained layers compared to the newly added layers. This allows the pre-trained weights to be gently adapted to the target task while preserving the knowledge learned from the source task. It is also common to start by freezing the lower layers and only fine-tuning the higher layers, and then gradually unfreezing more layers as training progresses. The choice between feature extraction and fine-tuning also depends on the available computational resources. Fine-tuning requires more computation than feature extraction, as it involves backpropagation through the entire network. If computational resources are limited, feature extraction may be the only feasible option. In practice, the best approach often involves experimentation and validation. One can start by using the pre-trained model as a fixed feature extractor and then try fine-tuning different portions of the network to see if it improves performance. Cross-validation can be used to compare different approaches and select the best one for the specific task and dataset. It is also worth noting that the choice between feature extraction and fine-tuning is not binary. One can adopt intermediate approaches, such as fine-tuning some layers while keeping others fixed, or using different learning rates for different layers. The optimal strategy depends on the specific characteristics of the target task and dataset, as well as the available computational resources. In recent years, there has been a trend towards end-to-end fine-tuning of large pre-trained models, particularly in natural language processing. Models like BERT and GPT are pre-trained on massive text corpora and then fine-tuned end-to-end on downstream tasks. This approach has led to significant improvements in performance across a wide range of NLP tasks. Ultimately, the choice between feature extraction and fine-tuning, and the specific strategy adopted, should be guided by empirical evaluation and a good understanding of the problem at hand. Domain adaptation, handling differences between source and target domains. Domain adaptation is a subfield of transfer learning that deals with situations where the source and target domains have different data distributions. This can happen when the data used for pre-training a model is drawn from a different distribution than the data encountered in the target task. For example, a model pre-trained on images of real objects might be applied to images of paintings or sketches, or a model pre-trained on text from news articles might be applied to social media posts. In such cases, directly applying a pre-trained model to the target domain may lead to poor performance due to the domain shift. Domain adaptation techniques aim to bridge the gap between the source and target domains, allowing the knowledge learned from the source domain to be effectively transferred to the target domain. One common approach to domain adaptation is to learn domain-invariant features. These are features that are both discriminative for the task at hand and invariant to the differences between the source and target domains. One way to learn such features is to use a domain adversarial loss during training. This involves adding a domain classifier to the network that tries to predict the domain, source or target, of the input based on the learned features. The feature extractor is then trained to fool the domain classifier, encouraging it to learn features that are indistinguishable between the two domains. Another approach is to use instance weighting or importance weighting. This involves assigning weights to the samples from the source domain based on their similarity to the target domain. Samples that are more similar to the target domain are given higher weights during training, effectively making the source domain distribution closer to the target domain distribution. Maximum mean discrepancy, MMD, is another technique used for domain adaptation. MMD measures the distance between the feature distributions of the source and target domains in a reproducing kernel Hilbert space. By minimizing the MMD loss during training, the model learns to map both the source and target data to a common feature space where their distributions are similar. Adversarial methods have also been applied to domain adaptation. Generative adversarial networks, GANs, can be used to learn a mapping from the source domain to the target domain, such that the mapped source data is indistinguishable from the target data to a discriminator network. This can help to align the distributions of the two domains and improve the performance of models trained on the source domain when applied to the target domain. Domain adaptation can also involve unsupervised or semi-supervised learning on the target domain. For example, one can use a pre-trained model to generate pseudo-labels for the unlabeled target data and then fine-tune the model using these pseudo-labels. Self-training is another technique where the model is iteratively trained on its own predictions on the target data. The choice of domain adaptation technique depends on the specific characteristics of the source and target domains, the amount of labeled data available in each domain, and the type of model being used. In some cases, a combination of techniques may be most effective. Domain adaptation is an active area of research in transfer learning and has important applications in various fields. For example, in medical image analysis, domain adaptation can help to transfer knowledge learned from one type of medical image, e.g., MRI, to another, e.g., CT, or from one hospital or scanner to another. In autonomous driving, domain adaptation can help to adapt models trained in simulation or in one geographic location to real-world driving or to new locations. As deep learning models are increasingly deployed in diverse real-world settings, the ability to adapt to new domains and handle distribution shifts will become even more crucial. Domain adaptation techniques provide a powerful set of tools for addressing these challenges and improving the generalization and robustness of deep learning models. Applications in computer vision, transfer learning for image classification, object detection, and more. Transfer learning has become a cornerstone of many successful applications of deep learning in computer vision. By leveraging models pre-trained on large-scale datasets like ImageNet, researchers and practitioners have achieved state-of-the-art results on a wide range of tasks, often with significantly less data and computational resources than would be required to train a model from scratch. Image classification is one of the most common applications of transfer learning in computer vision. Models pre-trained on ImageNet, such as VGG, ResNet, Inception, and EfficientNet, have learned rich hierarchies of visual features that can be effectively transferred to other image classification tasks. By fine-tuning these pre-trained models on new datasets, it is often possible to achieve high accuracy with relatively small amounts of labeled data. This has enabled the development of specialized image classifiers for various domains, such as medical imaging, satellite image analysis, and fine-grained classification of plants and animals. Transfer learning has also revolutionized object detection, the task of identifying and localizing objects within an image. Object detection models typically consist of two main components: a backbone network that extracts features from the input image, and a detection head that predicts bounding boxes and class labels for objects. Transfer learning can be applied by using a pre-trained CNN, such as ResNet or Inception, as the backbone network. The detection head is then trained from scratch on the target dataset, while the backbone is either fine-tuned or kept frozen. This approach has been used in popular object detection frameworks such as FASTER RCNN, SSD, and YOLO. By leveraging pre-trained backbones, these models can achieve high accuracy on object detection benchmarks, such as COCO and Pascal VOC, with significantly less training data than would be required to train the entire model from scratch. Image segmentation, the task of assigning a label to each pixel in an image, has also benefited from transfer learning. Models such as UNet and DeepLab, which use encoder-decoder architectures with skip connections, often use pre-trained CNNs as the encoder part of the network. The pre-trained encoder provides a strong starting point for learning to segment images, while the decoder is trained to generate pixel-level predictions. This approach has been particularly successful in medical image segmentation, where labeled data is often scarce and expensive to obtain. Transfer learning has also been applied to other computer vision tasks, such as facial recognition, pose estimation, and action recognition. In facial recognition, pre-trained models can be used to extract facial features, which are then used to train a classifier or a similarity metric for face identification or verification. In pose estimation, pre-trained models can be used to initialize the weights of a network that predicts the locations of key points on the human body. In action recognition, pre-trained models can be used to extract features from video frames, which are then fed into a recurrent network or a 3D CNN to classify actions. The success of transfer learning in computer vision can be attributed to several factors. First, the features learned by deep CNNs on large-scale datasets like ImageNet are often highly generalizable and transferable to other visual tasks. Second, the availability of high-quality pre-trained models and easy-to-use deep learning libraries has made it straightforward for researchers and practitioners to apply transfer learning in their own work. Third, the fine-tuning process allows the pre-trained models to be adapted to the specific characteristics of the target task and dataset, leading to improved performance. Despite its success, transfer learning in computer vision also faces some challenges. One challenge is the potential for negative transfer when the target task is very different from the pre-training task. In such cases, fine-tuning a pre-trained model may not be effective, and training from scratch or using unsupervised or self-supervised learning on the target data may be better alternatives. Another challenge is the computational cost of fine-tuning very large pre-trained models, which may require specialized hardware and significant amounts of memory. Developing more efficient and effective methods for transfer learning in computer vision is an active area of research. Techniques such as knowledge distillation, network pruning, and quantization can help to reduce the computational cost of fine-tuning in deploying pre-trained models. Applications in natural language processing, transfer learning for text classification, sentiment analysis, and more transfer learning has had a transformative impact on the field of natural language processing, NLP, enabling the development of state-of-the-art models for a wide range of tasks with significantly less labeled data than was previously required. The key innovation that has driven this progress is the development of pre-trained language models, which are large neural networks trained on massive text corpora using self-supervised learning objectives. These models learn rich representations of words and sentences that capture syntactic and semantic information, and they can be fine-tuned for various downstream tasks with relatively small amounts of labeled data. One of the earliest and most influential pre-trained language models is Word2Vec, which learns word embeddings by predicting the context words given a target word or vice versa. Word2Vec and related methods, such as glove and fast text, produce fixed-length vector representations for each word in the vocabulary, capturing semantic relationships between words. These pre-trained word embeddings can be used as input features for various NLP tasks, such as text classification, sentiment analysis, and named entity recognition, often leading to improved performance compared to using randomly initialized embeddings. More recently, models such as ELMO, ULM-FIT, BERT, and GPT have extended the idea of pre-training to the level of entire sentences and documents. ELMO, embeddings from language models, uses a deep, bidirectional LSTM to generate contextualized word representations, where the representation of each word depends on the entire input sentence. ULM-FIT, Universal Language Model Fine-Tuning, introduced techniques for effectively fine-tuning a pre-trained language model to various text classification tasks, such as using discriminative fine-tuning and gradual unfreezing of layers. BERT, Bidirectional Encoder Representations from Transformers, is a transformer-based model that is pre-trained using two self-supervised objectives, masked language modeling, where the model predicts randomly masked words in the input, and next sentence prediction, where the model predicts whether two input sentences are consecutive in the original text. BERT learns deep bidirectional representations by jointly conditioning on both left and right context in all layers. GPT, Generative Pre-trained Transformer, is another transformer-based model that is pre-trained using a language modeling objective, where the model predicts the next word in a sequence given the previous words. Unlike BERT, GPT uses a left-to-right, autoregressive architecture. These pre-trained language models can be fine-tuned for a wide range of NLP tasks by adding a task-specific output layer on top of the pre-trained model and training on labeled data for the target task. This approach has led to significant improvements in performance across various benchmarks, including text classification, question answering, natural language inference, and coreference resolution. For example, in text classification, a pre-trained model like BERT can be fine-tuned by adding a classification layer on top of the final hidden state corresponding to the special, CLS, token, which is used to represent the entire input sequence. The entire model is then trained on the target dataset, updating both the pre-trained weights and the weights of the classification layer. This approach often achieves state-of-the-art results with significantly less labeled data than training a model from scratch. In sentiment analysis, transfer learning can be used to adapt a pre-trained language model to the specific domain or style of the target dataset. For example, a model pre-trained on general text can be fine-tuned on a dataset of product reviews to learn sentiment-specific representations and improve the accuracy of sentiment classification. Transfer learning has also been applied to other NLP tasks, such as named entity recognition, part-of-speech tagging, and parsing. In these tasks, pre-trained word embeddings or contextualized representations from models like ELMO or BERT can be used as input features to the task-specific model, often leading to improved performance. One of the advantages of using pre-trained language models is that they can capture long-range dependencies and contextual information that are difficult to learn from scratch with limited data. They also encode a significant amount of linguistic knowledge learned from the massive pre-training corpora, which can be beneficial for various downstream tasks. Despite the impressive success of transfer learning in NLP, there are still challenges and open questions. One challenge is how to effectively adapt pre-trained models to domains that are very different from the pre-training data. Techniques such as domain-adaptive pre-training and adversarial training have been explored to address this challenge. Another challenge is the computational cost of fine-tuning very large pre-trained models, which can have hundreds of millions or even billions of parameters. Methods such as parameter-efficient fine-tuning, which involves updating only a small subset of the model parameters, and knowledge distillation, which involves training a smaller student model to mimic the behavior of a larger teacher model, are being developed to address this issue. The development of pre-trained language models and the application of transfer learning have fundamentally changed the landscape of NLP. Challenges and limitations of transfer learning, negative transfer, domain shift, and more. While transfer learning has proven to be a powerful technique in many applications of deep learning, it also faces several challenges and limitations. Understanding these challenges is crucial for effectively applying transfer learning and for guiding future research in this area. One of the main limitations of transfer learning is the potential for negative transfer. Negative transfer occurs when the knowledge learned from the source task or domain does not help or even hurts performance on the target task or domain. This can happen when the source and target tasks are too dissimilar, or when the features learned from the source task are not relevant or even misleading for the target task. For example, a model pre-trained on natural images may not be effective for medical image analysis if the visual features that are important for medical diagnosis are very different from those learned from natural images. Domain shift or domain adaptation is a related challenge that arises when the distribution of the source data is different from the distribution of the target data. Even if the source and target tasks are similar, differences in the data distribution can lead to poor performance when applying a pre-trained model directly to the target domain. For example, a model trained on images taken in daylight may perform poorly on images taken at night or under different lighting conditions. Several techniques have been developed to address domain shift, such as domain adversarial training, instance weighting, and distribution matching. However, effectively adapting to new domains remains a challenging problem, particularly when the domain shift is large or when there is limited labeled data available in the target domain. Another limitation of transfer learning is the difficulty of determining the optimal fine-tuning strategy. Fine-tuning involves making choices about which layers to freeze or unfreeze, what learning rates to use for different layers, and how many epochs to train for. These choices can significantly impact the performance of the fine-tuned model, and finding the best strategy often requires experimentation and validation. The size and quality of the pre-trained model also play a crucial role in the success of transfer learning. Larger and deeper pre-trained models, such as ResNet 152 or BERT Large, often lead to better transfer learning performance compared to smaller models. However, fine-tuning very large models can be computationally expensive and may require specialized hardware, such as GPUs with large memory capacity. The quality and relevance of the pre-training data are also important factors. Pre-training on a dataset that is closely related to the target task is more likely to yield good results than pre-training on a very different dataset. However, in some cases, even pre-training on a seemingly unrelated dataset can be beneficial, as it may help the model learn more general and robust features. Another challenge in transfer learning is the potential for the pre-trained model to encode biases present in the source data. If the pre-training dataset contains biases related to gender, race, or other sensitive attributes, these biases may be transferred to the target task, leading to unfair or discriminatory outcomes. Addressing bias in pre-trained models and ensuring fairness in transfer learning is an important area of research. Catastrophic forgetting is another issue that can arise in transfer learning, particularly when fine-tuning a pre-trained model on a sequence of tasks. Catastrophic forgetting refers to the phenomenon where a model forgets previously learned knowledge when trained on new data. In the context of transfer learning, this can manifest as a significant drop in performance on the original source task after fine-tuning on the target task. Techniques such as elastic weight consolidation, EWC, and progressive neural networks have been proposed to mitigate catastrophic forgetting in transfer learning and continual learning settings. Despite these challenges and limitations, transfer learning remains a powerful and widely used technique in deep learning. Best practices for transfer learning and fine-tuning, tips and techniques for effective adaptation. To effectively apply transfer learning and fine-tuning in practice, it is important to follow some best practices and guidelines that have been developed through research and experience. These tips and techniques can help to maximize the benefits of transfer learning and avoid common pitfalls. One of the first considerations when applying transfer learning is the choice of the pre-trained model. It is generally a good idea to choose a model that was pre-trained on a task and dataset that are as similar as possible to the target task and dataset. For example, if the target task is image classification, a model pre-trained on ImageNet is likely to be a good starting point. If the target task is in the medical domain, a model pre-trained on medical images, if available, may be more suitable. It is also important to consider the size and architecture of the pre-trained model. Larger and deeper models, such as ResNet 152 or BERT Large, often lead to better transfer learning performance, but they also require more computational resources and may be more prone to overfitting if the target dataset is small. It may be necessary to experiment with different pre-trained models to find the best one for the specific task and dataset. When fine-tuning a pre-trained model, it is generally recommended to start by freezing the weights of the lower layers and only updating the weights of the higher layers. This is because the lower layers tend to learn more general features that are likely to be transferable across tasks, while the higher layers learn more task-specific features. By freezing the lower layers, we can prevent overfitting to the target dataset and preserve the knowledge learned from the source task. As training progresses, it may be beneficial to gradually unfreeze more layers, allowing the model to adapt the pre-trained features to the target task. This process is sometimes referred to as gradual unfreezing. It is also a good practice to use a smaller learning rate for the pre-trained layers compared to the newly added layers. This allows the pre-trained weights to be gently adapted to the target task while preserving the knowledge learned from the source task. The learning rate is a crucial hyperparameter in fine-tuning, and it often needs to be set much lower than when training from scratch. A learning rate that is too high can cause the model to quickly forget the knowledge learned during pre-training, while a learning rate that is too low can lead to slow convergence or getting stuck in a suboptimal solution. Techniques such as learning rate schedules, where the learning rate is decreased over time, can be helpful in fine-tuning. Data augmentation can also be beneficial when fine-tuning, particularly when the target dataset is small. Applying transformations such as random crops, flips, and rotations to the input data can help to prevent overfitting and improve the generalization ability of the fine-tuned model. It is important to monitor the performance of the model on a validation set during fine-tuning and to use early stopping to prevent overfitting. Early stopping involves stopping the training process when the performance on the validation set starts to degrade, even if the performance on the training set is still improving. Regularization techniques, such as L2 regularization and dropout, can also be used during fine-tuning to prevent overfitting. However, it may be necessary to adjust the strength of these regularizers compared to when training from scratch, as the pre-trained weights may already provide some regularization effect. When using a pre-trained model as a fixed feature extractor, it is often beneficial to apply some form of dimensionality reduction or feature selection to the extracted features before using them to train a new classifier. Techniques such as principal component analysis, PCA, or T-distributed stochastic neighbor embedding, TSNE, can be used to reduce the dimensionality of the feature vectors and remove redundant or noisy features. It is also important to consider the ethical implications of transfer learning, particularly when using pre-trained models that may encode biases present in the source data. Care should be taken to evaluate the pre-trained model for potential biases and to mitigate these biases when fine-tuning for the target task. Techniques such as fairness-aware training and debiasing methods can be used to address these issues. In summary, effective transfer learning and fine-tuning require careful consideration of the choice of pre-trained model, the fine-tuning strategy, and the specific characteristics of the target task and dataset. By following these best practices and guidelines, practitioners can maximize the benefits of transfer learning and develop high-performing models with less data and computational resources. Future directions in transfer learning, cross-modal, cross-lingual, and beyond transfer learning is a rapidly evolving field, and many exciting research directions are being explored to further enhance its capabilities and expand its applicability. One important direction is cross-modal transfer learning, which aims to transfer knowledge between different modalities of data, such as images, text, and audio. Cross-modal transfer learning can enable the development of models that can learn from one modality and perform tasks in another. For example, a model trained on images and their corresponding captions could be used to generate captions for new images or to retrieve images based on textual descriptions. This could have significant implications for tasks such as image and video retrieval, cross-modal translation, and multimodal reasoning. One approach to cross-modal transfer learning is to learn a joint embedding space where different modalities can be represented and compared. For example, a model can be trained to map images and text to a common embedding space such that images and their corresponding captions are close to each other in the embedding space. This can be achieved using techniques such as canonical correlation analysis, CCA, or by training a deep neural network with a contrastive loss that encourages similar items to have similar embeddings and dissimilar items to have different embeddings. Another approach is to use a pre-trained model from one modality as a teacher to train a model in another modality. For example, a pre-trained language model can be used to generate pseudo-labels for unlabeled images, which can then be used to train an image classifier. This can help to leverage the vast amount of unlabeled data available in one modality to improve performance in another modality where labeled data is scarce. Cross-lingual transfer learning is another important research direction, particularly in natural language processing. The goal is to leverage knowledge learned from high-resource languages, such as English, to improve performance on low-resource languages, where labeled data is limited. One approach is to train a multilingual model on data from multiple languages and then fine-tune it on the target low-resource language. This allows the model to learn cross-lingual representations that capture commonalities between languages. Another approach is to use machine translation to translate the labeled data from a high-resource language to the low-resource language and then train a model on the translated data. This can help to augment the limited labeled data available in the low-resource language. Zero-shot and few-shot learning are also closely related to transfer learning and are gaining increasing attention. In zero-shot learning, the goal is to learn a model that can recognize or classify objects from classes that were not seen during training. This requires the model to generalize to new classes based on some form of side information, such as semantic descriptions or attributes of the classes. Few-shot learning, on the other hand, aims to learn a model that can quickly adapt to new tasks or classes with only a few examples. Meta-learning, which was discussed in Lesson 9, is a powerful approach for few-shot learning. By training a model on a distribution of tasks, it can learn to quickly adapt to new tasks with limited data. Transfer learning is also being explored in the context of reinforcement learning. One approach is to transfer knowledge from a pre-trained policy in a source task to a new target task. This can help to speed up learning in the target task by providing a good initialization for the policy or by guiding exploration. Another approach is to learn a model of the environment in the source task and then transfer this model to the target task. This can help the agent to learn more efficiently in the target task by leveraging its understanding of the environment dynamics. Domain adaptation and domain generalization are also important research directions in transfer learning. Domain adaptation aims to address the problem of domain shift, where the distribution of the target data is different from that of the source data. Domain generalization, on the other hand, aims to learn models that can generalize to new, unseen domains without the need for explicit adaptation. These techniques are crucial for deploying deep learning models in real-world settings, where the data distribution may change over time or where the model may encounter new environments or conditions. The development of more principled and automated methods for transfer learning is another important research direction. This includes developing methods for automatically selecting the best pre-trained model for a given task, determining which layers to freeze or fine-tune, and setting the learning rates and other hyperparameters. It also includes developing methods for evaluating the transferability of knowledge between tasks and for predicting the performance of transfer learning in new settings. As deep learning continues to advance and find applications in increasingly diverse domains, transfer learning will play an ever more important role in enabling the development of high-performing models with limited data and computational resources. Lesson 14, Unsupervised and Self-Supervised Learning. Introduction to Unsupervised and Self-Supervised Learning. Unsupervised learning is a branch of machine learning that deals with learning from unlabeled data, that is, data without any specific output or target variable associated with it. Unlike supervised learning, where the model is trained on input-output pairs, unsupervised learning aims to discover patterns, structures, and relationships in the data without any explicit guidance. Unsupervised learning has several important applications, including dimensionality reduction, clustering, anomaly detection, and generative modeling. By learning from unlabeled data, unsupervised learning can help to uncover hidden structures in the data, reduce the dimensionality of the data while preserving important information, and generate new data samples that are similar to the training data. One of the most common unsupervised learning techniques is clustering, which aims to group similar data points together based on some measure of similarity or distance. K-means clustering and hierarchical clustering are examples of widely used clustering algorithms. These algorithms can be used to discover natural groupings in the data, such as customer segments in marketing data or topics in a collection of text documents. Dimensionality reduction is another important application of unsupervised learning. Techniques such as principal component analysis, PCA, and T-distributed stochastic neighbor embedding, TSNE, can be used to project high-dimensional data onto a lower-dimensional space while preserving the most important information or structure in the data. This can be useful for visualization, noise reduction, and as a pre-processing step for other machine learning tasks. Autoencoders, which we covered in Lesson 5, are a type of neural network that can be used for unsupervised learning. By training an autoencoder to reconstruct its input, the model learns a compressed representation of the data in the latent space. This representation can capture important features and patterns in the data and can be used for dimensionality reduction, feature extraction, or anomaly detection. Generative models, such as variational autoencoders, VAEs, and generative adversarial networks, GANs, are another important class of unsupervised learning models. These models learn to generate new data samples that are similar to the training data. They have been successfully applied to tasks such as image generation, text generation, and data augmentation. Self-supervised learning is a more recent paradigm that bridges the gap between supervised and unsupervised learning. In self-supervised learning, a model is trained on an auxiliary task that can be created from unlabeled data itself. For example, a model can be trained to predict missing parts of an image, e.g., image in painting, to colorize a grayscale image, or to predict the next word in a sentence. By learning to solve this auxiliary task, the model learns useful representations of the data that can then be transferred to downstream tasks using supervised learning. Self-supervised learning has gained significant attention in recent years, particularly in the fields of computer vision and natural language processing. It has been shown to be a powerful method for learning representations from large amounts of unlabeled data, reducing the reliance on expensive labeled data. Unsupervised and self-supervised learning are active areas of research in deep learning. They offer the potential to learn from vast amounts of unlabeled data that are readily available in many domains, and to discover new structures and patterns in data that might not be apparent to human experts. Clustering, K-means, hierarchical clustering, and DBSCN clustering is a fundamental unsupervised learning technique that aims to partition a dataset into groups, or clusters, such that data points within the same cluster are more similar to each other than to data points in other clusters. Clustering has numerous applications, including customer segmentation, image segmentation, anomaly detection, and exploratory data analysis. K-means clustering is one of the most widely used clustering algorithms. It aims to partition the data into K clusters, where K is a user-specified parameter. The algorithm works by iteratively assigning data points to the nearest cluster centroid and updating the centroids as the mean of the data points assigned to each cluster. The K-means algorithm can be summarized as follows: initialize K cluster centroids randomly. Assign each data point to the nearest centroid. Update each centroid as the mean of the data points assigned to it. Repeat steps 2 and 3 until convergence, i.e., until the assignments no longer change or a maximum number of iterations is reached. K-means is relatively simple to implement and computationally efficient, making it suitable for large datasets. However, it has some limitations. It assumes that clusters are spherical and equally sized, which may not be true for all datasets. It is also sensitive to the initial choice of centroids and can converge to suboptimal solutions. To mitigate the sensitivity to initialization, the algorithm is often run multiple times with different random initializations, and the best solution, i.e., the one with the lowest within-cluster sum of squares, is selected. Hierarchical clustering is another popular clustering technique that builds a hierarchy of clusters. Unlike K-means, hierarchical clustering does not require the number of clusters to be specified in advance. There are two main types of hierarchical clustering, agglomerative and divisive. Agglomerative clustering, also known as bottom-up clustering, starts with each data point as a separate cluster and iteratively merges the most similar clusters until all data points belong to a single cluster. Divisive clustering, also known as top-down clustering, starts with all data points in a single cluster and iteratively splits clusters until each data point is in its own cluster. The result of hierarchical clustering is typically represented as a dendrogram, which is a tree-like diagram that shows the hierarchy of clusters and the distances at which clusters are merged or split. The dendrogram can be cut at different levels to obtain different numbers of clusters. Density-based spatial clustering of applications with noise, DISCAN, is a density-based clustering algorithm that can discover clusters of arbitrary shapes and sizes. Unlike K-means, DISCAN does not assume that clusters are spherical or equally sized. It also does not require the number of clusters to be specified in advance. DISCAN works by defining a neighborhood around each data point based on two parameters, epsilon, which specifies the radius of the neighborhood, and min-PTS, which specifies the minimum number of points required to form a dense cluster. A data point is considered a core point if its epsilon neighborhood contains at least min-PTS points. A data point is considered a border point if it is in the epsilon neighborhood of a core point but is not a core point itself. Data points that are neither core points nor border points are considered noise points. DISCAN starts by selecting an arbitrary data point and checking if it is a core point. If it is, a new cluster is formed, and all points in its epsilon neighborhood are added to the cluster. The algorithm then recursively expands the cluster by checking the epsilon neighborhoods of all core points in the cluster. If a border point is encountered, it is added to the cluster but its neighborhood is not explored further. DISCAN has several advantages over K-means and hierarchical clustering. It can discover clusters of arbitrary shapes and sizes, it is robust to noise and outliers, and it does not require the number of clusters to be specified in advance. However, it can be sensitive to the choice of epsilon and min-PTS parameters, and it may struggle with datasets that have clusters of varying densities. Other clustering algorithms include Gaussian mixture models, GMMs, which model the data as a mixture of Gaussian distributions, and spectral clustering, which uses the eigenvectors of a similarity matrix to perform dimensionality reduction before clustering in a lower dimensional space. The choice of clustering algorithm depends on the specific characteristics of the dataset and the goals of the analysis. It is often useful to try multiple algorithms and compare their results using appropriate evaluation metrics, such as the silhouette score or the Kolinsky-Harabas index. Dimensionality reduction, PCA, TSNE, and autoencoder's dimensionality reduction is a set of techniques used to reduce the number of variables or features in a dataset while preserving the most important information or structure in the data. Dimensionality reduction can be useful for various purposes, such as visualization of high-dimensional data, noise reduction, feature extraction, and improving the computational efficiency of machine learning algorithms. Principal component analysis, PCA, is a widely used linear dimensionality reduction technique that aims to find a lower dimensional representation of the data that captures the maximum variance. PCA works by finding the principal components of the data, which are orthogonal linear combinations of the original features that explain the most variance in the data. The first principal component is the linear combination that explains the largest amount of variance, the second principal component is the linear combination that explains the second largest amount of variance and is orthogonal to the first principal component, and so on. To perform PCA, the covariance matrix of the data is computed, and its eigenvectors and eigenvalues are found. The eigenvectors corresponding to the largest eigenvalues are the principal components. The data can then be projected onto the lower dimensional space spanned by the top k principal components, where k is the desired dimensionality of the reduced data. PCA is often used for visualization of high-dimensional data, by projecting the data onto the first two or three principal components. It can also be used for noise reduction, by discarding the principal components corresponding to small eigenvalues, which often represent noise or less important variations in the data. PCA is relatively simple to implement and computationally efficient, but it has some limitations. It assumes that the data is linearly related and that the principal components are orthogonal, which may not be true for all datasets. It is also sensitive to the scale of the features, so it is often necessary to standardize the data before applying PCA. T-distributed stochastic neighbor embedding, TSNE, is a nonlinear dimensionality reduction technique that is particularly well suited for visualizing high-dimensional data in 2 or 3 dimensions. Unlike PCA, TSNE does not assume that the data is linearly related or that the most important variations are along orthogonal directions. Instead, it aims to preserve the local neighborhood structure of the data, such that points that are close to each other in the high-dimensional space are also close to each other in the low-dimensional space. TSNE works by first computing pairwise similarities between data points in the high-dimensional space, typically using a Gaussian kernel. It then defines a similar probability distribution over the points in the low-dimensional space, using a student's t-distribution with 1 degree of freedom, also known as the Cauchy distribution. The low-dimensional embeddings are then optimized to minimize the Kullback-Leibler (KL) divergence between the two probability distributions. This encourages points that are similar in the high-dimensional space to be close together in the low-dimensional space, while dissimilar points are pushed apart. TSNE has become a popular technique for visualizing high-dimensional data, particularly in the context of deep learning. It can reveal complex structures and clusters in the data that may not be apparent using linear techniques like PCA. However, TSNE also has some limitations. It is a nonparametric technique, meaning that it does not learn an explicit mapping from the high-dimensional space to the low-dimensional space. This makes it difficult to embed new data points once the initial embedding has been computed. The global structure of the data is also not preserved in TSNE, so the distances between clusters in the low-dimensional space may not be meaningful. Autoencoders, which we covered in Lesson 5, can also be used for nonlinear dimensionality reduction. An autoencoder is trained to reconstruct its input, and the bottleneck layer, i.e., the latent space, provides a lower dimensional representation of the data. Unlike PCA, autoencoders can learn nonlinear mappings between the input space and the latent space, allowing them to capture more complex structures in the data. The dimensionality of the latent space in an autoencoder is a hyperparameter that can be tuned based on the desired level of compression and the complexity of the data. A smaller latent space will result in a more compressed representation but may lose more information. Autoencoders can also be used for feature extraction, where the learned latent representation is used as input to other machine learning models. Other dimensionality reduction techniques include linear discriminate analysis, LDA, which is a supervised technique that aims to find a linear combination of features that best separates different classes, and non-negative matrix factorization, NMF, which decomposes the data matrix into 2 non-negative matrices, providing a parts-based representation of the data. The choice of dimensionality reduction technique depends on the specific characteristics of the data and the goals of the analysis. It is often useful to try multiple techniques and compare their results using appropriate evaluation metrics. Self-supervised learning. Learning from unlabeled data. Self-supervised learning is a powerful paradigm in deep learning that aims to learn useful representations from unlabeled data by creating an auxiliary supervised learning task from the data itself. Unlike traditional supervised learning, which requires labeled data, or unsupervised learning, which does not use any labels, self-supervised learning leverages the structure and information present in the unlabeled data to define a supervisory signal. The key idea behind self-supervised learning is to formulate a pretext task, which is a supervised learning problem that can be created from unlabeled data. The model is then trained to solve this pretext task, and in doing so, it learns representations that capture important characteristics of the data. These learned representations can then be used for downstream tasks, such as classification or object detection, often with significantly less labeled data than would be required to train a model from scratch. One common pretext task in computer vision is to predict the relative position of image patches. Given two patches from an image, the model is trained to predict their relative spatial relationship, such as whether one patch is to the left, right, above, or below the other. This forces the model to learn visual features that capture spatial context and object structure. Another popular pretext task is image colorization. In this task, the model is given a grayscale image as input and is trained to predict the color channels. This requires the model to learn about object shapes, textures, and semantic information in order to produce plausible colorizations. Image and painting is another pretext task where the model is trained to fill in missing or corrupted parts of an image. This can be achieved by masking out a portion of the image and training the model to reconstruct the missing pixels based on the surrounding context. This forces the model to learn about image structure and coherence. Rotation prediction is another pretext task where the model is trained to predict the rotation angle applied to an image. The input image is rotated by a multiple of 90 degrees, e.g., 0, 90, 180, or 270 degrees, and the model has to predict the applied rotation. This task encourages the model to learn features that are invariant to rotation and to understand the global structure of objects. In natural language processing, one of the most successful pretext tasks is language modeling. Given a sequence of words, the model is trained to predict the next word in the sequence. This forces the model to learn about the statistical structure of language, including syntax, semantics, and long-range dependencies. Masked language modeling, as used in BERT, is a variant where some words in the input sequence are masked out, and the model is trained to predict the masked words based on the surrounding context. Another popular pretext task in NLP is next sentence prediction, where the model is trained to predict whether two given sentences are consecutive in the original text. This encourages the model to learn about discourse-level relationships between sentences. Self-supervised learning has several advantages over traditional supervised learning. It can leverage vast amounts of unlabeled data that are readily available in many domains. It can learn representations that are more general and transferable to different tasks, as they are not tied to a specific set of labels. It can also help to avoid overfitting to specific label biases that may be present in labeled datasets. The representations learned through self-supervised learning can be used in several ways. They can be used as fixed feature extractors, where the learned representations are used as input to a separate classifier or model for the downstream task. They can also be fine-tuned on the downstream task, where the self-supervised model is used as a starting point and is further trained on the labeled data for the target task. Self-supervised learning has achieved impressive results in recent years, particularly in computer vision and natural language processing. Models such as SimCLR, MoCo, and BYOL in computer vision, and BERT, GPT, and RoBERTa in NLP, have demonstrated that self-supervised learning can learn representations that are competitive with or even superior to those learned through supervised learning, particularly when labeled data is limited. Despite its success, self-supervised learning also faces some challenges. One challenge is the design of effective pretext tasks that can lead to useful and generalizable representations. Another challenge is understanding what exactly these models are learning and how their representations relate to human perception and cognition. Self-supervised learning is an active and rapidly evolving area of research in deep learning. It has the potential to significantly reduce the reliance on labeled data and to enable the development of more general and adaptable models that can learn from the vast amounts of unlabeled data available in the world. Contrastive learning. Learning by comparing. Contrastive learning is a powerful approach in self-supervised learning that has gained significant attention in recent years. The key idea behind contrastive learning is to learn representations by contrasting positive pairs of data samples against negative pairs. A positive pair consists of two data samples that are considered similar or related in some way, while a negative pair consists of two data samples that are considered dissimilar or unrelated. The goal of contrastive learning is to learn an embedding space where positive pairs are close to each other and negative pairs are far apart. This is typically achieved by training a neural network to minimize a contrastive loss function, which encourages the embeddings of positive pairs to be similar and the embeddings of negative pairs to be dissimilar. One of the most popular contrastive learning frameworks is SimCLR, a simple framework for contrastive learning of visual representations, introduced by Chen et al. In 2020. SimCLR learns representations by maximizing agreement between differently augmented views of the same image under a contrastive loss in the latent space. The SimCLR framework can be summarized as follows: for each image in a mini-batch, create two augmented views by applying random transformations such as cropping, flipping, color jittering, and Gaussian blurring. These two views form a positive pair. Encode each augmented view using a neural network encoder, e.g., ResNet, to obtain a representation vector. Project the representation vector to a lower-dimensional space using a small neural network projection head. Compute a contrastive loss that encourages the representations of positive pairs to be similar and the representations of negative pairs, i.e., views from different images, to be dissimilar. A commonly used contrastive loss is the InfoNCE loss, which is a normalized temperature-scaled cross-entropy loss. Update the parameters of the encoder and projection head to minimize the contrastive loss using stochastic gradient descent. After training, the projection head is discarded, and the encoder is used to extract representations for downstream tasks. SimCLR demonstrated that this simple framework can learn high-quality visual representations without using any labeled data. The learned representations achieve strong performance when fine-tuned on supervised tasks such as image classification, often outperforming models trained from scratch with labeled data, especially when the number of labels is limited. MoCo, momentum contrast, is another influential contrastive learning framework that addresses some of the limitations of SimCLR. One limitation of SimCLR is that it requires large batch sizes to provide a sufficient number of negative examples for the contrastive loss. MoCo, on the other hand, maintains a queue of negative examples from previous batches and uses a momentum encoder to provide consistent representations for these negatives. This allows MoCo to use a much larger set of negatives without increasing the batch size, leading to improved performance. BYOL, Bootstrap Your Own Latent, is a more recent contrastive learning framework that achieves state-of-the-art results without using negative pairs at all. Instead, BYOL trains two neural networks, an online network and a target network, and encourages the output of the online network for one view of an image to predict the output of the target network for a different view of the same image. The target network is updated as an exponential moving average of the online network's weights. This approach avoids the need for explicit negative examples and has been shown to be surprisingly effective. Contrastive learning has also been applied to other types of data beyond images. In natural language processing, contrastive learning has been used to learn sentence embeddings by contrasting different sentences from the same document as positive pairs and sentences from different documents as negative pairs. In graph representation learning, contrastive learning has been used to learn node and graph embeddings by contrasting different views of the same graph, such as different subgraphs or augmentations of the graph structure. One of the key advantages of contrastive learning is its simplicity and flexibility. It can be applied to various types of data and can be combined with different network architectures and augmentation strategies. It also provides a powerful framework for learning from unlabeled data, which is often abundant and readily available. However, contrastive learning also has some limitations. The performance of contrastive learning methods can be sensitive to the choice of data augmentations and the size of the negative sample set. It can also be computationally expensive, particularly when using large batch sizes or maintaining a large queue of negatives. Despite these limitations, contrastive learning has emerged as a leading approach in self-supervised learning and has significantly advanced the state-of-the-art in representation learning. It has also inspired new research directions, such as exploring different types of contrastive losses, combining contrastive learning with other self-supervised objectives, and understanding the theoretical underpinnings of contrastive learning. Applications in computer vision, image pre-training and object detection. Self-supervised learning, including contrastive learning, has had a significant impact on computer vision, enabling the learning of powerful visual representations from unlabeled images. These representations can be used for various downstream tasks, such as image classification, object detection, and semantic segmentation, often achieving performance comparable to or even surpassing that of models trained with full supervision. One of the most prominent applications of self-supervised learning in computer vision is image pre-training. Similar to how language models are pre-trained on large text corpora, self-supervised learning allows us to pre-train visual models on large unlabeled image datasets, such as ImageNet, without using any human annotations. The pre-trained models learn rich visual features that can be transferred to other computer vision tasks through fine-tuning or used as fixed feature extractors. Self-supervised pre-training typically involves defining a pretext task that can be solved using only unlabeled images. For example, a model can be trained to predict the relative positions of image patches, to colorize grayscale images, or to fill in masked regions of an image. More recently, contrastive learning methods, such as SimCLR and MoCo, have become the dominant approach for self-supervised pre-training in computer vision. These methods train a model to produce similar representations for different augmented views of the same image and dissimilar representations for views of different images. By learning to distinguish between positive and negative pairs, the model learns to capture essential visual features that are invariant to various transformations and augmentations. The pre-trained models can then be fine-tuned for specific downstream tasks by adding a task-specific output layer, e.g., a classification layer for image classification or a detection head for object detection, and training on labeled data for the target task. This often requires significantly less labeled data compared to training a model from scratch, as the pre-trained model already captures a rich set of visual features. Self-supervised pre-training has been shown to be particularly effective when labeled data is scarce or expensive to obtain, such as in medical imaging or satellite imagery. It can also help to improve the robustness and generalization of models, as they are trained on a more diverse set of images and are not solely reliant on the specific labels of the target task. Despite the success of self-supervised learning in computer vision, there are still many open research questions. One challenge is to design pretext tasks or contrastive learning objectives that are most effective for learning useful and generalizable visual representations. Another challenge is to understand the theoretical properties of self-supervised learning and how the learned representations relate to those learned through supervised learning. Furthermore, the development of self-supervised methods that can effectively leverage unlabeled video data is an important research direction. Videos contain rich temporal information that can be exploited for self-supervised learning, for example, by predicting future frames, enforcing temporal coherence, or learning from the audio track. Self-supervised learning has emerged as a powerful paradigm in computer vision, enabling the learning of visual representations from unlabeled data that are competitive with or even surpass those learned through full supervision. Applications in natural language processing. Pre-training language model. Self-supervised learning has revolutionized the field of natural language processing, NLP, by enabling the development of powerful pre-trained language models that can be fine-tuned for a wide range of downstream tasks. These models are trained on massive text corpora using self-supervised objectives, such as language modeling or masked language modeling, and learn rich representations of words, sentences, and documents that capture syntactic and semantic information. One of the most influential pre-trained language models is BERT, bidirectional encoder representations from transformers, introduced by Devlin et al. In 2018. BERT is a transformer-based model that is pre-trained using two self-supervised objectives, masked language modeling and next sentence prediction. In masked language modeling, a certain percentage of the input tokens, e.g., 15%, are randomly masked out, and the model is trained to predict the original masked tokens based on the surrounding context. This forces the model to learn bidirectional representations that consider both the left and right context of each word. In next sentence prediction, the model is given two sentences and trained to predict whether the second sentence is the actual next sentence in the original text or a randomly chosen sentence. This helps the model learn relationships between sentences. BERT is pre-trained on a massive text corpus, consisting of the book's corpus, 800 words, and English Wikipedia, 500 words. The pre-training process involves training a deep transformer encoder with multiple layers and attention heads, allowing the model to capture complex dependencies and relationships in the text. After pre-training, BERT can be fine-tuned for various downstream NLP tasks by adding a task-specific output layer on top of the pre-trained model. For example, for text classification, a classification layer can be added on top of the final hidden state corresponding to the special CLS token, which is used to represent the entire input sequence. For question answering, the model can be fine-tuned to predict the start and end positions of the answer span within a given passage. Fine-tuning BERT typically involves training the entire model, including both the pre-trained BERT parameters and the task-specific output layer, on the labeled data for the target task. This allows the model to adapt the pre-trained representations to the specific characteristics of the downstream task. BERT has achieved state-of-the-art results on a wide range of NLP benchmarks, including the GLUE benchmark, Squad question answering, and SWAG common sense reasoning. It has significantly advanced the state-of-the-art in tasks such as text classification, named entity recognition, sentiment analysis, and natural language inference. Since the introduction of BERT, several other pre-trained language models have been developed, building upon its success. Roberta, a robustly optimized BERT pre-training approach, is a variant of BERT that uses a modified pre-training procedure, including training on larger batches for more iterations, removing the next sentence prediction objective, and using dynamic masking instead of static masking. Roberta has been shown to outperform BERT on several benchmarks. Albert, a light BERT, is another variant that aims to reduce the memory consumption and increase the training speed of BERT. It uses two-parameter reduction techniques, factorized embedding parameterization, which separates the size of the hidden layers from the size of the vocabulary embedding, and cross-layer parameter sharing, which shares parameters across different layers. DistilBERT is a smaller, faster, and lighter version of BERT that is trained using knowledge distillation. It is trained to mimic the behavior of a larger BERT model, the teacher, while having fewer parameters and a simpler architecture. GPT, Generative Pre-trained Transformer, is another family of pre-trained language models that have achieved impressive results, particularly in text generation tasks. Unlike BERT, which uses a bidirectional transformer encoder, GPT uses a left-to-right transformer decoder and is pre-trained using a standard language modeling objective, where the model predicts the next word in a sequence given the previous words. GPT models, such as GPT-2 and GPT-3, have demonstrated remarkable capabilities in generating coherent and contextually relevant text. They have also shown strong performance on various NLP tasks in a zero-shot or few-shot setting, where the model is not explicitly fine-tuned on the target task but is instead given a prompt or a few examples at inference time. The development of pre-trained language models has had a profound impact on the field of NLP. These models have significantly improved the performance of various NLP systems, often requiring much less labeled data than training from scratch. They have also simplified the development process, as practitioners can start with a powerful pre-trained model and fine-tune it for their specific task, rather than having to design and train a new model from the ground up. Pre-trained language models have become a fundamental building block in many NLP applications and have enabled new capabilities, such as more natural and human-like conversational agents, improved machine translation, and more accurate information extraction systems. Challenges and future directions in unsupervised and self-supervised learning. Despite the significant progress in unsupervised and self-supervised learning, several challenges remain, and many exciting research directions are being explored. One of the main challenges in unsupervised learning is the evaluation of the learned representations. Unlike supervised learning, where there are clear metrics such as accuracy or F1 score, it is often unclear how to evaluate the quality of representations learned without any labels. One common approach is to use the learned representations as input features for downstream supervised tasks and measure the performance on these tasks. However, this approach may not fully capture the quality of the representations themselves and can be influenced by the specific downstream task and the amount of labeled data available. Developing better intrinsic evaluation metrics for unsupervised learning is an active area of research. Some approaches include measuring the disentanglement of the learned representations, their ability to reconstruct the input data, or their usefulness for clustering or anomaly detection. Another challenge is the design of effective pretext tasks for self-supervised learning. The choice of pretext task can significantly impact the quality of the learned representations and their transferability to downstream tasks. While many pretext tasks have been proposed, it is still an open question what makes a good pretext task and how to design tasks that are most effective for learning useful and generalizable representations. Contrastive learning methods, which have become very popular in self-supervised learning, also face some challenges. The performance of these methods can be sensitive to the choice of data augmentations, the size of the negative sample set, and the temperature parameter in the contrastive loss. Understanding the theoretical underpinnings of contrastive learning and developing more robust and efficient training methods are important research directions. Another challenge is scaling up self-supervised learning to even larger datasets and models. While self-supervised learning has shown impressive results on large datasets like ImageNet, training on even larger and more diverse datasets, such as web-scale image and video collections, could potentially lead to even more powerful and general representations. Developing self-supervised methods that can effectively leverage such massive datasets is an open research problem. The development of self-supervised learning methods for modalities beyond images and text, such as audio, video, and 3D data, is another important research direction. Extending self-supervised learning to these modalities could enable new applications and improve the performance of models in domains where labeled data is scarce or expensive to obtain. For example, in robotics, self-supervised learning from video data could enable robots to learn about the physical world and develop useful skills without the need for extensive human supervision or hand-engineered reward functions. Another exciting direction is the combination of self-supervised learning with other paradigms, such as reinforcement learning and active learning. For example, self-supervised learning could be used to learn a representation of the environment in a reinforcement learning setting, which could then be used to learn a policy more efficiently. In active learning, self-supervised learning could be used to select the most informative unlabeled examples to be labeled by a human expert, reducing the overall labeling cost. The theoretical understanding of self-supervised learning is also an important research area. While self-supervised learning has shown impressive empirical results, a deeper theoretical understanding of why these methods work so well and how they relate to supervised learning and other unsupervised methods is still lacking. Developing a more solid theoretical foundation for self-supervised learning could lead to the design of more principled and effective algorithms. Finally, the societal impact of unsupervised and self-supervised learning should be carefully considered. As these methods enable the learning of powerful representations from unlabeled data, there are potential risks related to privacy, bias, and misuse. For example, models trained on unlabeled web data may inadvertently learn and perpetuate harmful stereotypes or biases present in the data. Developing methods for auditing and mitigating biases in self-supervised models, as well as understanding the potential societal implications of these technologies, is crucial for ensuring their responsible development and deployment. Unsupervised and self-supervised learning are rapidly evolving fields with the potential to transform many areas of machine learning and artificial intelligence. Lesson 15, Generative Adversarial Networks, GANs, for Image Synthesis. Introduction to Generative Adversarial Networks, GANs. Generative Adversarial Networks, GANs, are a class of deep generative models that have gained immense popularity since their introduction in 2014 by Goodfellow et al. GANs are based on the idea of training two neural networks, a generator and a discriminator, in an adversarial manner. The generator learns to create new data samples that are similar to the training data, while the discriminator learns to distinguish between real data samples and generated samples. Through this adversarial process, the generator learns to produce increasingly realistic data samples, while the discriminator becomes better at identifying fake samples. GANs have shown impressive results in generating high-quality images, and they have been applied to various other domains, such as text generation, audio synthesis, and video generation. The basic GAN framework consists of two neural networks, a generator G and a discriminator D. The generator takes a random noise vector Z as input, typically sampled from a simple distribution such as a uniform or normal distribution, and outputs a data sample G, Z. The discriminator takes a data sample X as input, which can be either a real sample from the training data or a generated sample from the generator, and outputs a scalar value D, X, representing the probability that the sample is real rather than generated. The generator and discriminator are trained jointly in a two-player minimax game. The discriminator's objective is to maximize the probability of correctly classifying real and generated samples, while the generator's objective is to minimize the probability that the discriminator correctly classifies its generated samples as fake. This can be expressed as the following minimax objective function: min is sub a g slash sub a max sub d slash sub a v d g equals e sub x p sub a data slash sub x slash sub log d x plus e sub z p sub z slash sub log 1 d g z, where p sub a data slash sub x is the distribution of real data, p sub z slash sub z is the distribution of the input noise vectors, e denotes the expected value, and log is the natural logarithm. During training, the discriminator and generator are updated alternately. In each iteration, the discriminator is trained for one or more steps to improve its ability to distinguish between real and generated samples, while the generator's parameters are held fixed. Then, the generator is trained for one or more steps to improve its ability to generate samples that can fool the discriminator, while the discriminator's parameters are held fixed. The training process can be challenging and unstable, as it involves finding a Nash equilibrium of a non-convex game. If the discriminator is too strong, the generator may not be able to learn effectively due to vanishing gradients. If the generator is too strong, it may produce samples that exploit weaknesses in the discriminator but do not correspond to realistic data. Despite these challenges, GANs have achieved remarkable success in generating high-quality images. Early GAN models, such as the Deep Convolutional GAN, DCGAN, demonstrated the ability to generate realistic images of faces, bedrooms, and other objects. Subsequent research has led to significant improvements in the quality, diversity, and resolution of generated images. GANs have also been applied to various image synthesis tasks beyond unconditional image generation. Conditional GANs, CGANs, allow for generating images that are conditioned on some additional information, such as class labels or text descriptions. This enables more control over the generated images and allows for generating images with specific attributes or characteristics. Image-to-image translation is another application where GANs have shown impressive results. Models like Pix2Pix and CycleGAN can learn to map images from one domain to another, such as translating sketches to realistic images, converting daytime images to nighttime images, or transforming horses into zebras. GANs have also been used for tasks such as image and painting, super resolution, and style transfer. Their ability to learn complex, nonlinear mappings from noise vectors to high-dimensional data samples has made them a powerful tool for various image synthesis and manipulation tasks. The development of GANs has been one of the most exciting and impactful advances in deep learning in recent years. They have not only enabled the creation of realistic and diverse synthetic images but have also deepened our understanding of generative modeling and unsupervised learning. GAN architecture, generator and discriminator networks. The architecture of a generative adversarial network, GAN, consists of two main components, a generator network and a discriminator network. These two networks are trained together in an adversarial manner, with the generator trying to produce realistic data samples and the discriminator trying to distinguish between real and generated samples. The generator network, denoted by G, takes a random noise vector Z as input and produces a data sample G, Z, as output. The noise vector Z is typically sampled from a simple distribution, such as a uniform or normal distribution, and serves as a source of randomness for the generator. The generator can be thought of as a mapping from the latent space, represented by the noise vectors, to the data space. The generator is usually implemented as a deep neural network, with the specific architecture depending on the type of data being generated. For image generation, the generator often uses a series of transposed convolutional layers, also known as deconvolutional layers, to upsample the noise vector and generate an image. The first layer of the generator is typically a fully connected layer that maps the noise vector to a small, high-dimensional representation. This representation is then reshaped into a 4D tensor, a feature map with spatial dimensions and multiple channels, and passed through a series of transposed convolutional layers, each of which increases the spatial dimensions and reduces the number of channels. Batch normalization and ReLU activation functions are commonly used between the transposed convolutional layers. The final layer typically uses a 10 activation function to produce pixel values in the range -1, 1. The discriminator network, denoted by D, takes a data sample X as input, which can be either a real sample from the training data or a generated sample from the generator, and outputs a scalar value D, X, representing the probability that the sample is real rather than generated. The discriminator is also implemented as a deep neural network, with an architecture that is often a mirror image of the generator. For image data, the discriminator typically uses a series of convolutional layers to process the input image and extract features. Each convolutional layer is followed by batch normalization and a leaky ReLU activation function. The final layers of the discriminator are typically fully connected layers that produce a single output value, which is passed through a sigmoid activation function to produce a probability between 0 and 1. During training, the discriminator and generator are updated alternately. The discriminator is trained to maximize the probability of correctly classifying real and generated samples. This can be achieved by minimizing the following loss function, L sub D sub equals E sub X P sub data sub X sub log D X E sub Z P sub Z sub Z sub log 1 D G Z, where P sub data sub X is the distribution of real data, P sub Z sub Z is the distribution of the input noise vectors, E denotes the expected value, and log is the natural logarithm. The generator is trained to minimize the probability that the discriminator correctly classifies its generated samples as fake. This can be achieved by minimizing the following loss function, L sub G sub equals E sub Z P sub Z sub Z sub log D G Z. In practice, the generator is often trained to maximize log D G Z instead of minimizing log 1 D G, Z, as this provides stronger gradients early in training when the discriminator is easily able to distinguish between real and generated samples. The training process involves finding a Nash equilibrium of the adversarial game between the generator and the discriminator. Ideally, the generator learns to produce samples that are indistinguishable from real data, and the discriminator becomes unable to distinguish between real and generated samples, outputting a probability of 0. 5 for all inputs. However, achieving this equilibrium in practice can be challenging, and GAN training is known to be unstable and sensitive to the choice of hyperparameters. Several techniques have been proposed to stabilize GAN training, such as using different loss functions, e.g., Wasserstein distance, modifying the network architectures, e.g., using residual connections, and using regularization techniques, e.g., spectral normalization. The specific architectures of the generator and discriminator can vary depending on the task and the type of data being generated. For example, in text generation, recurrent neural networks, RNNs, or transformers may be used instead of convolutional networks. In some cases, the generator and discriminator may share some layers or parameters, or they may be connected in more complex ways, such as in a cyclic or bidirectional manner. The design of GAN architectures is an active area of research, with new architectures and techniques being developed to improve the quality, diversity, and controllability of generated samples. Training GANs, objective functions, optimization, and challenges. Training generative adversarial networks, GANs, is a challenging task that involves finding a Nash equilibrium of a non-convex game between two neural networks, the generator and the discriminator. The training process is typically carried out using an alternating optimization procedure, where the discriminator is updated for one or more steps while holding the generator fixed, and then the generator is updated for one or more steps while holding the discriminator fixed. The objective function for the discriminator is to maximize the probability of correctly classifying real and generated samples. This can be expressed as max sub d slash sub v d g equals e sub x p sub data slash sub x slash sub log d x plus e sub z p sub z slash sub z slash sub log 1 d g z, where p sub data slash sub x is the distribution of real data, p sub z slash sub z is the distribution of the input noise vectors, e denotes the expected value, and log is the natural logarithm. In practice, the discriminator is trained to minimize the negative of this objective function, which is equivalent to minimizing the binary cross-entropy loss between the discriminator's predictions and the true labels, 1 for real samples and 0 for generated samples. The objective function for the generator is to minimize the probability that the discriminator correctly classifies its generated samples as fake. This can be expressed as min sub g slash sub v d g equals e sub z p sub z slash sub z slash sub log 1 d g z. However, in practice, the generator is often trained to maximize log d g z instead of minimizing log 1 d g z. This is because when the generator is performing poorly early in training, the discriminator can easily reject its generated samples, leading to small gradients for the generator. Maximizing log d g z provides stronger gradients in this situation and helps the generator to learn more effectively. The training process involves iteratively updating the discriminator and the generator using stochastic gradient descent, SGD, or a related optimization algorithm, such as ADAM. In each iteration, a mini-batch of real data samples is drawn from the training set, and a mini-batch of noise vectors is sampled from the prior distribution. The generator is used to produce a batch of generated samples from the noise vectors. The discriminator is then updated by computing the gradients of its loss function with respect to its parameters, using both the real and generated samples. The generator is updated by computing the gradients of its loss function with respect to its parameters, using the generated samples and the discriminator's current predictions. One of the main challenges in training GANs is maintaining a balance between the generator and the discriminator. If the discriminator is too strong, the generator may not be able to learn effectively due to vanishing gradients. If the generator is too strong, it may produce samples that exploit weaknesses in the discriminator but do not correspond to realistic data. This can lead to mode collapse, where the generator produces only a limited variety of samples, failing to capture the full diversity of the training data distribution. Another challenge is the instability of GAN training. The adversarial dynamics between the generator and discriminator can lead to oscillations, divergence, and other forms of instability. The training process can be highly sensitive to the choice of hyperparameters, such as the learning rates, the network architectures, and the batch size. Several techniques have been proposed to stabilize GAN training and improve the quality of generated samples. One common approach is to use different loss functions, such as the Wasserstein loss, which provides a more meaningful measure of the distance between the real and generated data distributions and can lead to more stable training. Another approach is to use regularization techniques, such as spectral normalization, which constrains the Lipschitz constant of the discriminator to prevent it from becoming too complex and to improve the stability of training. Modifying the network architectures can also help to improve GAN training. For example, using residual connections, as in ResNet, can improve gradient flow and enable the training of deeper and more powerful GANs. Other techniques, such as using larger batch sizes, employing one-sided label smoothing, and using virtual batch normalization, have also been shown to improve GAN training. Despite these advances, training GANs remains a challenging and active area of research. Developing more stable and efficient training algorithms, as well as better evaluation metrics for generated samples, are important open problems in the field. The choice of hyperparameters, such as the learning rates, the number of discriminator updates per generator update, and the specific architectures of the generator and discriminator, can have a significant impact on the training process and the quality of the generated samples. Careful tuning and experimentation are often required to achieve good results when training GANs. In recent years, there has been a growing interest in understanding the theoretical properties of GANs and their training dynamics. This research aims to provide a more principled understanding of GANs, to develop more stable and efficient training algorithms, and to guide the design of new GAN architectures and applications. Loss functions for GANs, adversarial loss, Wasserstein loss, and others. The choice of loss function is a crucial aspect of training generative adversarial networks, GANs, and has a significant impact on the stability of training and the quality of generated samples. The original GAN formulation used a minimax objective function based on the binary cross-entropy loss, but several alternative loss functions have been proposed to address the challenges of GAN training and improve performance. The adversarial loss in the original GAN formulation can be expressed as min is sub g slash sub max sub d slash sub v d g equals e sub x p sub a data slash sub x slash sub log d x plus e sub z p sub z slash sub z slash sub log 1 d g z, where d x is the discriminator's output for a real sample x, g z is the generator's output for a noise vector z, p sub a data e slash sub x is the distribution of real data, and p sub z slash sub a z is the distribution of the noise vectors. This loss function is derived from the Jensen-Shannon divergence between the real data distribution and the generated data distribution. However, it has been observed that this loss function can lead to unstable training and vanishing gradients, particularly when the discriminator is much stronger than the generator. One popular alternative to the original adversarial loss is the Wasserstein loss, which is used in Wasserstein GANs, WANs. The Wasserstein loss is based on the Wasserstein distance, also known as the Earth mover's distance, which measures the minimum cost of transporting mass from one distribution to another. In the context of GANs, the Wasserstein distance measures the distance between the distribution of real data and the distribution of generated data. The Wasserstein loss for the discriminator can be expressed as L e sub d e slash sub equals e sub x p sub a data e slash sub x slash sub d x e sub z p sub z slash sub d g z, and for the generator as L sub g slash sub equals e sub z p sub z slash sub d g z. To use the Wasserstein distance, the discriminator must be a 1 Lipschitz function, which means that the norm of its gradients must be at most 1 everywhere. This constraint is typically enforced by clipping the weights of the discriminator to a small range, e.g., -0, 0, 1, 0, 0, 1, after each gradient update, or by using a gradient penalty term that penalizes deviations from the one Lipschitz constraint. WANs have been shown to be more stable to train than the original GAN and less prone to mode collapse. They also provide a more meaningful loss metric that correlates with the quality of generated samples. Another popular loss function for GANs is the least squares loss, which is used in least squares GANs, scans. Scans replaced the binary cross-entropy loss in the original GAN with a least squares loss. The objective function for the discriminator in LSGAN is min e sub d sub v d equals 0. 5 e sub x p sub data sub x sub d x 1 sub 2 sub plus 0. 5 e sub z p sub z sub z sub d g z sub 2 sub, and for the generator, min sub g sub v g equals 0. 5 e sub z p sub z sub z sub d g z 1 sub 2 sub. Scans have been shown to generate higher quality images than the original GAN and to be more stable during training. Other loss functions that have been proposed for GANs include the hinge loss, which is commonly used in support vector machines, and the relativistic average loss, which compares the discriminator's output for real and generated samples in a pairwise manner. The choice of loss function can have a significant impact on the performance of GANs, and different loss functions may be more suitable for different tasks and datasets. In practice, it is often beneficial to experiment with different loss functions and to combine them with other techniques for stabilizing GAN training, such as spectral normalization and gradient penalties. In addition to the choice of loss function, the specific way in which the discriminator and generator are updated during training can also affect the performance of GANs. For example, using a separate learning rate for the discriminator and generator, or updating the discriminator multiple times for each generator update, can help to maintain a balance between the two networks and improve training stability. The development of new and improved loss functions for GANs is an active area of research. Researchers are exploring loss functions that can better capture the structure and diversity of the data distribution, that are more robust to mode collapse, and that provide more stable and efficient training. Advanced GAN architectures, DC-GAN, cycle-GAN, style-GAN, and more since the introduction of the original GAN framework, many advanced GAN architectures have been proposed to improve the quality, diversity, and controllability of generated samples. These architectures often involve modifications to the generator and discriminator networks, the training procedure, or both. They have led to significant advances in various applications of GANs, particularly in the field of image synthesis. Deep convolutional GANs, GANs, introduced by Radford et al. In 2015, were one of the first architectures to successfully apply convolutional neural networks, CNNs, to both the generator and discriminator for image generation. GANs demonstrated that GANs could generate high-quality images and provided a set of architectural guidelines for stable training of GANs. The DC-GAN generator uses a series of transposed convolutional layers to upsample a random noise vector to an image. Batch normalization is used after each transposed convolutional layer, except for the output layer, and ReLU activations are used for all layers except the output layer, which uses TAN. The DC-GAN discriminator is a standard CNN that uses strided convolutions instead of pooling layers to downsample the input image. Leaky ReLU activations are used in the discriminator, and batch normalization is applied to all convolutional layers except the input layer. GANs also introduced the use of the atom optimizer with specific hyperparameters for training GANs, which has become a common practice. Cycle-GAN, introduced by Zhu et al. In 2017, is an architecture for unpaired image-to-image translation. Unlike previous methods that required paired training data, i.e., images from one domain explicitly matched with corresponding images in another domain, cycle-GAN can learn a mapping between two image domains without paired examples. This is achieved by using a cycle consistency loss that encourages the mapping to be invertible. The cycle GN architecture consists of two generators and two discriminators. One generator, G sub xy/sub, learns to map images from domain X to domain Y, while the other generator, G sub yx/sub, learns to map images from domain Y to domain X. The discriminators, D sub x/sub and D sub y/sub, are trained to distinguish between real and generated images in each domain. In addition to the standard adversarial loss, cycle GN uses a cycle consistency loss that enforces the constraint that an image translated from domain X to domain Y and then back to domain X should be similar to the original image, i.e., G sub yx/sub, G sub xy/sub, X, is almost equal to X, and vice versa. This encourages the mappings to be consistent and helps to prevent mode collapse. Cycle GN has been used for various image-to-image translation tasks, such as converting horses to zebras, transforming summer landscapes to winter landscapes, and translating paintings to photographs. Style GN, introduced by Karas et al. In 2018, is a state-of-the-art architecture for high-resolution image generation that focuses on controlling the style of generated images. Style GN introduces several modifications to the traditional GN generator architecture, including a mapping network that transforms the input noise vector into an intermediate latent code, and an adaptive instance normalization (ADA-IN) operation that incorporates style information into the feature maps at each convolutional layer. The mapping network in Style GN is a multi-layer perceptron that maps the input noise vector Z to an intermediate latent code W. This intermediate code is then used to generate style parameters that modulate the feature maps in the generator via ADA-IN. The ADA-IN operation normalizes the feature maps in each channel to have zero mean and unit variance, and then scales and shifts them using the style parameters derived from W. By using different parts of the intermediate latent code W to control the style at different layers of the generator, Style GN can disentangle different factors of variation in the generated images. For example, coarse-level styles, e.g., pose, face shape, can be controlled by the style parameters applied to the early layers of the generator, while fine-level details, e.g., hair color, texture, can be controlled by the style parameters applied to the later layers. Style GN also introduces a technique called mixing regularization, where two different noise vectors Z sub 1/sub and Z sub 2/sub are used to generate different parts of the image during training. This encourages the model to learn a more disentangled representation of style and improves the controllability of the generated images. Style GN has achieved impressive results in generating high-resolution, realistic images, particularly of human faces. It has also been used for various image editing and manipulation tasks, such as style mixing, interpolation, and attribute editing. Progressive growing of GANs, GANs, is another technique for high-resolution image generation that was introduced by Karas et al. In 2017. GANs involve training the generator and discriminator incrementally, starting with low-resolution images, e.g., 4x4, and progressively increasing the resolution during training by adding new layers to the generator and discriminator. This progressive growing approach helps to stabilize the training of GANs for high-resolution image generation and allows the model to first learn the large-scale structure of the images and then gradually learn finer details. GANs have been used to generate high-quality images at resolutions up to 1024 by 1024 pixels, demonstrating the effectiveness of this approach. These are just a few examples of the many advanced GAN architectures that have been proposed in recent years. Other notable architectures include Big GAN, which uses large-scale GAN training with improved regularization techniques to generate high-resolution images, and Self-Attention GAN, SAGAN, which incorporates self-attention mechanisms into the generator and discriminator to capture long-range dependencies in the image. The development of advanced GAN architectures is an active and rapidly evolving area of research. These architectures have significantly improved the quality, diversity, and controllability of generated images and have expanded the range of applications for GANs in image synthesis and beyond. Applications of GANs in image synthesis, image generation, translation, and manipulation. Generative adversarial networks, GANs, have demonstrated remarkable capabilities in various image synthesis tasks, enabling the generation of realistic and diverse images, the translation of images from one domain to another, and the manipulation of image attributes and styles. These applications have significant implications for fields such as computer graphics, art, design, and entertainment. One of the most prominent applications of GANs is unconditional image generation, where the goal is to generate new images that are similar to the training data but not exact copies. Advanced GAN architectures, such as DCGAN, StyleGAN, and BigGAN, have achieved impressive results in generating high-resolution, realistic images of various categories, including faces, animals, landscapes, and objects. These models have learned to capture the complex statistical properties of natural images and can generate novel samples that are often indistinguishable from real images to the human eye. Conditional image generation is another important application, where the goal is to generate images that satisfy certain conditions or constraints. Conditional GANs, CGANs, can be used to generate images based on class labels, text descriptions, or other types of conditioning information. For example, a CGAN can be trained to generate images of specific digits in the NIST dataset, conditioned on the digit label. Or it can be trained to generate images of faces with specific attributes, such as age, gender, or hair color, conditioned on these attributes. Image-to-image translation is a particularly exciting application of GANs, where the goal is to learn a mapping between two image domains. This can involve translating images from one style or modality to another, such as converting sketches to realistic images, translating daytime images to nighttime images, or mapping semantic segmentation maps to photorealistic images. CycleGAN is a popular architecture for unpaired image-to-image translation, where the training data does not consist of paired examples from the two domains. CycleGAN learns two mappings, one from domain X to domain Y and another from domain Y to domain X, and uses a cycle consistency loss to ensure that the mappings are consistent with each other. This allows CycleGAN to learn mappings between domains even when paired data is not available. Pix2Pix is another widely used model for image-to-image translation, which uses a conditional GAN to learn a mapping from an input image to an output image, conditioned on the input image. Unlike CycleGAN, Pix2Pix requires paired training data, where each input image is associated with a corresponding target output image. GANs have also been used for various image manipulation tasks, such as superresolution, in painting, and style transfer. In superresolution, GANs can be used to generate high-resolution images from low-resolution inputs, hallucinating fine details that are not present in the input. In painting, GANs can be used to fill in missing or corrupted parts of an image, generating plausible content that is consistent with the surrounding context. Style transfer is another application where GANs have shown impressive results. By combining the content of one image with the style of another image, GANs can create novel artistic images. This can be achieved by using a pre-trained CNN, such as VGG, to extract content and style representations from the respective images, and then optimizing an image to match the content representation of the content image and the style representation of the style image. GANs have also been used for interactive image editing and manipulation. For example, IGN allows users to interactively edit images by manipulating a latent vector that controls the attributes of the generated image. GAUGN, developed by NVIDIA, allows users to create photorealistic images from simple semantic segmentation maps, providing a powerful tool for artists and designers. The applications of GANs in image synthesis are vast and rapidly expanding. They have the potential to revolutionize various creative fields, enabling new forms of artistic expression, automating tedious and time-consuming tasks, and providing powerful tools for image editing and manipulation. Evaluating GANs, metrics and challenges in assessing generated image quality. Evaluating the quality and diversity of images generated by generative adversarial networks, GANs, is a challenging task. Unlike supervised learning, where there are clear metrics such as accuracy or mean squared error, there is no single, universally accepted metric for evaluating the performance of GANs. Moreover, the notion of image quality itself can be subjective and multifaceted, involving factors such as realism, diversity, novelty, and fidelity to the training data distribution. One of the most widely used metrics for evaluating GANs is the inception score, IS, which was introduced by Salomons et al. In 2016. The inception score uses a pre-trained inception network to classify generated images and measures both the quality and diversity of the samples. It is based on the idea that a good generative model should produce images that are diverse, i.e., cover a wide range of classes, and that each image should be confidently classified as belonging to a specific class, i.e., have low entropy in its predicted class probabilities. The inception score is computed as IS, G, equals exp, e sub x p sub g sub d sub kl sub p y x p y, where x is a generated image, p sub g sub is the distribution of generated images, p y x is the conditional class distribution predicted by the inception network for image x, p y is the marginal class distribution, i.e., the average of p yx over many generated images, and d sub kl sub is the Kullback-Leibler divergence. A higher inception score indicates better performance, with the score increasing as the generated images become more diverse and classifiable. However, the inception score has some limitations. It relies on the assumption that the classes in the inception model are relevant to the generated images, which may not always be the case. It also does not directly measure the similarity between the generated images and the real images, and it can be fooled by models that generate highly classifiable but unrealistic images. The Fréchet inception distance, FID, introduced by Husel et al. In 2017, is another widely used metric that addresses some of the limitations of the inception score. FID compares the distribution of generated images to the distribution of real images in the feature space of a pre-trained inception network. It models the feature representations of both real and generated images as continuous multivariate Gaussians and computes the Fréchet distance, also known as the Wasserstein-2 distance, between these Gaussians. The FID is computed as FID x g equals mu e sub x slash sub mu e sub g slash sub 2 e slash sub plus tr sigma sub x slash sub plus sigma sub g slash sub 2 sigma sub x slash sub sigma sub g slash sub 1 slash 2 slash sub, where x and g are the real and generated images, respectively. Mu e sub x slash sub and mu sub g slash sub are the mean feature vectors, sigma e sub x slash sub and sigma sub g slash sub are the covariance matrices of the feature vectors, and tr denotes the trace operator. A lower FID score indicates better performance, with the score decreasing as the generated images become more similar to the real images in terms of their feature statistics. FID has been shown to correlate well with human judgments of visual quality and is less sensitive to mode collapse than the inception score. However, it also has some limitations. It assumes that the feature representations follow a Gaussian distribution, which may not be accurate, and it is sensitive to the choice of the pre-trained network used to extract features. Other metrics that have been proposed for evaluating GANs include the kernel inception distance, KID, which is a variant of FID that uses a polynomial kernel instead of the Fréchet distance, and the precision and recall metrics adapted from information retrieval, which measure the fraction of generated images that are similar to real images, precision, and the fraction of real images that are captured by the generated images, recall. Perceptual similarity metrics, such as the Learned Perceptual Image Patch Similarity, LPIPS, metric, use deep neural networks to measure the perceptual similarity between images, based on the idea that images that are perceptually similar to humans should have similar feature representations in a well-trained neural network. Evaluating GANs is an active area of research, and new metrics and evaluation protocols are constantly being developed. It is generally recommended to use multiple metrics to evaluate different aspects of the generated images, such as quality, diversity, and fidelity to the training data. Visual inspection of generated samples is also an important part of the evaluation process, as it can reveal artifacts and failure modes that may not be captured by quantitative metrics. In addition to evaluating the quality of generated images, it is also important to consider other factors when assessing GANs, such as training stability, computational cost, and sample efficiency. Different GAN architectures and training methods may have different trade-offs between these factors, and the choice of the best model often depends on the specific application and constraints. Lesson 16, Advanced Deep Reinforcement Learning Introduction to Advanced Deep Reinforcement Learning. Deep reinforcement learning, DeepRL, has emerged as a powerful approach for solving complex decision-making and control problems by combining the strengths of deep neural networks and reinforcement learning. While basic DeepRL algorithms, such as DeepQ networks, DQN, and policy gradient methods, have demonstrated impressive results in various domains, advanced DeepRL algorithms aim to address their limitations and improve their performance, stability, and efficiency. These advanced algorithms often incorporate techniques such as improved exploration strategies, more stable and efficient learning updates, and the use of more sophisticated neural network architectures. One important area of research in advanced DeepRL is the development of algorithms that can learn more effectively in environments with sparse rewards. In many real-world problems, the agent receives non-zero rewards only infrequently, making it difficult to learn which actions are responsible for the rewards. This can lead to very slow learning, especially when using basic RL algorithms. Advanced DeepRL algorithms often incorporate techniques such as curiosity-driven exploration, intrinsic motivation, and hierarchical reinforcement learning to address the sparse reward problem. Another important area is the improvement of the stability and sample efficiency of DeepRL algorithms. DeepRL algorithms can be sensitive to the choice of hyperparameters and can suffer from instability during training due to the use of function approximation and the non-stationarity of the learning problem. Advanced algorithms often use techniques such as target networks, experience replay, and trust region updates to stabilize learning and improve sample efficiency. The development of more sophisticated neural network architectures has also played a crucial role in advancing DeepRL. For example, the use of recurrent neural networks, RNNs, in DeepRL agents can enable them to learn from sequences of observations and maintain an internal state that captures information about past interactions with the environment. This can be particularly important in partially observable environments, where the current observation does not provide complete information about the state of the environment. Another trend in advanced DeepRL is the development of algorithms that can learn multiple tasks simultaneously or transfer knowledge between tasks. Multitask and transfer learning can significantly improve the efficiency of learning and enable the development of more general and adaptable agents. Meta-learning, or learning to learn, has also been applied to DeepRL to enable agents to quickly adapt to new, unseen tasks with only a few examples or trials. Advanced DeepRL algorithms have achieved impressive results in various challenging domains, including robotics, game playing, and control systems. For example, algorithms such as Trust Region Policy Optimization, TRPO, Proximal Policy Optimization, PPO, and Soft Actor Critic, SAC, have demonstrated state-of-the-art performance on continuous control tasks, such as those in the MuJoCo physics simulator. DeepRL agents have also achieved superhuman performance in complex strategy games like Go, Dota 2, and StarCraft 2, outperforming the best human players in the world. Despite the progress in advanced DeepRL, many challenges remain. These include improving the sample efficiency of DeepRL algorithms, developing more effective exploration strategies, addressing the instability and hyperparameter sensitivity of training, and improving the generalization and robustness of DeepRL agents. The development of advanced DeepRL algorithms is an active and rapidly evolving area of research, with new algorithms and techniques constantly being proposed. These algorithms are pushing the boundaries of what's possible with DeepRL and enabling the development of more powerful and versatile agents that can solve increasingly complex real-world problems. Distributional RL, learning value distributions. Traditional reinforcement learning algorithms, such as Q-learning and SERSA, typically estimate the expected return, i.e., the mean of the return distribution, for each state action pair. However, the full distribution over returns can provide more information than just the mean. Distributional reinforcement learning is an approach that aims to learn the entire distribution over returns, rather than just the expected value. The key idea behind distributional RL is to represent the value function as a distribution over possible returns, rather than a single scalar value. This distribution, often referred to as the value distribution, captures the inherent randomness or uncertainty in the returns due to the stochasticity of the environment, the agent's policy, or both. One of the first distributional RL algorithms was the categorical DQN, also known as C51, introduced by Belmar et al. In 2017. C51 represents the value distribution as a discrete distribution over a fixed set of atoms, where each atom represents a possible return value. The network outputs a probability mass function over these atoms for each action, effectively learning a categorical distribution over returns. The training of C51 involves minimizing the distance between the predicted distribution and a target distribution, which is obtained by applying the Bellman operator to the current distribution. The distance between distributions is typically measured using the Kullback-Leibler, KL, divergence or a similar metric. Another popular distributional RL algorithm is the quantile regression DQN, QRDQN, introduced by Dabney et al. In 2018. QRDQN represents the value distribution using a set of quantiles, which are specific points in the cumulative distribution function, CDF, of the return distribution. For example, the 0. 1 quantile represents the return value below which 10% of the returns fall, the 0. 5 quantile represents the median return, and the 0. 9 quantile represents the return value below which 90% of the returns fall. QRDQN learns to predict the locations of these quantiles for each action, effectively approximating the entire CDF of the return distribution. The network is trained using quantile regression, which minimizes the quantile loss, also known as the pinball loss, between the predicted quantiles and the observed returns. Distributional RL has several potential advantages over traditional value-based methods. By learning the full distribution over returns, distributional RL agents can capture more nuanced information about the uncertainty and risk associated with different actions. This can lead to improved decision-making, particularly in stochastic environments or when the agent needs to balance exploration and exploitation. Distributional RL can also improve the stability and performance of reinforcement learning algorithms. The additional information provided by the value distribution can help to smooth the learning process and reduce the impact of noise or outliers in the observed returns. Moreover, distributional RL provides a natural framework for risk-sensitive decision-making. By examining different quantiles of the value distribution, the agent can make decisions that take into account not only the expected return but also the potential for extreme outcomes. For example, a risk-averse agent might choose an action that has a lower expected return but a higher probability of achieving a minimum acceptable return, while a risk-seeking agent might choose an action with a higher expected return but also a higher probability of a very low return. Distributional RL has been shown to improve the performance of deep RL agents on various tasks, including Atari games and continuous control problems. It has also been combined with other advanced techniques, such as prioritized experience replay and distributional deterministic policy gradients, D4PG, to further enhance performance. Despite its advantages, distributional RL also has some limitations. Learning a full distribution over returns is generally more computationally expensive than learning a single value estimate. The choice of how to represent the distribution, e.g., using a fixed set of atoms or quantiles, can also impact performance and may require careful tuning. Furthermore, interpreting and visualizing value distributions can be more challenging than interpreting scalar value estimates. Developing more efficient and scalable distributional RL algorithms, as well as better methods for interpreting and utilizing value distributions, are active areas of research. Distributional RL represents a significant departure from traditional value-based methods and offers a more nuanced and informative approach to reinforcement learning. By learning the full distribution over returns, distributional RL agents can make more informed decisions, better handle uncertainty, and potentially achieve improved performance in complex environments. Noisy nets. Parameter space noise for exploration. Exploration is a crucial aspect of reinforcement learning, as agents need to try out different actions and visit different states to discover optimal policies. One common approach to exploration is to add noise to the agent's actions, such as an epsilon-greedy or Boltzmann exploration. However, these methods operate in action space and can be inefficient in tasks that require temporally extended or structured exploration. Noisy nets, introduced by Fortunato et al. In 2017, are a deep RL technique that uses parametric noise to drive exploration. Instead of adding noise directly to the actions, noisy nets add noise to the parameters, i.e., the weights, of the neural network that represents the agent's policy or value function. This induces a stochastic policy that can lead to more consistent and effective exploration behavior. The key idea behind noisy nets is to replace the deterministic linear layers in a standard neural network with noisy linear layers. A noisy linear layer is defined as y equals mu sup w slash sup plus sigma sup w slash sup epsilon sup w slash sup x plus mu sup b slash sup plus sigma sup b slash sup epsilon sup b slash sup, where mu is sup w slash sup and sigma sup w slash sup are learnable parameter matrices for the weight mean and standard deviation. Mu sup b slash sup and sigma sup b slash sup are learnable parameter vectors for the bias mean and standard deviation. Epsilon sup w slash sup and epsilon sup b slash sup are random noise variables. X is the input to the layer, y is the output, and denotes element-wise multiplication. The noise variables epsilon sup w slash sup and epsilon sup b slash sup can follow different distributions, such as independent Gaussian noise for each weight and bias, or factorized Gaussian noise, which uses a smaller number of independent noise variables to generate correlated noise for the weights and biases. The latter approach, known as noisinet factorized, has been shown to be more effective in practice. During training, the noise variables epsilon sup w slash sup and epsilon sup b slash sup are sampled at the beginning of each episode or trajectory and kept fixed throughout the episode. The agent's policy is thus stochastic due to the noisy weights, but the noise is consistent within an episode, allowing the agent to learn temporally extended exploration strategies. The parameters mu sup w slash sup, sigma sup w slash sup, mu sup b slash sup, and sigma sup b slash sup are learned jointly with the rest of the network parameters using standard reinforcement learning algorithms, such as DQN or A3C. Noisy nets have several advantages over action space noise exploration methods. First, the exploration is learned and can be adapted to the specific task and state. The network can learn to adjust the level of noise in different parts of the state space, allowing for more efficient exploration. Second, the noise is consistent within an episode, which can lead to more structured and temporally extended exploration. This can be particularly important in tasks that require a specific sequence of actions to achieve a goal or where exploration needs to be coordinated over multiple time steps. Third, noisy nets can be more computationally efficient than action space noise methods, as they do not require additional sampling or computation at each time step during an episode. Noisy nets have been shown to improve the performance of deep RL agents on various tasks, including Atari games and continuous control problems. They have been particularly effective in hard exploration tasks, where the agent needs to perform a specific sequence of actions to receive any reward, such as in the game Montezuma's Revenge. Noisy nets can be combined with other deep RL algorithms and techniques, such as prioritized experience replay, distributional RL, and recurrent networks. They have also been used in combination with other exploration methods, such as intrinsic motivation and curiosity-driven exploration. Despite their advantages, noisy nets also have some limitations. The additional parameters introduced by the noisy layers increase the memory requirements of the model. The performance of noisy nets can also be sensitive to the choice of noise distribution and the scale of the noise. Moreover, while noisy nets can improve exploration, they do not explicitly address the exploration-exploitation trade-off. The agent may still get stuck in suboptimal policies if the noise is not properly balanced with exploitation of the learned value function or policy. Developing more advanced and adaptive exploration strategies that combine the strengths of parameter space noise and other exploration methods is an active area of research in deep RL. Noisy nets represent an important step towards more efficient and effective exploration in deep reinforcement learning and have inspired further research into the role of noise and stochasticity in learning and decision-making. Rainbow, combining improvements to deep Q networks, DQNs, have been one of the most influential algorithms in deep reinforcement learning, demonstrating that deep neural networks can be used to approximate the optimal action value function in complex, high-dimensional environments. However, the original DQN algorithm has several limitations and can be unstable or sample inefficient in certain settings. Over the years, many improvements and extensions to DQN have been proposed to address these limitations. Rainbow, introduced by Hessel et al. In 2017, is an algorithm that combines several of these improvements into a single integrated agent. By combining multiple algorithmic components, Rainbow achieves state-of-the-art performance on the Atari 2600 benchmark, significantly outperforming the original DQN and demonstrating the benefits of combining different enhancements to deep Q learning. The Rainbow agent incorporates the following 6 improvements to the original DQN algorithm: double DQN, addresses the overestimation bias in Q learning by decoupling the selection of the action from the evaluation of its value in the target. In double DQN, the main network is used to select the best action, but the target network is used to evaluate the value of that action. Prioritized experience replay. Instead of uniformly sampling transitions from the replay buffer, prioritized experience replay biases the sampling towards transitions with higher temporal difference, TD, error. This allows the agent to learn more from surprising or informative experiences. Dueling networks, uses a network architecture that separately estimates the state value function versus and the advantage function A, S, A. The Q values are then computed as Q, S, A, equals versus plus A, S, A. This can improve performance by allowing the agent to learn which states are valuable without having to learn the effect of each action in each state. Multi-step learning, instead of using single-step returns in the TD update, multi-step learning uses n-step returns, which are computed by summing the rewards over n steps and adding the discounted value of the state n steps ahead. This can help to propagate rewards faster and reduce the bias of the value estimates. Distributional RL, instead of estimating the expected return for each action, distributional RL, specifically, the C51 algorithm, learns a distribution over possible returns. This can capture more nuanced information about the uncertainty and risk associated with different actions and can lead to improved performance. Noisy nets, uses noisy linear layers instead of epsilon-greedy exploration to drive exploration. Noisy nets add parametric noise to the weights of the network, inducing a stochastic policy that can lead to more efficient and consistent exploration. The Rainbow agent combines all these components into a single algorithm. The agent uses a dueling network architecture with noisy layers to estimate a categorical distribution over returns for each action. It stores transitions in a prioritized experience replay buffer and samples mini-batches of transitions to update the network. The target values for the updates are computed using multi-step returns and the double Q-learning target. The Rainbow algorithm achieved state-of-the-art performance on the Atari 2600 benchmark, outperforming each of its individual components and demonstrating the effectiveness of combining multiple improvements to deep Q-learning. It showed that these improvements are largely complementary and that their combination leads to significant performance gains. Despite its success, the Rainbow algorithm also has some limitations. It is computationally more expensive than the original DQN due to the use of distributional RL and multi-step learning. It also has more hyperparameters to tune, which can make it more challenging to apply to new problems. Moreover, the relative importance of each component in Rainbow can vary depending on the specific task and environment. Subsequent research has investigated the contribution of each component and has shown that some components, such as prioritized experience replay and distributional RL, are generally more important than others. The Rainbow algorithm represents an important milestone in the development of deep RL algorithms. It demonstrates the power of combining multiple algorithmic improvements and provides a strong baseline for future research. The insights gained from Rainbow have also influenced the development of other deep RL algorithms and have helped to deepen our understanding of the factors that contribute to the success of deep Q-learning. Implicit quantile networks, distributional RL with flexible quantiles. Implicit quantile networks, IQN, introduced by Dabney et al. In 2018, are an advanced distributional reinforcement learning algorithm that generalizes the quantile regression DQN, QRDQN, by learning to approximate the full quantile function for the state action return distribution. Unlike QRDQN, which approximates the value distribution at a fixed set of quantiles, IQN allows for sampling the quantile fractions from any distribution, enabling a more flexible and expressive representation of the return distribution. In distributional RL, the goal is to learn the distribution of returns, rather than just the expected return. This distribution, often referred to as the value distribution, captures the inherent randomness or uncertainty in the returns due to the stochasticity of the environment, the agent's policy, or both. For example, one could sample tau uniformly from 0, 1, to approximate the full quantile function, or sample from a specific distribution to focus on certain parts of the return distribution. The IQN network is trained by minimizing the quantile regression loss, also known as the quantile Huber loss or the pinball loss. Given a target quantile value y and a predicted quantile value y for a quantile fraction tau, the quantile Huber loss is defined as L sub tau slash sub y equals tau delta sub y slash sub asterisk rho sub kappa slash sub y, where delta is an indicator function that is 1 if the condition is true and 0 otherwise. Rho sub kappa slash sub u is the Huber loss with parameter kappa, defined as rho sub kappa slash sub u equals 0, 5u sub 2 slash sub, if u less than or equal to kappa, u 0, 5 kappa. Otherwise the quantile Huber loss is an asymmetric loss function that penalizes overestimation and underestimation differently, depending on the quantile fraction tau. For tau 0, 5, overestimation is penalized more heavily, while for tau 0, 5, underestimation is penalized more heavily. The Huber loss is used to make the loss function less sensitive to large errors and to provide a smooth transition between the squared loss and the absolute loss. During training, the IQN network is updated by sampling transitions from an experience replay buffer, sampling quantile fractions for each transition, and minimizing the expected quantile Huber loss between the target quantile values and the predicted quantile values. The target quantile values are computed using a target network, similar to DQN, to improve stability. One of the advantages of IQN is its flexibility in representing the return distribution. By sampling quantile fractions from different distributions, the agent can focus on different parts of the return distribution. For example, sampling from a uniform distribution allows the agent to approximate the full quantile function, while sampling from a distribution that is skewed towards lower or higher quantiles allows the agent to focus on the tails of the distribution, which can be useful for risk-sensitive decision-making. IQN has been shown to outperform QRDQN and other distributional RL algorithms on various benchmarks, including the Atari 2600 games. It has also been combined with other improvements to deep RL, such as prioritized experience replay and multi-step returns, to further enhance performance. Despite its advantages, IQN also has some limitations. Like other distributional RL methods, it is computationally more expensive than non-distributional methods, as it requires learning a more complex representation of the value function. The performance of IQN can also be sensitive to the choice of the quantile fraction sampling distribution and the hyperparameters of the quantile Huber loss. Moreover, while IQN provides a more flexible representation of the return distribution compared to QRDQN, it still relies on a parametric model of the quantile function, which may not be able to capture all the complexities of the true distribution. Developing more expressive and flexible distributional RL algorithms is an active area of research. Some recent work has explored nonparametric approaches to distributional RL, such as using kernel methods or normalizing flows to represent the value distribution. Implicit quantile networks represent an important advance in distributional reinforcement learning, enabling a more flexible and expressive representation of the return distribution. By learning the quantile function, IQN can capture complex distributional information and adapt to different risk sensitivities, leading to improved performance and more nuanced decision-making in deep RL agents. Multi-agent reinforcement learning, cooperation, competition, and communication. Multi-agent reinforcement learning, MARL, is a subfield of reinforcement learning that deals with the problem of learning optimal policies for multiple agents that interact in a shared environment. Unlike single-agent RL, where the goal is to find an optimal policy for a single agent, MARL considers scenarios where multiple agents, each with its own policy and potentially different goals, learn and act simultaneously. This introduces new challenges and complexities that are not present in the single-agent setting. One of the key challenges in MARL is the non-stationarity of the environment. In single-agent RL, the environment is typically assumed to be stationary, meaning that the transition probabilities and reward function do not change over time. However, in MARL, the behavior of each agent affects the environment and the other agent's experiences. As the agent's policies change during learning, the environment becomes non-stationary from the perspective of any individual agent. This violates the Markov property that is often assumed in single-agent RL algorithms and can make learning more difficult. Another challenge in MARL is the problem of credit assignment. When multiple agents are acting simultaneously, it can be difficult to determine which agent's actions contributed to a particular outcome or reward. This is particularly challenging when the agent's actions have delayed or indirect effects on the environment and when the reward signal is sparse or noisy. Coordination and cooperation are also important challenges in MARL. In many multi-agent settings, the agents need to coordinate their actions to achieve a common goal or to maximize their joint reward. This requires the agents to learn compatible policies that work well together. However, achieving coordination can be difficult, especially when the agents have limited communication or when their individual incentives are not fully aligned with the global objective. Competition is another important aspect of MARL. In some multi-agent settings, the agents have conflicting goals and are competing against each other. This can lead to complex strategic interactions, where each agent needs to anticipate and respond to the actions of the other agents. Game theory provides a useful framework for analyzing such competitive scenarios and for designing algorithms that can learn effective strategies in the presence of other adaptive agents. Communication is a crucial element in many multi-agent systems. Agents may need to communicate with each other to share information, coordinate their actions, or negotiate agreements. Designing effective communication protocols and learning how to use communication effectively are important challenges in MARL. Several approaches have been developed for MARL. One common approach is independent learning, where each agent learns its own policy independently, treating the other agents as part of the environment. Independent Q-learning is an example of this approach, where each agent learns its own Q function without explicitly considering the actions or policies of the other agents. While simple, independent learning can suffer from instability and may fail to converge to optimal policies due to the non-stationarity of the environment. Another approach is centralized training with decentralized execution. In this approach, a central controller is used during training to learn a joint policy for all agents, taking into account the actions and observations of all agents. During execution, each agent uses its own decentralized policy, which is typically a component of the joint policy. This approach can help to address the non-stationarity problem and can facilitate coordination between agents. However, it may be difficult to scale to large numbers of agents and may not be applicable in settings where centralized training is not feasible. Multi-agent policy gradient methods, such as multi-agent deep deterministic policy gradient, MADG, extend policy gradient algorithms to the multi-agent setting. These methods often use a centralized critic that takes as input the actions and observations of all agents to estimate the value function, while each agent has its own actor that learns a decentralized policy. Communication between agents can be incorporated into moral algorithms in various ways. Some approaches use a shared communication channel, where agents can broadcast messages to each other. The content and usage of these messages can be learned jointly with the agent's policies. Other approaches use attention mechanisms to allow agents to selectively attend to the observations and actions of other agents. Moral has been applied to various domains, including robotics, autonomous driving, traffic control, and resource management. For example, in multi-robot coordination, moral can be used to learn policies that enable a team of robots to collaboratively perform tasks, such as exploration, surveillance, or object manipulation. In autonomous driving, moral can be used to model the interactions between multiple vehicles and to learn policies that enable safe and efficient driving in the presence of other adaptive agents. In traffic control, moral can be used to optimize the timing of traffic signals to reduce congestion and improve traffic flow. Despite the progress in moral, many challenges remain. These include developing algorithms that can scale to large numbers of agents, addressing the problem of partial observability in multi-agent settings, and designing effective mechanisms for communication, cooperation, and competition. The development of multi-agent reinforcement learning algorithms is an active and rapidly growing area of research, with the potential to enable new applications and capabilities in various domains involving multiple interacting agents. Applications in robotics, learning complex control policies. Deep reinforcement learning has emerged as a promising approach for enabling robots to learn complex control policies directly from raw sensory inputs and through interactions with their environment. By combining the representation learning capabilities of deep neural networks with the trial-and-error learning framework of reinforcement learning, DeepRL can allow robots to acquire sophisticated skills and behaviors that would be difficult to program manually. One of the key challenges in applying DeepRL to robotics is the high dimensionality of the state and action spaces. Robots often have many degrees of freedom, and their sensory inputs, such as camera images, depth maps, and joint angles, can be high-dimensional and noisy. Deep neural networks can help to address this challenge by learning compact and informative representations of the robot's state from raw sensory data. Another challenge is the cost and potential risks associated with learning from real-world interactions. Training a robot in the real world can be time-consuming, expensive, and potentially dangerous if the robot makes mistakes during the learning process. To address this challenge, researchers often use simulation environments to train DeepRL agents before deploying them on physical robots. Simulators such as MuJoCo, Gazebo, and PyBullet provide realistic physics simulations and allow for faster and safer training of robot control policies. Transfer learning techniques can then be used to adapt the policies learned in simulation to the real world. DeepRL has been used to learn a wide range of robotic skills, including locomotion, manipulation, and navigation. For example, DeepRL agents have been trained to control simulated and real-legged robots to walk, run, and perform other dynamic behaviors, such as jumping and backflips. These agents often learn directly from raw sensory inputs, such as joint angles and camera images, and can adapt to different terrains and perturbations. In manipulation tasks, DeepRL has been used to learn policies for grasping, pushing, and other complex object interactions. These policies can be learned directly from raw visual inputs, allowing robots to interact with objects in unstructured environments. For example, DeepRL agents have been trained to grasp a wide variety of objects from a cluttered bin, to assemble objects using tools, and to perform complex manipulation tasks such as opening doors and drawers. DeepRL has also been applied to robotic navigation, where the goal is to learn policies that enable robots to navigate through complex environments to reach a goal location while avoiding obstacles. These policies can be learned from raw sensory inputs, such as laser scans, depth images, or camera images, and can enable robots to navigate in previously unseen environments. One notable example of DeepRL for robotics is the dactyl system developed by OpenAI, which learned to manipulate a Rubik's Cube with a human-like robot hand. The system was trained using a combination of reinforcement learning and supervised learning and demonstrated impressive dexterity and robustness to perturbations. Despite the successes of DeepRL in robotics, several challenges remain. One challenge is the sample inefficiency of DeepRL algorithms, which can require a large number of trials to learn effective policies. This can be particularly problematic in robotics, where each trial can be time-consuming and potentially costly. Another challenge is the safety and robustness of DeepRL policies. DeepRL agents can sometimes learn unexpected or unsafe behaviors, particularly when they are deployed in environments that are different from the training environment. Ensuring the safety and reliability of DeepRL agents is a crucial area of research, particularly for applications where robots interact with humans or operate in safety-critical domains. Developing methods for incorporating prior knowledge and constraints into DeepRL algorithms is another important research direction. This can help to improve the sample efficiency of learning and to ensure that the learned policies are safe and compliant with task requirements. Techniques such as imitation learning, where the agent learns from demonstrations provided by a human expert, and inverse reinforcement learning, where the agent tries to infer the reward function from expert demonstrations, can be used to incorporate prior knowledge into DeepRL. The development of DeepRL algorithms that can learn from limited real-world interactions and can generalize to new, unseen environments and tasks is a key challenge for the field. Techniques such as meta-learning, transfer learning, and domain randomization are being explored to address this challenge. As DeepRL algorithms continue to improve and as simulation and transfer learning techniques become more sophisticated, we can expect to see DeepRL playing an increasingly important role in enabling robots to acquire complex skills and behaviors and to operate more autonomously and effectively in the real world. Applications in game playing, superhuman performance in complex games. Deep reinforcement learning has achieved remarkable success in the domain of game playing, with DeepRL agents demonstrating superhuman performance in several complex games that were previously considered to be extremely challenging for AI systems. These successes have not only advanced the state-of-the-art in game playing but have also deepened our understanding of learning and decision-making in complex, strategic environments. One of the most notable achievements of DeepRL in game playing is the development of AlphaGo by DeepMind. AlphaGo was the first computer program to defeat a professional human player in the game of Go, a feat that was previously thought to be decades away. Go is an ancient board game that is known for its strategic depth and complexity, with a search space that is vastly larger than that of chess. AlphaGo combined deep neural networks with Monte Carlo tree search, MCTS, to achieve its groundbreaking performance. It used a value network to evaluate board positions and a policy network to select moves. The networks were initially trained using supervised learning on a dataset of human expert games, and then further improved using reinforcement learning through self-play. AlphaGo's victory over Lee Sedol, one of the world's top Go players, in 2016 was a landmark moment in the history of artificial intelligence. It demonstrated the power of DeepRL to master complex, strategic tasks that require long-term planning and intuition. Building on the success of AlphaGo, DeepMind developed AlphaGo Zero, a more general and powerful version of the algorithm that learned to play Go from scratch, without any human data or prior knowledge beyond the basic rules of the game. AlphaGo Zero used a single neural network that combined the policy and value functions, and it was trained purely through self-play reinforcement learning, starting from random play. Remarkably, AlphaGo Zero surpassed the performance of all previous versions of AlphaGo, including the one that defeated Lee Sedol, after just a few days of training. AlphaZero extended these ideas to other games, demonstrating that a single algorithm could learn to play Go, chess, and shogi at a superhuman level, starting from random play and without any game-specific knowledge beyond the basic rules. This showed that deep RL can be a powerful and general approach for learning complex strategic behaviors. Deep RL has also achieved impressive results in video games. DeepMind's DQN algorithm was the first deep RL agent to learn to play a wide range of Atari games directly from pixel inputs, achieving human-level or even superhuman performance in many of them. This work demonstrated the potential of combining deep learning with reinforcement learning to solve complex, high-dimensional problems. More recently, deep RL agents have achieved superhuman performance in more complex video games, such as Dota 2 and StarCraft 2. OpenAI 5, a team of deep RL agents developed by OpenAI, defeated the world champions in the game of Dota 2, a complex team-based multiplayer game that requires long-term planning, coordination, and adaptation. AlphaStar, developed by DeepMind, achieved Grandmaster level in StarCraft 2, a real-time strategy game that is known for its complexity and strategic depth. AlphaStar used a combination of supervised learning from human expert games and reinforcement learning through self-play, and it demonstrated advanced strategic decision-making and adaptation during gameplay. These successes in game playing have implications beyond games themselves. They demonstrate that deep RL can be used to learn complex, strategic behaviors in environments with large state and action spaces, partial observability, and long time horizons. These capabilities are also relevant to many real-world problems, such as robotics, autonomous driving, and resource management. However, applying deep RL to real-world problems also poses significant challenges. Real-world environments are often more complex, unpredictable, and less well-defined than game environments. They may involve safety constraints, ethical considerations, and the need to interact with humans. Developing deep RL algorithms that are safe, robust, and efficient enough to be deployed in real-world settings is an active area of research. This includes developing methods for incorporating prior knowledge and constraints into deep RL, improving the sample efficiency and generalization of deep RL algorithms, and addressing issues of interpretability, safety, and ethics. The successes of deep RL in game playing have been a major driver of progress in the field and have captured the public imagination. They have shown that deep RL can enable the development of AI systems with superhuman capabilities in complex, strategic domains, and they have paved the way for future advances in deep RL and its application to real-world problems. Lesson 17, Deep Learning for Computer Vision, Introduction to Advanced Topics in Computer Vision. Computer vision is a field of artificial intelligence that aims to enable computers to understand and interpret visual information from the real world, such as images and videos. Deep learning has revolutionized the field of computer vision, leading to significant advances in various tasks, including image classification, object detection, semantic segmentation, and image generation. While earlier lessons have covered the fundamentals of CNNs and their applications in computer vision, this lesson will delve into more advanced topics and cutting-edge techniques in this rapidly evolving field. One important area of research in deep learning for computer vision is the development of more efficient and lightweight models. As deep learning models are increasingly deployed on resource-constrained devices, such as mobile phones and embedded systems, there is a growing need for models that can perform inference quickly and with low memory and power consumption. This has led to the development of efficient architectures, such as mobile nets, shuffle nets, and efficient nets, which we discussed in Lesson 11. Another important direction is the development of models that can learn from limited labeled data. While deep learning has achieved impressive results on tasks with large labeled datasets, collecting and annotating large amounts of data can be expensive and time-consuming, particularly for specialized domains such as medical imaging or rare object detection. Techniques such as transfer learning, self-supervised learning, and few-shot learning aim to reduce the reliance on large labeled datasets and enable models to learn effectively from limited data. The robustness and security of computer vision models are also crucial areas of research. Deep learning models, including CNNs, have been shown to be vulnerable to adversarial examples, which are inputs that are specifically designed to fool the model into making incorrect predictions. Developing methods to defend against adversarial attacks and to improve the robustness of models to various types of noise and perturbations is an active area of research. Another important topic is the development of models that can understand and reason about 3D visual data. While much of the work in deep learning for computer vision has focused on 2D images, many real-world applications, such as robotics, autonomous driving, and augmented reality, require an understanding of the 3D structure of the world. This has led to the development of models that can process 3D data, such as point clouds, meshes, and voxels, and perform tasks such as 3D object detection, segmentation, and reconstruction. The interpretability and explainability of computer vision models are also receiving increasing attention. As deep learning models are deployed in high-stakes applications, it becomes crucial to understand how they arrive at their decisions and to be able to provide explanations for their predictions. Techniques such as attention mechanisms, saliency maps, and model-agnostic methods like LIME and SHAP are being used to provide insights into the decision-making process of computer vision models. In this lesson, we will explore some of these advanced topics in more detail, focusing on cutting-edge techniques and recent research developments in deep learning for computer vision. We will cover topics such as advanced object detection and segmentation methods, 3D computer vision, video analysis, and generative models for images and videos. We will also discuss emerging trends and challenges in the field, such as the need for more efficient, robust, and interpretable models, and the growing importance of learning from limited labeled data. By the end of this lesson, you will have a deeper understanding of the state-of-the-art in deep learning for computer vision and the exciting research directions that are shaping the future of this field. Advanced object detection, anchor-free methods and transformer-based detectors. Object detection is a fundamental task in computer vision that involves identifying and localizing objects within an image. While earlier lessons introduced popular object detection frameworks like faster RCNN, SSD, and YOLO, recent research has explored more advanced techniques that push the boundaries of object detection performance. One significant trend is the development of anchor-free methods, which eliminate the need for predefined anchor boxes. Anchor-based methods, such as faster RCNN and SSD, rely on a set of predefined anchor boxes of different scales and aspect ratios to generate region proposals. These methods typically involve complex anchor matching and non-maximum suppression steps, which can be computationally expensive and require careful tuning of hyperparameters. Anchor-free methods, on the other hand, directly predict object bounding boxes without using anchor boxes, simplifying the detection pipeline and often improving performance. One of the first successful anchor-free methods was YOLO 9000, which extended the original YOLO architecture to predict bounding boxes directly from grid cells without using anchors. DenseBox, another early anchor-free method, predicted bounding boxes and objectness scores at each location of a feature map. CornerNet, introduced by Law and Deng in 2018, is a notable anchor-free method that detects objects by predicting the top left and bottom right corners of their bounding boxes. CornerNet uses a single convolutional neural network to predict heat maps for the top left corners and bottom right corners of objects belonging to each class, as well as embeddings that are used to group pairs of corners belonging to the same object. CornerNet achieved state-of-the-art results on the MS-COCO benchmark, demonstrating the effectiveness of anchor-free object detection. CenterNet, introduced by Zhou et al. In 2019, is another anchor-free method that detects objects as points. Instead of predicting corners or bounding boxes directly, CenterNet predicts the center point of each object and then regresses to the object's size and other properties. CenterNet uses a fully convolutional network to generate heat maps for the center points of objects belonging to each class, as well as maps for object size and offset. CenterNet is simpler and faster than many anchor-based methods and has achieved competitive performance on benchmark datasets. FCOS, Fully Convolutional One-Stage Object Detector, introduced by Tian et al. In 2019, is an anchor-free, per-pixel prediction method that is similar in spirit to semantic segmentation. FCOS predicts a 4D vector representing the distances from each location on the feature map to the four sides of the bounding box, as well as an objectness score. FCOS uses a feature pyramid network, FPN, to detect objects at multiple scales and introduces a centerness branch to suppress low-quality detections far from object centers. Another trend in advanced object detection is the use of transformer-based architectures. DETR, Detection Transformer, introduced by Karian et al. In 2020, was the first work to successfully apply a transformer to object detection. DETR uses a standard CNN backbone to extract image features and then feeds these features into a transformer encoder-decoder architecture. The decoder takes as input a small fixed number of learned positional embeddings, called object queries, and attends to the encoder output to predict a set of bounding boxes and class labels. DETR simplifies the object detection pipeline by eliminating the need for hand-designed components like anchor generation and non-maximum suppression. It also enables end-to-end optimization of the detection process using a set prediction loss based on bipartite matching between predicted and ground truth objects. DETR has achieved competitive performance compared to highly optimized faster RCNN baselines on the COCO dataset, while being conceptually simpler and more flexible. It has also inspired follow-up work that aims to improve its efficiency and performance, such as deformable DETR, which uses deformable attention modules to focus on a sparse set of key sampling points around each reference point. The development of advanced object detection methods is an active and rapidly evolving area of research. Anchor-free methods and transformer-based detectors have shown great promise in simplifying the detection pipeline, improving performance, and enabling new capabilities, such as end-to-end learning and more flexible output representations. As research in this area continues, we can expect to see even more powerful and efficient object detection models that can handle increasingly complex and diverse scenes. Advanced segmentation, instance segmentation and panoptic segmentation. Semantic segmentation, which involves assigning a class label to each pixel in an image, is a fundamental task in computer vision. While earlier lessons introduced basic semantic segmentation architectures like UNet, advanced segmentation methods go beyond pixel-level classification and aim to identify and delineate individual object instances within an image. This is known as instance segmentation. Instance segmentation combines the challenges of object detection, where the goal is to localize individual objects, and semantic segmentation, where the goal is to classify each pixel. Instance segmentation methods typically output a segmentation mask for each detected object instance, providing a more detailed understanding of the scene. Mask RCNN, introduced by He et al. In 2017, is one of the most influential and widely used instance segmentation frameworks. Mask RCNN extends faster RCNN, a popular object detection framework, by adding a branch for predicting an object mask in parallel with the existing branch for bounding box recognition. The mask RCNN architecture consists of a backbone network, typically a ResNet or ResNeXT, followed by a region proposal network, RPN, that generates region proposals. For each region proposal, a row-align operation is used to extract a fixed-size feature map from the backbone's output. These feature maps are then fed into two branches, a bounding box classification and regression branch, which is the same as in faster RCNN, and a mask prediction branch, which is a small fully convolutional network that predicts a binary mask for each object class. One of the key contributions of mask RCNN is the row-align operation, which addresses the misalignment issue caused by the quantization in the original row-I-pool operation used in faster RCNN. Row-align uses bilinear interpolation to compute the values of the input features at 4 regularly sampled locations in each ROI bin and then aggregates the results using max or average pooling. This more accurate spatial alignment significantly improves the performance of mask prediction. Mask RCNN is trained end-to-end with a multitask loss that combines the losses for classification, bounding box regression, and mask prediction. The mask branch is trained using a per-pixel sigmoid and binary cross-entropy loss. Mask RCNN has achieved state-of-the-art results on various instance segmentation benchmarks, such as the COCO dataset. It is also relatively efficient and can be used for real-time instance segmentation. Several extensions and improvements to mask RCNN have been proposed. Path Aggregation Network (PANET) introduces a bottom-up path augmentation that enhances the information flow in the network. Cascade Mask RCNN uses a cascade of detectors to refine the mask predictions iteratively. Hybrid Task Cascade (HTC) combines instance segmentation and semantic segmentation in a single framework, using a joint multitask cascade architecture. Panoptic segmentation is a more recent task that unifies semantic segmentation and instance segmentation. Introduced by Kirillov et al. In 2018, panoptic segmentation aims to assign a class label to each pixel in the image and to segment each object instance, providing a complete and unified understanding of the scene. In panoptic segmentation, each pixel is assigned a semantic label and an instance ID. Pixels belonging to the same object instance have the same instance ID, while pixels belonging to stuff classes, e.g., sky, road, wall, do not have an instance ID. The performance of panoptic segmentation is typically measured using the panoptic quality (PQ) metric, which combines segmentation quality and recognition quality. Several approaches have been proposed for panoptic segmentation. One common approach is to combine the outputs of a semantic segmentation network and an instance segmentation network. For example, the Panoptic Feature Pyramid Network (FPN) uses a feature pyramid network to generate semantic segmentation predictions and combines them with the output of a mask RCNN model for instance segmentation. Another approach is to use a single network to jointly predict semantic and instance segmentation. The UPSNet, Unified Panoptic Segmentation Network, uses a parameter-free panoptic head that combines semantic and instance segmentation predictions based on the objectness scores and a learned kernel. Panoptic segmentation is a challenging task that requires a unified understanding of both things, countable objects, and stuff, amorphous regions of similar texture or material. It has important applications in autonomous driving, robotics, and scene understanding. The development of advanced segmentation methods, including instance segmentation and panoptic segmentation, is an active and rapidly evolving area of research in computer vision. These methods provide a more detailed and comprehensive understanding of visual scenes compared to traditional semantic segmentation and have the potential to enable new applications in various domains. 3D computer vision, point clouds, meshes, and volumetric representations. While much of the work in computer vision has focused on 2D images, there is a growing interest in developing deep learning methods for understanding and processing 3D data. 3D computer vision has important applications in various domains, including robotics, autonomous driving, augmented reality, and 3D content creation. Unlike 2D images, which are typically represented as regular grids of pixels, 3D data can be represented in various forms, such as point clouds, meshes, and volumetric grids. Point clouds are one of the most common representations of 3D data. A point cloud is a set of 3D points, where each point is typically represented by its x, y, z coordinates. Point clouds can be acquired using sensors such as LiDAR scanners or can be reconstructed from multiple 2D images using techniques like structure from motion. One of the challenges in processing point clouds with deep learning is that they are unordered sets of points, and the number of points can vary. This makes it difficult to apply standard convolutional neural networks, CNNs, directly to point clouds. PointNet, introduced by Chi et al. In 2017, was one of the first deep learning architectures designed specifically for processing point clouds. PointNet processes each point independently using a shared multilayer perceptron, MLP, to learn per point features. It then aggregates these features using a symmetric function, such as max pooling, to obtain a global feature vector that is invariant to the order of the points. PointNet can be used for tasks such as 3D object classification and segmentation. PointNet++ is an extension of PointNet that introduces a hierarchical structure to capture local patterns at different scales. It recursively applies PointNet on increasingly larger neighborhoods of points, similar to how CNNs capture hierarchical features in images. Other approaches for processing point clouds with deep learning include using graph neural networks, GNNs, which can operate on irregular graph structures, and projecting point clouds onto 2D planes or volumetric grids to leverage standard CNN architectures. Meshes are another common representation of 3D data, particularly in computer graphics and 3D modeling. A mesh is a collection of vertices, edges, and faces that define the shape of a 3D object. Unlike point clouds, meshes explicitly represent the surface and topology of the object. Processing meshes with deep learning poses challenges due to their irregular structure. One approach is to use graph neural networks that operate directly on the mesh structure, where vertices or edges are treated as nodes in the graph. MeshCNN, for example, defines convolution and pooling operations on meshes by exploiting the regular structure of mesh edges. Another approach is to convert the mesh into a volumetric representation or a multi-view representation that can be processed using standard CNN architectures. Volumetric representations discretize the 3D space into a regular grid of voxels, volumetric pixels, and represent the object as a binary occupancy grid, where each voxel is labeled as either occupied or empty. Volumetric CNNs can then be used to process this representation, similar to how 2D CNNs process images. However, volumetric representations can be memory-intensive and computationally expensive, particularly at high resolutions. Octree-based CNNs and sparse convolutional networks have been proposed to address this issue by exploiting the sparsity of volumetric data. Multi-view representations, on the other hand, represent a 3D object as a collection of 2D views rendered from different viewpoints. These views can then be processed using standard 2D CNNs, and the resulting features can be aggregated to obtain a global representation of the object. 3D shape generation is another important task in 3D computer vision. Generative models, such as autoencoders, VAEs, and GANs, have been adapted to generate 3D shapes represented as point clouds, meshes, or volumetric grids. These models can learn to generate novel 3D shapes, reconstruct 3D shapes from partial or noisy data, and perform shape completion and interpolation. 3D object detection and segmentation are also active research areas. These tasks involve identifying and localizing objects in 3D data, such as point clouds or volumetric grids, and segmenting them into individual instances. Extensions of popular 2D object detection and segmentation methods, such as faster RCNN and mask RCNN, have been proposed for 3D data. Deep learning for 3D computer vision is a rapidly growing field with many exciting research directions. These include developing more efficient and effective architectures for processing different 3D representations, improving the quality and diversity of generated 3D shapes, and developing methods for 3D scene understanding that can handle complex, cluttered environments. As 3D sensors become more prevalent and the demand for 3D understanding increases in applications such as robotics, autonomous driving, and augmented reality, deep learning will play an increasingly important role in enabling computers to perceive and interact with the 3D world. Video analysis, action recognition, video object tracking, and segmentation video analysis is an important area of computer vision that deals with understanding and processing sequences of images over time. Unlike static image analysis, video analysis needs to take into account the temporal dimension and model the motion and changes that occur between frames. Deep learning has significantly advanced the state-of-the-art in various video analysis tasks, including action recognition, object tracking, and video segmentation. Action recognition is the task of identifying and classifying actions or activities in a video. This can involve recognizing simple actions, such as walking or running, or more complex activities, such as making a sandwich or playing a musical instrument. Action recognition has applications in various domains, including surveillance, human-computer interaction, and sports analysis. One approach to action recognition using deep learning is to use 3D convolutional neural networks, 3D CNNs, which extend the 2D convolutions used in image analysis to the temporal dimension. 3D CNNs can capture spatiotemporal features by applying 3D convolutional filters that span both space and time. C3D, convolutional 3D, is an example of a 3D CNN architecture that has been successfully applied to action recognition. Another approach is to use a two-stream architecture, where one stream processes the appearance information from individual frames using a 2D CNN, and the other stream processes the motion information, typically represented as optical flow, using another 2D CNN. The outputs of the two streams are then fused to make the final prediction. Recurrent neural networks, RNNs, particularly LSTMs, have also been used for action recognition. RNNs can model the temporal dependencies between frames and learn to recognize actions based on the sequence of features extracted from each frame. More recently, transformer-based architectures have shown promise for action recognition. These models use self-attention mechanisms to capture long-range dependencies between frames and have achieved state-of-the-art results on several action recognition benchmarks. Video object tracking is another important task in video analysis, which involves localizing a specific object in each frame of a video sequence, given its initial location in the first frame. Object tracking has applications in surveillance, autonomous driving, and human-computer interaction. One approach to object tracking using deep learning is to use Siamese networks, which learn a similarity function between two inputs. In the context of tracking, a Siamese network can be trained to compare a template image of the target object with candidate regions in each frame of the video. The region with the highest similarity score is selected as the new location of the object. MDNet, multi-domain network, is another deep learning-based approach to object tracking that uses a pre-trained CNN to extract features from the target object and the search region in each frame. It then uses a fully connected layer to classify each region as either the target object or background. MDNet is trained online using multiple domains, i.e., different videos, to learn a more robust representation of the target object. Correlation filters have also been combined with deep learning for object tracking. The DeepSRDCF method, for example, uses a CNN to extract features from the target object in the search region, and then learns a correlation filter in the feature space to localize the object in subsequent frames. Video object segmentation is the task of segmenting a specific object in each frame of a video sequence, given its segmentation mask in the first frame. This is also known as semi-supervised video object segmentation, as the segmentation mask is only provided for the first frame. Video object segmentation has applications in video editing, robotics, and augmented reality. One approach to video object segmentation using deep learning is to use a fully convolutional network that takes the first frame and its mask as input, as well as the current frame, and outputs a segmentation mask for the current frame. OSPOS, one-shot video object segmentation, is an example of this approach, which fine-tunes a pre-trained semantic segmentation network on the first frame and its mask to learn the appearance of the target object. Another approach is to use a Siamese network to learn a similarity metric between the target object and each pixel in the current frame. The Siam mask method, for example, combines a Siamese network with a mask prediction branch to perform both object tracking and segmentation. Spacetime memory networks are another class of models that have been proposed for video object segmentation. These networks maintain a memory of past frames and their corresponding masks, and use an attention mechanism to retrieve relevant information from the memory when processing the current frame. Video analysis is a challenging and active area of research in computer vision. Deep learning has significantly advanced the state-of-the-art in tasks such as action recognition, object tracking, and video segmentation, but many challenges remain. These include handling long-range temporal dependencies, dealing with occlusions and fast motion, and developing models that can generalize to new, unseen videos. The development of more efficient and effective deep learning models for video analysis is an important research direction. This includes exploring new architectures, such as 3D CNNs, RNNs, and transformers, as well as developing methods for unsupervised and self-supervised learning from video. As video data becomes increasingly prevalent and as applications such as autonomous driving, robotics, and video surveillance become more widespread, the importance of video analysis will only continue to grow. Generative models for images and videos, VAEs, GANs, and autoregressive models. Generative models have become a powerful tool in computer vision for creating new, realistic images and videos. These models learn the underlying distribution of the training data and can generate novel samples that are similar to, but not exact copies of, the training examples. Generative models have applications in various domains, including image synthesis, video prediction, image editing, and data augmentation. Variational autoencoders, VAEs, which were introduced in Lesson 5, are one class of generative models that can be used for image and video generation. VAEs combine the autoencoder architecture with probabilistic modeling to learn a latent representation of the data that follows a specific probability distribution, typically a multivariate Gaussian. To generate a new sample, a VAE first samples a latent vector from the prior distribution, usually a standard normal distribution, and then passes it through the decoder network to generate a data sample. The decoder is typically a deep neural network, such as a CNN for image generation or an RNN for sequence generation. VAEs are trained by maximizing a variational lower bound on the log likelihood of the data. This involves minimizing a reconstruction loss, which measures the difference between the input and the reconstructed output, and a KL divergence term, which encourages the learned latent distribution to be close to the prior distribution. Generative adversarial networks, GANs, which were also covered in Lesson 5, are another powerful class of generative models that have achieved impressive results in image synthesis. GANs train two networks, a generator and a discriminator, in an adversarial manner. The generator learns to create new data samples that are similar to the training data, while the discriminator learns to distinguish between real data samples and generated samples. Through this adversarial process, the generator learns to produce increasingly realistic data samples. GANs have been used to generate high-quality images in various domains, including faces, objects, and scenes. Advanced GAN architectures, such as DC-GAN, Style-GAN, and Big-GAN, have pushed the boundaries of image generation, producing images that are often indistinguishable from real images to the human eye. GANs have also been extended to video generation. This typically involves using a 3D CNN or a combination of CNNs and RNNs to model the spatial and temporal structure of videos. Video GANs have been used to generate short video clips, to predict future frames in a video sequence, and to perform video-to-video translation. Autoregressive models are another class of generative models that can be used for image and video generation. These models generate data sequentially, one pixel or one frame at a time, conditioned on the previously generated pixels or frames. PixelRNN and PixelCNN are examples of autoregressive models for image generation that use RNNs and CNNs, respectively, to model the conditional distribution of each pixel given the previously generated pixels. For video generation, autoregressive models can be used to predict the next frame in a sequence given the previous frames. This can be done using RNNs, 3D CNNs, or a combination of both. Autoregressive models have the advantage of providing a tractable likelihood for the generated data, which can be useful for tasks such as anomaly detection and density estimation. However, they can be slow to generate samples from, as each pixel or frame must be generated sequentially. Generative models for images and videos have numerous applications beyond simply creating new samples. They can be used for image and video editing, such as in painting missing regions, super resolution, and style transfer. They can also be used for data augmentation, where new training examples are generated by applying transformations or perturbations to existing examples. Moreover, generative models can be used to learn useful representations of images and videos, which can then be used for downstream tasks such as classification, detection, and segmentation. For example, the latent representations learned by VAEs can be used as features for image classification, and the features learned by GN discriminators have been shown to be useful for object detection. Despite the impressive results achieved by generative models, several challenges remain. One challenge is the evaluation of generative models, as there is no single metric that captures all aspects of the quality and diversity of generated samples. Another challenge is the mode collapse problem in GANs, where the generator produces only a limited variety of samples, failing to capture the full diversity of the training data distribution. Developing more stable and efficient training algorithms for generative models, as well as better evaluation metrics, are active areas of research. There is also growing interest in developing generative models that can learn disentangled representations, where different factors of variation in the data are captured by separate latent variables. This can improve the interpretability and controllability of the generated samples. The field of generative models for images and videos is rapidly evolving, with new architectures, training methods, and applications constantly being developed. As these models continue to improve, they will likely play an increasingly important role in various computer vision tasks and enable new forms of creative expression and content creation. Emerging trends and challenges in deep learning for computer vision. Deep learning for computer vision is a dynamic and rapidly evolving field, with new research directions and trends constantly emerging. As the field matures, researchers are tackling increasingly complex problems and developing more sophisticated models and techniques to address the limitations of current approaches. One important trend is the development of models that can learn from limited labeled data. While deep learning has achieved impressive results on tasks with large labeled datasets, collecting and annotating large amounts of data can be expensive and time-consuming, particularly for specialized domains. Self-supervised learning, which we discussed in Lesson 14, has emerged as a powerful paradigm for learning from unlabeled data by creating auxiliary supervised learning tasks from the data itself. Contrastive learning, in particular, has shown great promise in learning visual representations that are competitive with or even superior to those learned through full supervision. Few-shot learning and meta-learning are also gaining increasing attention. These approaches aim to develop models that can quickly adapt to new tasks or classes with only a few examples, mimicking the ability of humans to learn from limited experience. Meta-learning algorithms, such as MAML and Reptile, learn to learn by training on a distribution of tasks and optimizing for fast adaptation to new tasks. Another important trend is the development of more efficient and lightweight models for deployment on resource-constrained devices. As computer vision applications are increasingly deployed on mobile phones, embedded systems, and other edge devices, there is a growing need for models that can perform inference quickly and with low memory and power consumption. Model compression techniques, such as pruning, quantization, and knowledge distillation, are being actively researched to reduce the size and computational cost of deep learning models without significantly sacrificing accuracy. The robustness and security of computer vision models are also receiving increased attention. Adversarial examples have highlighted the vulnerability of deep learning models to small, carefully crafted perturbations in the input. Developing methods to defend against adversarial attacks and to improve the robustness of models to various types of noise and perturbations is an important research direction. Adversarial training, which involves augmenting the training data with adversarial examples, has shown promise in improving robustness but can also reduce accuracy on clean examples. Other approaches, such as input transformations, model ensembling, and certified defenses, are also being explored. The interpretability and explainability of computer vision models are becoming increasingly important, particularly as these models are deployed in high-stakes applications. Techniques such as attention mechanisms, saliency maps, and model-agnostic methods like LIME and SHAP are being used to provide insights into the decision-making process of deep learning models. However, developing more comprehensive and reliable methods for interpreting and explaining complex vision models remains an open challenge. Another important research direction is the development of models that can understand and reason about 3D visual data. While much of the work in deep learning for computer vision has focused on 2D images, many real-world applications, such as robotics, autonomous driving, and augmented reality, require an understanding of the 3D structure of the world. This has led to the development of models that can process 3D data, such as point clouds, meshes, and voxels, and perform tasks such as 3D object detection, segmentation, and reconstruction. The intersection of computer vision with other fields, such as natural language processing and graphics, is also an exciting area of research. Joint models of vision and language can enable new applications, such as visual question answering, image captioning, and text-guided image editing. The combination of computer vision and graphics can lead to improved methods for 3D scene understanding, rendering, and animation. Finally, the societal impact of computer vision technologies is receiving increasing scrutiny. Issues such as bias, fairness, privacy, and security are being recognized as crucial considerations in the development and deployment of computer vision systems. Researchers are working on methods to detect and mitigate biases in datasets and models, to ensure fairness and equity in the application of computer vision, and to develop privacy-preserving techniques for visual data. As deep learning for computer vision continues to advance, it is essential to address these challenges and to develop models and techniques that are not only accurate and efficient but also robust, interpretable, and ethically sound. The field is constantly evolving, driven by new research breakthroughs, the availability of new datasets and computational resources, and the growing demand for intelligent visual systems in various real-world applications. The coming years will likely see even more exciting developments in this dynamic field, further pushing the boundaries of what's possible in computer vision. Lesson 18, Deep Learning for Natural Language Processing, Introduction to Advanced Topics in NLP. Natural Language Processing, NLP, is a field of artificial intelligence that focuses on enabling computers to understand, interpret, and generate human language. Deep learning has revolutionized the field of NLP in recent years, leading to significant advances in various tasks such as machine translation, text classification, question answering, and text generation. While earlier lessons have covered the fundamentals of RNNs and their applications in NLP, this lesson will delve into more advanced topics and cutting-edge techniques in this rapidly evolving field. One major trend in deep learning for NLP is the development of large-scale pre-trained language models, such as BERT, GPT, and Roberta. These models are trained on massive text corpora using self-supervised learning objectives, such as masked language modeling and next sentence prediction. They learn rich representations of words and sentences that capture syntactic and semantic information, and they can be fine-tuned for various downstream tasks with relatively small amounts of labeled data. The use of pre-trained language models has become a cornerstone of modern NLP, significantly improving the state of the art across a wide range of tasks and simplifying the development process by reducing the need for task-specific architectures and large labeled datasets. Another important direction is the development of models that can better capture long-range dependencies and complex structures in text. While RNNs, particularly LSTMs and GRUs, have been successful in modeling sequential data, they can still struggle with very long sequences and complex syntactic or semantic relationships. Transformers, which use self-attention mechanisms to capture relationships between all words in a sequence in parallel, have emerged as a powerful alternative to RNNs and have achieved state-of-the-art results in many NLP tasks. The development of more efficient and interpretable attention mechanisms is an active area of research. Multitask learning and transfer learning are also important trends in deep learning for NLP. Multitask learning involves training a single model on multiple related tasks simultaneously, allowing the model to learn shared representations that are useful across tasks. This can improve performance, particularly when labeled data is limited for some of the tasks. Transfer learning, as discussed in Lesson 13, involves leveraging knowledge learned from one task or domain to improve performance on a different but related task or domain. Pre-trained language models are a prime example of transfer learning in NLP. Another important area of research is the development of models that can reason and perform inference over text. This includes tasks such as natural language inference, question answering, and reading comprehension, which require the model to understand the meaning of text and draw conclusions based on the information presented. Deep learning models that incorporate external knowledge, such as knowledge graphs or common sense knowledge bases, are also being explored to improve their reasoning and inference capabilities. The interpretability and explainability of deep learning models for NLP are receiving increasing attention. As these models are deployed in real-world applications, it becomes crucial to understand how they arrive at their decisions and to be able to provide explanations for their predictions. Techniques such as attention visualization, saliency maps, and model-agnostic methods like LIME and SHAP are being adapted and applied to NLP models to provide insights into their behavior. In this lesson, we will explore some of these advanced topics in more detail, focusing on cutting-edge techniques and recent research developments in deep learning for NLP. We will cover topics such as advanced attention mechanisms, transformer-based models, multitask and transfer learning, and methods for incorporating external knowledge into deep learning models. We will also discuss emerging trends and challenges in the field, such as the need for more efficient and interpretable models, the development of models that can handle low-resource languages, and the ethical considerations surrounding the use of deep learning in NLP. By the end of this lesson, you will have a deeper understanding of the state-of-the-art in deep learning for NLP and the exciting research directions that are shaping the future of this field. Advanced attention mechanisms, multi-head attention, self-attention, and more attention mechanisms have become a crucial component in many deep learning models for natural language processing, allowing models to focus on the most relevant parts of the input when making predictions. While earlier lessons introduced the basic concept of attention, this section will delve into more advanced attention mechanisms, such as multi-head attention and self-attention, which have been instrumental in the success of models like the transformer. Multi-head attention, introduced in the transformer architecture, extends the basic attention mechanism by allowing the model to attend to information from different representation subspaces at different positions. Instead of performing a single attention computation, multi-head attention performs multiple attention computations in parallel, each with different learned linear projections of the input. The input sequence is first linearly projected into multiple sets of queries, keys, and values, using different learned weight matrices for each head. The scaled dot product attention is then computed separately for each head, resulting in multiple output sequences. These output sequences are concatenated and linearly projected again to produce the final output of the multi-head attention layer. The multi-head attention mechanism can be formalized as follows: multi-head, Q, K, V, equals concat, head sub 1 slash sub comma, head sub H slash sub, W sub O slash sub, where head sub I slash sub equals attention, QW sub I slash sub Q slash sub, KW sub I slash sub K slash sub, VW sub I slash sub V slash sub. Here, Q, K, and V are the input matrices representing the queries, keys, and values, respectively. W sub I slash sub Q slash sub, W sub I slash sub K slash sub, and W sub I slash sub V slash sub are the weight matrices for the ITH head, and W sub O slash sub is the output weight matrix. The scaled dot product attention for each head is computed as attention, Q, K, V, equals softmax, QK sub T slash sub forward slash square root D sub K slash sub, where D sub K slash sub is the dimension of the keys. By using multiple attention heads, the model can jointly attend to information from different representation subspaces at different positions. This allows the model to capture more complex relationships and dependencies in the input sequence. Self-attention is a special case of attention where the queries, keys, and values are all derived from the same input sequence. In other words, self-attention allows the model to attend to different parts of the input sequence itself, rather than attending to a separate sequence. Self-attention is a key component of the transformer architecture and has been instrumental in its success in various NLP tasks. In self-attention, each element in the input sequence is used to compute a query, a key, and a value. The attention weights are then computed based on the similarity between the query of each element and the keys of all elements in the sequence. This allows the model to capture relationships between all pairs of elements in the sequence, regardless of their distance. The self-attention mechanism can be seen as a way for the model to dynamically weight the importance of each element in the sequence when computing the representation of another element. They provide a powerful and flexible way for models to focus on the most relevant parts of the input and to capture complex relationships between different elements in a sequence or a set. The development of new and improved attention mechanisms is an active area of research in deep learning for NLP. Transformer networks, encoder, decoder, and applications. The transformer, introduced by Vaswani et al. In 2017, is a neural network architecture that has revolutionized the field of natural language processing. Unlike recurrent neural networks, RNNs, which process sequential data one element at a time, the transformer relies entirely on attention mechanisms to capture relationships between input elements and generate output. This allows the transformer to process the entire input sequence in parallel, leading to significant improvements in training efficiency and performance. The transformer architecture consists of an encoder and a decoder, each composed of a stack of identical layers. The encoder is responsible for processing the input sequence and generating a contextualized representation of each element. The decoder is responsible for generating the output sequence, attending to both the encoder output and the previously generated output elements. Each encoder layer consists of two sublayers, a multi-head self-attention mechanism and a position-wise fully connected feed-forward network. The multi-head self-attention mechanism allows the model to jointly attend to information from different representation subspaces at different positions in the input sequence. The feed-forward network applies a nonlinear transformation to each position separately and identically. Each encoder layer also includes residual connections around each of the two sublayers, followed by layer normalization. The residual connections help to mitigate the vanishing gradient problem and enable the training of deeper networks. The layer normalization helps to stabilize the training process and improve generalization. The decoder is similar to the encoder but has an additional sublayer in each layer that performs multi-head attention over the output of the encoder stack. This allows the decoder to attend to relevant parts of the input sequence when generating each output element. The decoder also uses masked self-attention in its first sublayer to prevent positions from attending to subsequent positions, ensuring that the predictions for each position can depend only on the known outputs at positions less than the current position. The transformer uses positional encodings to provide information about the position of each element in the input sequence. Since the transformer does not have any recurrent or convolutional structure, it needs a way to make use of the order of the sequence. The positional encodings are added to the input embeddings at the bottoms of the encoder and decoder stacks. They have the same dimension as the embedding so that the two can be summed. The original transformer model was developed for machine translation, where the input sequence is a sentence in the source language, and the output sequence is the corresponding translation in the target language. The transformer achieved state-of-the-art results on several machine translation benchmarks, outperforming previous RNN-based models while being significantly faster to train due to its parallelizable architecture. Since its introduction, the transformer has been adapted and extended for various other NLP tasks beyond machine translation. BERT, bidirectional encoder representations from transformers, is a transformer-based model that is pre-trained on a large text corpus using a masked language modeling objective and a next sentence prediction objective. BERT learns deep bidirectional representations by jointly conditioning on both left and right context in all layers. The pre-trained BERT model can be fine-tuned for a wide range of downstream tasks, such as text classification, question answering, and named entity recognition, often achieving state-of-the-art results with minimal task-specific modifications. GPT, Generative Pre-trained Transformer, is another transformer-based model that is pre-trained using a language modeling objective, where the model predicts the next word in a sequence given the previous words. Unlike BERT, GPT uses a left-to-right, autoregressive architecture. GPT models, such as GPT-2 and GPT-3, have demonstrated remarkable capabilities in generating coherent and contextually relevant text and have achieved strong performance on various NLP tasks in a zero-shot or few-shot setting. The transformer architecture has also been applied to other domains beyond NLP, such as computer vision and audio processing. The Vision Transformer, VIT, for example, applies a transformer encoder directly to image patches, treating them as a sequence of tokens. VIT has achieved competitive results compared to state-of-the-art CNNs on image classification tasks, demonstrating the potential of transformers to generalize across different data modalities. Despite their success, transformers also have some limitations. The computational cost of self-attention grows quadratically with the sequence length, which can make it expensive to apply transformers to very long sequences. Several approaches have been proposed to address this limitation, such as sparse attention mechanisms and linear attention mechanisms, which reduce the computational complexity while maintaining most of the performance benefits. The transformer architecture has had a profound impact on the field of deep learning, particularly in NLP. Its ability to capture long-range dependencies and its parallelizable nature have made it a powerful tool for a wide range of sequence modeling tasks. Large-scale pre-trained language models, BERT, GPT, and their successors. The development of large-scale pre-trained language models has been one of the most significant trends in deep learning for natural language processing in recent years. These models, such as BERT, GPT, and their successors, are trained on massive text corpora using self-supervised learning objectives and can be fine-tuned for a wide range of downstream tasks. They have achieved state-of-the-art results across various NLP benchmarks and have become a cornerstone of modern NLP research and applications. BERT, bidirectional encoder representations from transformers, introduced by Devlin et al. In 2018, was one of the first widely adopted large-scale pre-trained language models. BERT is based on the transformer encoder architecture and is pre-trained using two self-supervised objectives, masked language modeling, MLM, and next sentence prediction, NSP. In masked language modeling, a certain percentage of the input tokens are randomly masked out, and the model is trained to predict the original masked tokens based on the surrounding context. This objective forces the model to learn bidirectional representations that consider both the left and right context of each word. In next sentence prediction, the model is given two sentences and trained to predict whether the second sentence is the actual next sentence in the original text or a randomly chosen sentence. This objective helps the model learn relationships between sentences. BERT is pre-trained on a massive text corpus, consisting of the book's corpus, 800 words, and English Wikipedia, 500 words. The pre-training process involves training a deep transformer encoder with multiple layers and attention heads, allowing the model to capture complex dependencies and relationships in the text. After pre-training, BERT can be fine-tuned for various downstream NLP tasks by adding a task-specific output layer on top of the pre-trained model and training on labeled data for the target task. For example, for text classification, a classification layer can be added on top of the final hidden state corresponding to the special, CLS, token, which is used to represent the entire input sequence. For question answering, the model can be fine-tuned to predict the start and end positions of the answer span within a given passage. BERT has achieved state-of-the-art results on a wide range of NLP benchmarks, including the GLUE benchmark, Squad question answering, and SWAG common sense reasoning. It has significantly advanced the state-of-the-art in tasks such as text classification, named entity recognition, sentiment analysis, and natural language inference. GPT, Generative Pre-trained Transformer, is another family of large-scale pre-trained language models that have achieved impressive results, particularly in text generation tasks. Unlike BERT, which uses a bidirectional transformer encoder, GPT uses a left-to-right transformer decoder and is pre-trained using a standard language modeling objective, where the model predicts the next word in a sequence given the previous words. GPT models, such as GPT-2 and GPT-3, have demonstrated remarkable capabilities in generating coherent and contextually relevant text. They have also shown strong performance on various NLP tasks in a zero-shot or few-shot setting, where the model is not explicitly fine-tuned on the target task but is instead given a prompt or a few examples at inference time. GPT-3, the largest version of GPT to date, has 175 billion parameters and was trained on a massive dataset of 570 gigabytes of text from various sources, including Common Crawl, web text, Wikipedia, and books. GPT-3 has shown impressive few-shot learning capabilities, achieving strong performance on various NLP tasks simply by conditioning on a few examples in the input prompt, without any gradient updates or fine-tuning. Since the introduction of BERT and GPT, several other large-scale pre-trained language models have been developed, building upon their success. Roberta, a robustly optimized BERT pre-training approach, is a variant of BERT that uses a modified pre-training procedure, including training on larger batches for more iterations, removing the next sentence prediction objective, and using dynamic masking instead of static masking. Roberta has been shown to outperform BERT on several benchmarks. Albert, a light BERT, is another variant that aims to reduce the memory consumption and increase the training speed of BERT. It uses two-parameter reduction techniques, factorized embedding parameterization and cross-layer parameter sharing. DistilBERT is a smaller, faster, and lighter version of BERT that is trained using knowledge distillation. It is trained to mimic the behavior of a larger BERT model while having fewer parameters and a simpler architecture. T5, Text-to-Text Transfer Transformer, is a unified framework that casts all NLP tasks as text-to-text problems. For example, translation can be formulated as mapping the input text in the source language to the output text in the target language, and text classification can be formulated as mapping the input text to a text label. T5 is pre-trained on a large text corpus using a denoising objective, where the model is trained to reconstruct masked spans of text. The development of large-scale pre-trained language models has had a profound impact on the field of NLP. These models have significantly improved the performance of various NLP systems, often requiring much less labeled data than training from scratch. They have also simplified the development process, as practitioners can start with a powerful pre-trained model and fine-tune it for their specific task, rather than having to design and train a new model from the ground up. However, the large size of these models also poses challenges for their deployment, particularly in resource-constrained settings. Moreover, the societal impact of these models, including potential biases and the risk of misuse for generating misleading or harmful content, needs to be carefully considered. Research on large-scale pre-trained language models is rapidly advancing, with new models and techniques constantly being developed. Multitask learning and transfer learning in NLP, sharing knowledge across tasks and domains. Multitask learning and transfer learning are two closely related techniques that have become increasingly important in deep learning for natural language processing. Multitask learning involves training a single model to perform multiple tasks simultaneously, while transfer learning involves leveraging knowledge learned from one task or domain to improve performance on a different but related task or one domain. Both techniques aim to improve the efficiency, generalization, and robustness of deep learning models by sharing information and representations across tasks. In multitask learning, a single model is trained to minimize a combined loss function that includes terms for each task. The model typically has a shared set of layers that are used for all tasks, as well as task-specific layers that are used only for individual tasks. By training the model on multiple tasks jointly, the shared layers learn representations that are useful across tasks, while the task-specific layers allow the model to specialize for each task. Multitask learning can be particularly beneficial when some tasks have limited labeled data. By jointly training on related tasks with more abundant data, the model can learn more robust and generalizable representations, improving performance on the data-scarce tasks. This can be seen as a form of inductive transfer, where the additional tasks provide an inductive bias that helps the model learn more effectively. Multitask learning has been successfully applied to various NLP tasks, such as part-of-speech tagging, named entity recognition, sentiment analysis, and machine translation. For example, a multitask model for part-of-speech tagging and named entity recognition might have a shared BI-LSTM layer to process the input sequence and separate output layers for predicting the part-of-speech tag and named entity label for each word. Transfer learning, as discussed in Lesson 13, has had a profound impact on NLP, particularly through the use of pre-trained language models such as BERT and GPT. These models are first pre-trained on large text corpora using self-supervised objectives and then fine-tuned for specific downstream tasks. The pre-training process allows the models to learn rich representations of language that capture syntactic, semantic, and contextual information, which can then be transferred to other tasks. Transfer learning can be particularly useful when the target task has limited labeled data. By starting with a pre-trained model, the fine-tuning process requires significantly less data to achieve good performance compared to training a model from scratch. This has enabled the development of high-performing NLP models for many tasks where labeled data is scarce or expensive to obtain. Domain adaptation is a specific type of transfer learning where the goal is to adapt a model trained on a source domain to a target domain with a different data distribution. This is a common problem in NLP, as the language used in different domains, e.g., news articles, social media posts, medical records, can vary significantly in terms of vocabulary, style, and structure. Several techniques have been proposed for domain adaptation in NLP. One approach is to use adversarial training to learn domain-invariant representations. This involves adding a domain classifier to the model that tries to predict the domain of the input based on the learned representations. The feature extractor is then trained to fool the domain classifier, encouraging it to learn representations that are indistinguishable between the source and target domains. Another approach is to use instance weighting or importance weighting, where the examples from the source domain are weighted based on their similarity to the target domain. This can help to reduce the negative impact of source domain examples that are very different from the target domain. Cross-lingual transfer learning is another important area of research, where the goal is to leverage knowledge learned from high-resource languages to improve performance on low-resource languages. One approach is to train a multilingual model on data from multiple languages and then fine-tune it on the target low-resource language. Another approach is to use machine translation to translate the labeled data from a high-resource language to the low-resource language and then train a model on the translated data. Multitask learning and transfer learning are often used together in NLP. For example, a model might be pre-trained on a large text corpus using a language modeling objective, transfer learning, and then fine-tuned on multiple downstream tasks simultaneously, multitask learning. This allows the model to leverage both the general language knowledge learned during pre-training and the task-specific knowledge learned during fine-tuning. The development of more effective and efficient methods for multitask learning and transfer learning is an active area of research in NLP. This includes developing methods for selecting the most relevant pre-training tasks and datasets, designing architectures that can effectively share knowledge across tasks and domains, and developing techniques for adapting pre-trained models to new tasks and domains with minimal fine-tuning. As deep learning models continue to advance and find applications in increasingly diverse NLP tasks, multitask learning and transfer learning will play an ever more important role in enabling the development of robust, adaptable, and data-efficient models. Incorporating external knowledge, knowledge graphs, common sense reasoning, and more. One limitation of current deep learning models for natural language processing is their reliance on purely data-driven learning, without explicit incorporation of external knowledge or common sense. While these models have achieved impressive results on many NLP benchmarks, they often struggle with tasks that require reasoning, inference, or background knowledge that is not directly present in the training data. Incorporating external knowledge into deep learning models is an important research direction that aims to address this limitation and to develop models that can better understand and reason about language in a more human-like way. One common approach is to use knowledge graphs, which are structured representations of real-world entities and their relationships. Knowledge graphs, such as Freebase, Wikidata, and ConceptNet, encode information about entities, e.g., people, places, organizations, their properties, e.g., age, location, profession, and the relationships between them, e.g., born in, works for, located in. Deep learning models can leverage knowledge graphs in various ways. One approach is to learn embeddings of entities and relations in the knowledge graph and to use these embeddings as additional input features to the model. For example, in a question-answering task, the model might take as input a question and a set of relevant entities and relations from a knowledge graph, and use these to help answer the question. Another approach is to use the structure of the knowledge graph to guide the learning process or to constrain the model's predictions. For example, in a link prediction task, where the goal is to predict missing relationships between entities in the knowledge graph, the model can be trained to assign higher scores to entity pairs that are connected by a path in the graph or that share common neighbors. Common sense reasoning is another important aspect of human intelligence that is often lacking in current deep learning models. Common sense knowledge refers to the basic facts and assumptions that people know about the world and use to understand and interact with it. This includes knowledge about physical properties of objects, e.g., gravity, solidity, social norms and conventions, and typical human behaviors and motivations. Several datasets and benchmarks have been created to evaluate common sense reasoning in NLP models, such as the Winograd Schema Challenge, the Abductive NLI Task, and the Physical Interaction, Question Answering, PICA, benchmark. These tasks require models to make inferences or predictions that go beyond the information explicitly stated in the text and require some form of common sense knowledge. Deep learning models that incorporate common sense reasoning often use external knowledge sources, such as structured knowledge bases or text corpora, to augment their understanding of the world. For example, a model might use a knowledge base of physical common sense to help answer questions about physical interactions between objects, or it might use a large text corpus to learn statistical regularities about how objects and events typically relate to each other. One approach to incorporating common sense knowledge is to use graph-based models, such as graph neural networks, GNNs, that can operate on knowledge graphs or other structured representations of common sense knowledge. These models can learn to propagate information between related entities and to make inferences based on the structure of the graph. Another approach is to use attention mechanisms to selectively attend to relevant pieces of external knowledge when processing a given input. For example, a model might learn to query a knowledge base or retrieve relevant passages from a text corpus based on the current context and use this information to make more informed predictions. Despite the progress in incorporating external knowledge and common sense reasoning into deep learning models, many challenges remain. Knowledge graphs are often incomplete and noisy, and it can be difficult to determine which parts of a knowledge graph are relevant to a given task. Common sense reasoning is a broad and multifaceted capability that is difficult to define and evaluate comprehensively. Moreover, it is not always clear how to best represent and incorporate external knowledge into deep learning models in a way that is both effective and computationally efficient. The development of deep learning models that can effectively leverage external knowledge and perform common sense reasoning is an active and important area of research in NLP. Progress in this area could lead to more robust and generalizable models that can better understand and reason about language in a human-like way, and could enable new applications that require deeper understanding and inference. Interpretability and explainability in NLP. Understanding model decisions as deep learning models for natural language processing become more complex and are deployed in high-stakes applications, the need for interpretability and explainability has grown. Interpretability refers to the ability to understand how a model arrives at its decisions, while explainability refers to the ability to provide clear and understandable reasons for a model's behavior to humans. In many NLP applications, such as medical diagnosis, legal document analysis, and financial decision-making, it is not enough for a model to make accurate predictions. It is also crucial to understand why the model made those predictions and to be able to justify them to stakeholders. Lack of interpretability can lead to several problems, including difficulty in identifying and correcting biases in the model, lack of trust in the model's predictions, and challenges in debugging and improving the model. Several techniques have been developed to improve the interpretability and explainability of deep learning models in NLP. One common approach is to use attention mechanisms, which allow the model to focus on specific parts of the input when making predictions. By visualizing the attention weights, we can gain insights into which words or phrases the model is attending to when making a decision. For example, in a sentiment analysis task, the attention weights might highlight words that are particularly indicative of positive or negative sentiment. Another approach is to use saliency maps or gradient-based methods to highlight the parts of the input that are most important for a particular prediction. These methods compute the gradient of the output with respect to the input to determine the contribution of each input element to the prediction. For example, in a text classification task, a saliency map might highlight the words in the input text that most strongly influence the model's classification decision. Model-agnostic methods, such as LIME, local interpretable model-agnostic explanations, and SHAP, Shapley additive explanations, can also be applied to NLP models to provide local explanations for individual predictions. LIME approximates the local behavior of the model around the data point being explained by training a simple, interpretable model on perturbed samples and their corresponding predictions. SHAP assigns an importance value to each feature based on its contribution to the prediction, using the concept of Shapley values from game theory. Another approach to improving interpretability is to design models that are inherently more interpretable, such as models that incorporate explicit attention mechanisms, use structured representations like parse trees or knowledge graphs, or generate natural language explanations along with their predictions. For example, a model might be trained to generate a rationale or explanation for its prediction in natural language, which can be more easily understood by humans. However, developing interpretable and explainable deep learning models for NLP is a challenging task. Natural language is inherently complex, ambiguous, and context-dependent, making it difficult to provide simple explanations for a model's behavior. Moreover, there is often a trade-off between interpretability and performance. More interpretable models, such as linear models or decision trees, may not be as accurate as more complex, less interpretable models like deep neural networks. Evaluating the quality and faithfulness of explanations is also a challenging problem. There is no single, universally accepted metric for assessing the quality of an explanation, and different stakeholders may have different requirements for interpretability. Human evaluation, where people are asked to rate the quality or usefulness of explanations, is often used but can be time-consuming and subjective. Despite these challenges, interpretability and explainability are becoming increasingly important considerations in the development and deployment of deep learning models for NLP. As these models are used in more high-stakes applications, the ability to understand and trust their decisions will become ever more crucial. The development of more interpretable and explainable deep learning models for NLP is an active and important area of research. This includes developing new model architectures, training methods, and evaluation metrics, as well as studying the trade-offs between interpretability, performance, and fairness. Emerging trends and challenges in deep learning for NLP. Deep learning for natural language processing is a rapidly evolving field, with new research directions and trends constantly emerging. As the field matures, researchers are tackling increasingly complex problems and developing more sophisticated models and techniques to address the limitations of current approaches. One important trend is the development of more efficient and scalable models. Large-scale pre-trained language models, such as BERT and GPT, have achieved impressive results on various NLP tasks but are computationally expensive to train and deploy. This has led to research on methods for reducing the size and computational cost of these models, such as model compression, knowledge distillation, and more efficient architectures. Model compression techniques, such as pruning and quantization, aim to reduce the number of parameters or the precision of the weights in a model without significantly sacrificing performance. Knowledge distillation involves training a smaller, student model to mimic the behavior of a larger, teacher model, allowing for the deployment of more efficient models that retain most of the performance of the larger models. Another trend is the development of models that can handle low-resource languages and tasks. While most current research in NLP focuses on high-resource languages like English, there is a growing need for models that can work well with limited labeled data and can generalize to the vast number of languages that have fewer resources available. Techniques such as transfer learning, cross-lingual learning, and zero-shot or few-shot learning are being explored to address this challenge. The robustness and security of NLP models are also receiving increasing attention. Deep learning models for NLP have been shown to be vulnerable to adversarial examples, where small, carefully crafted perturbations to the input can lead to incorrect predictions. Developing methods to defend against adversarial attacks and to improve the robustness of models to various types of noise and perturbations is an important research direction. Another important trend is the development of models that can better incorporate common sense, world knowledge, and reasoning abilities. While current models have achieved impressive results on many NLP benchmarks, they often struggle with tasks that require deeper understanding, inference, and the ability to integrate information from multiple sources. Incorporating external knowledge, such as knowledge graphs and common sense knowledge bases, into deep learning models is an active area of research. Developing models that can perform multi-step reasoning and inference over text is also an important research direction. The intersection of NLP with other fields, such as computer vision, robotics, and cognitive science, is another exciting trend. Multimodal learning, which involves processing and integrating information from multiple modalities, such as text, images, and audio, is becoming increasingly important. For example, models that can jointly process images and text can enable new applications in areas such as visual question answering, image captioning, and human-robot interaction. The development of more human-like conversational agents and dialogue systems is another active area of research. This involves not only improving the natural language understanding and generation capabilities of these systems but also incorporating aspects such as personality, emotion, and social intelligence into the models. Deep reinforcement learning has shown promise in training dialogue agents that can optimize long-term conversational goals and adapt to different users and contexts. Finally, the ethical and societal implications of deep learning for NLP are receiving increasing attention. As NLP models become more powerful and are deployed in real-world applications, it is crucial to consider issues such as bias, fairness, privacy, and accountability. For example, large language models have been shown to exhibit biases that reflect the biases present in the training data, and there are concerns about their potential misuse for generating fake news or malicious content. Developing methods for detecting and mitigating biases in NLP models, ensuring fairness and transparency in their application, and addressing the potential risks of misuse are important challenges for the field. This requires interdisciplinary collaboration between computer scientists, ethicists, social scientists, and policymakers. The field of deep learning for NLP is constantly evolving, driven by new research breakthroughs, the availability of new datasets and computational resources, and the growing demand for intelligent language technologies in various real-world applications. As the field continues to advance, we can expect to see even more powerful, efficient, robust, and ethical NLP models that can better understand, generate, and interact with human language. Lesson 19, Time Series Analysis with Deep Learning. Introduction to Time Series Analysis and Deep Learning. Time series analysis is a branch of statistics and signal processing that deals with analyzing and modeling data points collected or indexed in time order. Time series data is ubiquitous in various domains, including finance, economics, meteorology, engineering, and healthcare. Examples of time series data include stock prices, exchange rates, temperature readings, sensor data, and electroencephalogram (EEG) signals. Time series analysis aims to understand the underlying structure and patterns in the data, to make forecasts about future values, and to detect anomalies or change points. Traditional time series analysis methods, such as ARIMA, autoregressive integrated moving average, and GRCH, generalized autoregressive conditional heteroskedasticity, are based on statistical models that make assumptions about the data generating process. These models often involve linear relationships and stationarity assumptions, which may not hold for complex, real-world time series data. Deep learning has emerged as a powerful approach for time series analysis, offering the ability to model complex, nonlinear relationships and to learn hierarchical representations from raw data. Deep learning models, such as recurrent neural networks, RNNs, convolutional neural networks, CNNs, and more recently, transformer networks, have achieved state-of-the-art results on various time series tasks, including forecasting, classification, anomaly detection, and imputation. One of the key advantages of deep learning for time series analysis is the ability to automatically learn relevant features from the raw data, without the need for manual feature engineering. This is particularly important for high-dimensional time series data, where handcrafting features can be challenging and time-consuming. Deep learning models can learn hierarchical representations that capture both short-term and long-term dependencies in the data. Another advantage of deep learning is the ability to handle multivariate time series, where multiple variables are observed over time. Deep learning models can learn complex interactions and dependencies between different variables, which can be crucial for accurate modeling and forecasting. Recurrent neural networks, RNNs, which we covered in Lesson 12, are a natural choice for modeling time series data due to their ability to process sequential information. RNNs, particularly LSTMs and GRUs, can capture temporal dependencies in the data and learn to make predictions based on past observations. Convolutional neural networks, CNNs, have also been successfully applied to time series analysis. 1D convolutions can be used to extract local patterns and features from time series, and the hierarchical structure of CNNs can capture dependencies at different time scales. CNNs are often more computationally efficient than RNNs and can be easier to train, especially for long time series. More recently, transformer networks, which rely on self-attention mechanisms to capture relationships between different time steps, have shown promising results in time series analysis. Transformers can capture long-range dependencies more effectively than RNNs and can be more parallelizable than both RNNs and CNNs. Deep learning has been used for various time series tasks. In time series forecasting, the goal is to predict future values of a time series based on its past values. Deep learning models, such as RNNs and transformers, can be trained to make accurate forecasts by learning complex patterns and dependencies in the data. In time series classification, the goal is to assign a label or category to a time series. For example, classifying different types of activities based on sensor data or identifying different types of heartbeats from ECG signals. Deep learning models can be trained to classify time series by learning discriminative features from the raw data. Anomaly detection in time series involves identifying unusual or unexpected patterns in the data that deviate significantly from the norm. Deep learning models, such as autoencoders and GANs, can be trained on normal data and used to detect anomalies based on the reconstruction error or the discriminator's output. Deep learning has also been used for time series imputation, where the goal is to fill in missing values in a time series, and for time series clustering and segmentation, where the goal is to group similar time series together or to partition a time series into meaningful segments. Despite the success of deep learning in time series analysis, several challenges remain. These include handling irregular or non-uniformly sampled time series, dealing with missing data, incorporating domain knowledge into deep learning models, and developing more interpretable and explainable models for time series analysis. The development of deep learning methods for time series analysis is an active and rapidly evolving area of research. As deep learning models continue to improve and as new architectures and techniques are developed, we can expect to see even more powerful and effective applications of deep learning in this important domain. Recurrent neural networks for time series forecasting. Recurrent neural networks, RNNs, are a natural choice for time series forecasting due to their ability to process sequential data and capture temporal dependencies. RNNs maintain an internal state that is updated at each time step based on the current input and the previous state, allowing them to learn from the history of the time series. For time series forecasting, an RNN can be trained to predict future values of a time series based on its past values. The input to the RNN at each time step is typically a window of past values of the time series, and the output is a prediction for the next value or values in the sequence. The RNN is trained by minimizing the difference between the predicted values and the actual future values, using a loss function such as mean squared error or mean absolute error. One common architecture for time series forecasting with RNNs is the sequence-to-one model, where the RNN processes a sequence of past values and outputs a single prediction for the next time step. This can be implemented using an LSTM or GRU network, where the final hidden state of the network is used to make the prediction. The model is trained using teacher forcing, where the ground truth values from the training data are fed as input to the network at each time step during training. Another common architecture is the sequence-to-sequence model, where the RNN is used to encode the input sequence into a fixed-length vector representation, and another RNN is used to decode this representation into a sequence of future values. This approach can be used to forecast multiple time steps into the future. Attention mechanisms can be incorporated into the sequence-to-sequence model to allow the decoder to focus on different parts of the input sequence when making predictions. RNNs can also be used for multivariate time series forecasting, where the goal is to predict future values of multiple variables based on their past values. In this case, the input to the RNN at each time step is a vector containing the values of all variables at that time step, and the output is a vector of predictions for all variables at the next time step. The RNN learns to capture the dependencies and interactions between the different variables over time. One of the challenges in using RNNs for time series forecasting is the vanishing and exploding gradient problems, which can make it difficult to learn long-range dependencies. LSTMs and GRUs were specifically designed to address these issues by using gating mechanisms that control the flow of information through the network. These architectures have been shown to be more effective than basic RNNs for many time series forecasting tasks. Another challenge is determining the appropriate size of the input window, i.e., how many past time steps to use as input to the RNN. Using a longer input window can allow the RNN to capture longer-range dependencies but can also increase the computational cost and make the model more prone to overfitting. The optimal window size often depends on the specific characteristics of the time series and may need to be determined through experimentation and validation. Data preprocessing is also an important consideration when using RNNs for time series forecasting. Time series data often needs to be scaled or normalized before being fed into the network, to ensure that all variables have a similar range of values and to improve the convergence of the training process. Common preprocessing techniques include min-max scaling, standardization, and logarithmic transformation. It is also important to properly handle missing data in the time series. Missing values can be imputed using various techniques, such as forward fill, backward fill, or interpolation, or they can be explicitly modeled using special input values or masking. RNNs have been successfully applied to various time series forecasting tasks, including stock price prediction, weather forecasting, energy demand forecasting, and sales forecasting. They have been shown to outperform traditional statistical methods, such as ARIMA and exponential smoothing, in many cases, particularly for complex, nonlinear time series. Despite their success, RNNs also have some limitations for time series forecasting. They can be computationally expensive to train, especially for very long time series, and they can be sensitive to the choice of hyperparameters, such as the learning rate, the number of hidden units, and the input window size. The development of more efficient and robust RNN architectures and training methods for time series forecasting is an active area of research. This includes exploring techniques such as attention mechanisms, dilated convolutions, and hybrid architectures that combine RNNs with other types of neural networks, such as CNNs or transformers. RNNs are a powerful tool for time series forecasting, offering the ability to model complex temporal dependencies and learn directly from raw data. Convolutional neural networks for time series classification. While recurrent neural networks, RNNs, are a natural choice for processing sequential data like time series, convolutional neural networks, CNNs, have also been successfully applied to time series analysis tasks, including classification and forecasting. CNNs, which were originally designed for image data, can capture local patterns and hierarchical structures in time series data using convolutional filters and pooling operations. One of the main advantages of using CNNs for time series classification is their ability to automatically learn relevant features from the raw data, without the need for manual feature engineering. This is particularly useful for high-dimensional time series data, where handcrafting features can be challenging and time-consuming. For time series classification, a 1D CNN architecture is typically used. The input to the network is a 1D time series or a multi-channel time series, where each channel represents a different variable. The network consists of multiple convolutional layers, each followed by an activation function such as ReLU, and optionally, pooling layers to reduce the temporal dimension. The convolutional layers in a 1D CNN use 1D filters that slide along the time dimension, capturing local patterns and dependencies in the time series. The filters learn to detect specific features or motifs in the time series that are relevant for the classification task. Pooling layers, such as max pooling or average pooling, are often used to reduce the temporal resolution of the feature maps and to provide some degree of translation invariance. The final convolutional or pooling layer is typically followed by one or more fully connected layers that perform the classification based on the learned features. The output layer uses a softmax activation function to produce a probability distribution over the classes. One of the key advantages of CNNs over RNNs for time series classification is their ability to capture local patterns and dependencies regardless of their position in the time series. RNNs, on the other hand, process the time series sequentially and may struggle to capture patterns that are separated by long time lags. CNNs are also generally more computationally efficient than RNNs, as they can be easily parallelized on GPUs. CNNs can handle multivariate time series by treating each variable as a separate channel, similar to how color channels are treated in image data. The convolutional filters are applied across all channels, allowing the network to learn interactions and dependencies between different variables. The choice of hyperparameters, such as the number of convolutional layers, the number of filters in each layer, the filter size, and the pooling size, can have a significant impact on the performance of the CNN. These hyperparameters often need to be tuned based on the specific characteristics of the time series data and the classification task. Techniques such as cross-validation and grid search can be used to find the optimal hyperparameter settings. Data augmentation techniques, such as adding noise, time warping, and cropping, can also be used to improve the performance and robustness of CNNs for time series classification. These techniques can help to increase the effective size of the training dataset and make the model more invariant to small perturbations and variations in the input. CNNs have been successfully applied to various time series classification tasks, including activity recognition from sensor data, fault detection in industrial processes, and sleep stage classification from EEG signals. They have been shown to achieve state-of-the-art results on several benchmark datasets, outperforming traditional feature-based methods and, in some cases, RNN-based methods. Despite their advantages, CNNs also have some limitations for time series classification. They may not be as effective as RNNs in capturing very long-range dependencies in the time series, as the receptive field of the convolutional filters is typically limited. They may also require more data than RNNs to learn effective representations, particularly for complex, high-dimensional time series. Hybrid architectures that combine CNNs and RNNs have been proposed to leverage the strengths of both types of networks. For example, a CNN can be used to extract local features from the time series, and an RNN can be used to model the temporal dependencies between these features. The development of more advanced CNN architectures for time series classification is an active area of research. This includes exploring architectures such as residual networks, ResNets, and densely connected networks, DenseNets, for time series data, as well as incorporating attention mechanisms to allow the network to focus on the most relevant parts of the time series for classification. CNNs are a powerful tool for time series classification, offering the ability to automatically learn relevant features from raw data and to capture local patterns and dependencies. Transformers for time series, leveraging attention for temporal modeling transformers, which were originally introduced for natural language processing tasks, have recently emerged as a promising architecture for time series analysis. The key component of transformers is the self-attention mechanism, which allows the model to capture long-range dependencies and interactions between different time steps in a sequence. This makes transformers particularly well-suited for modeling time series data, where dependencies between distant time points can be crucial for accurate forecasting and classification. Unlike recurrent neural networks, RNNs, which process sequential data one step at a time, transformers can process the entire input sequence in parallel. This not only speeds up training and inference but also enables the model to directly attend to any part of the input sequence when making predictions, regardless of the distance between time steps. To apply transformers to time series data, the input sequence is typically represented as a matrix, where each row corresponds to a time step and each column corresponds to a feature or variable. Positional encodings are added to the input embeddings to provide information about the order of the time steps, as the transformer architecture itself does not have an inherent notion of sequential order. The transformer encoder, which consists of multiple layers of self-attention and feed-forward networks, is then applied to the input matrix. Each self-attention layer computes a weighted sum of the input features at each time step, where the weights are determined by the pairwise similarity between the query, key, and value vectors derived from the input features. This allows the model to capture dependencies between different time steps and to focus on the most relevant parts of the input sequence when making predictions. The output of the transformer encoder is a contextualized representation of the input sequence, where each time step is represented by a vector that encodes information from the entire sequence. This representation can then be used for various downstream tasks, such as time series forecasting, classification, or anomaly detection. For time series forecasting, the transformer decoder can be used to generate predictions for future time steps. The decoder takes as input the encoder output and a shifted version of the target sequence, i.e., the future values to be predicted. It uses masked self-attention to ensure that each prediction only depends on past information and not on future values. The decoder also attends to the encoder output to incorporate information from the input sequence when making predictions. For time series classification, the encoder output can be fed into a classification layer, such as a fully connected layer followed by a softmax activation, to predict a class label for the entire sequence. Alternatively, the output at each time step can be used to make predictions for each time step individually. Transformers have several advantages over RNNs for time series analysis. They can capture long-range dependencies more effectively than RNNs, which can suffer from vanishing or exploding gradients when processing long sequences. Transformers are also more parallelizable than RNNs, which can lead to significant speedups during training and inference. Moreover, the self-attention mechanism in transformers provides a degree of interpretability, as the attention weights can be visualized to show which parts of the input sequence the model is focusing on when making predictions. This can provide insights into the important temporal patterns and dependencies learned by the model. However, transformers also have some limitations when applied to time series data. The computational cost of self-attention grows quadratically with the sequence length, which can make it expensive to apply transformers to very long time series. Several approaches have been proposed to address this limitation, such as sparse attention mechanisms and linear attention mechanisms, which reduce the computational complexity while maintaining most of the performance benefits. Another challenge is adapting the transformer architecture, which was originally designed for discrete sequences, e.g., words in a sentence, to continuous time series data. This often involves discretizing the time series or using interpolation techniques to handle irregular sampling intervals. Despite these challenges, transformers have shown promising results on various time series analysis tasks, including forecasting, classification, and anomaly detection. They have outperformed traditional methods and even RNN-based approaches on several benchmarks. The development of transformer-based models for time series analysis is an active and rapidly growing area of research. This includes exploring new architectures, such as the Informer, which uses a probe-sparse self-attention mechanism and a generative-style decoder to improve the efficiency and accuracy of long-sequence time series forecasting, and the Autoformer, which incorporates an autocorrelation mechanism to capture dependencies based on the periodicity of time series. As research on transformers for time series continues to advance, we can expect to see even more powerful and efficient models being developed, further expanding the capabilities of deep learning in this important domain. Hybrid models, combining CNNs, RNNs, and transformers for time series. While CNNs, RNNs, and transformers each have their strengths in modeling time series data, combining these architectures into hybrid models can leverage their complementary capabilities and potentially achieve even better performance. Hybrid models can capture both local patterns and long-range dependencies, handle different types of time series data, and incorporate the benefits of different modeling paradigms. One common type of hybrid model combines CNNs and RNNs for time series analysis. In this approach, a CNN is first used to extract local features from the time series data. The CNN typically consists of multiple convolutional layers followed by pooling layers, which learn a hierarchical representation of the local patterns in the time series. The output of the CNN is then fed into an RNN, which models the temporal dependencies between the extracted features. The RNN, often an LSTM or GRU, processes the sequence of feature vectors produced by the CNN and learns to capture the long-range dependencies in the time series. This hybrid approach can be particularly effective for time series classification and forecasting tasks where both local patterns and global temporal dependencies are important. For example, in activity recognition from sensor data, the CNN can learn to extract features related to specific movements or actions from short segments of the time series, while the RNN can learn to combine these features over longer time scales to recognize complex activities. Another type of hybrid model combines CNNs with transformers. In this approach, a CNN is used to extract local features from the time series, and a transformer encoder is used to model the relationships between these features. The CNN can capture local patterns and reduce the dimensionality of the input, while the transformer can capture long-range dependencies and interactions between different parts of the time series. For example, a CNN transformer hybrid model for time series forecasting might first apply a series of 1D convolutional and pooling layers to the input time series to extract local features and reduce the temporal resolution. The output of the CNN is then fed into a transformer encoder, which uses self-attention to model the dependencies between the extracted features. Finally, a decoder, which can be another transformer or an RNN, is used to generate the forecast based on the encoded representation. Hybrid models can also combine RNNs and transformers. For instance, an RNN can be used to process the input time series and generate a sequence of hidden states, which are then fed into a transformer encoder to capture long-range dependencies and interactions. This approach can leverage the ability of RNNs to model sequential data and the ability of transformers to capture global context and relationships. Another interesting direction in hybrid models is the combination of deep learning with traditional time series models, such as ARIMA or GRCH. For example, a deep learning model can be used to learn a nonlinear transformation of the input time series, and the transformed data can then be modeled using a traditional time series model. This can combine the flexibility and representation power of deep learning with the interpretability and statistical properties of traditional models. The choice of which architectures to combine and how to combine them depends on the specific characteristics of the time series data and the task at hand. It often requires careful consideration of the trade-offs between model complexity, computational cost, and performance. Hybrid models can also be more challenging to train and tune than single architecture models, as they involve more hyperparameters and architectural choices. Techniques such as neural architecture search, NAS, are being explored to automate the design and optimization of hybrid models for time series analysis. Despite these challenges, hybrid models offer a promising approach to leveraging the strengths of different deep learning architectures and combining them with traditional time series models. They have the potential to achieve better performance and to handle more complex and diverse time series data than any single architecture alone. The development of effective hybrid models for time series analysis is an active and rapidly evolving area of research. As new architectures and techniques emerge in deep learning, we can expect to see even more powerful and sophisticated hybrid models being developed for time series analysis, further advancing the state of the art in this important domain. Applications in finance, stock price prediction, risk management, and algorithmic trading. Deep learning has been increasingly applied to various tasks in finance, including stock price prediction, risk management, and algorithmic trading. The ability of deep learning models to capture complex patterns and nonlinear relationships in financial time series data makes them a powerful tool for these applications. However, the financial domain also poses unique challenges, such as high noise levels, non-stationarity, and the presence of market manipulation. Stock price prediction is one of the most popular and challenging applications of deep learning in finance. The goal is to predict the future price or return of a stock based on historical price and volume data, as well as other relevant information such as news sentiment, macroeconomic indicators, and company financials. Recurrent neural networks, RNNs, particularly LSTMs and GRUs, have been widely used for stock price prediction due to their ability to model sequential data and capture temporal dependencies. For example, an LSTM can be trained to predict the next day's stock price based on a window of past prices and other relevant features. The model learns to identify patterns and trends in the historical data that are predictive of future price movements. Convolutional neural networks, CNNs, have also been applied to stock price prediction, often by treating the time series data as a 1D image or by constructing 2D representations of the data, such as a Gramian angular field or a Markov transition field. These representations can capture local patterns and dependencies in the time series, which can then be learned by the CNN. More recently, transformer-based models have shown promise in stock price prediction. The self-attention mechanism in transformers can capture long-range dependencies and interactions between different time steps, which can be crucial for modeling the complex dynamics of stock prices. Hybrid models that combine CNNs, RNNs, and transformers have also been proposed to leverage the strengths of each architecture. Deep learning models for stock price prediction often incorporate multiple sources of information beyond historical prices. For example, sentiment analysis of news articles and social media posts can provide valuable signals about market sentiment and investor behavior, which can be used as additional features for the model. Macroeconomic indicators, such as interest rates, inflation, and GDP growth, can also be incorporated to capture the broader economic context. Risk management is another important application of deep learning in finance. Deep learning models can be used to assess and manage various types of financial risk, such as credit risk, market risk, and operational risk. For example, deep learning models can be trained to predict the probability of default for a loan applicant based on their credit history, demographics, and other relevant factors. These models can capture complex nonlinear relationships between the input features and the default probability, often outperforming traditional credit scoring models. Deep learning can also be used to model and manage market risk, which is the risk of losses due to adverse movements in market prices. For example, deep learning models can be trained to predict the volatility of an asset or portfolio, which is a key input to many risk management models, such as value at risk, VAR, and expected shortfall, ES. Algorithmic trading is another area where deep learning has shown promise. Algorithmic trading involves using computer programs to automatically execute trades based on predefined rules or strategies. Deep reinforcement learning, in particular, has been applied to develop trading agents that can learn optimal trading policies through interactions with a simulated market environment. These agents can learn to make trading decisions based on various types of input data, such as historical prices, order book information, and news sentiment. They can optimize their policies to maximize a given objective, such as cumulative return or risk-adjusted return. Deep reinforcement learning has also been used to develop market-making agents, which provide liquidity to the market by continuously quoting bid and ask prices for a given asset. Despite the potential of deep learning in finance, there are also significant challenges. Financial data is often noisy, non-stationary, and subject to market manipulation, which can make it difficult to learn reliable and generalizable models. Overfitting is a major concern, as models may learn spurious correlations that do not hold out of sample. Moreover, the interpretability and explainability of deep learning models are particularly important in finance, where decisions often need to be justified to regulators and stakeholders. Developing deep learning models that are both accurate and interpretable is an active area of research. The ethical implications of using deep learning in finance, such as the potential for algorithmic bias and the impact on market stability and fairness, also need to be carefully considered. As deep learning research continues to advance and as more financial data becomes available, we can expect to see even more sophisticated and effective applications of deep learning in finance. Applications in healthcare, disease diagnosis, patient monitoring, and drug discovery. Deep learning has shown tremendous potential in revolutionizing healthcare, with applications ranging from disease diagnosis and patient monitoring to drug discovery in personalized medicine. The ability of deep learning models to learn from large, complex datasets and to identify subtle patterns that may be missed by human experts makes them a powerful tool for improving the accuracy, efficiency, and accessibility of healthcare. One of the most prominent applications of deep learning in healthcare is in medical image analysis. Deep learning models, particularly convolutional neural networks, CNNs, have achieved state-of-the-art results in various medical imaging tasks, such as detecting and classifying tumors in X-rays, CT scans, and MRI images, segmenting organs and tissues, and identifying diabetic retinopathy from retinal images. For example, deep learning models have been developed to detect breast cancer in mammograms with accuracy comparable to or even surpassing that of radiologists. These models can help to reduce the workload of radiologists, improve the efficiency of screening programs, and potentially enable earlier detection of cancer. Deep learning has also been used to analyze histopathology images for cancer diagnosis and prognosis. By learning from large datasets of annotated histopathology slides, deep learning models can identify subtle morphological features that are indicative of different types or grades of cancer. This can help pathologists to make more accurate and objective diagnoses and to predict patient outcomes more effectively. Beyond image analysis, deep learning has been applied to other types of medical data, such as electronic health records, EHRs, sensor data, and genomic data. For example, deep learning models can be trained on EHR data to predict the risk of hospital readmission, to identify patients at high risk of developing certain conditions, such as sepsis or heart failure, and to recommend personalized treatment plans. Recurrent neural networks, RNNs, in particular, have been used to model the temporal dependencies in patient data and to make predictions based on the patient's history. Deep learning has also been used for patient monitoring, particularly in intensive care units, ICUs, where patients are continuously monitored using various sensors. Deep learning models can be trained to analyze physiological time series data, such as heart rate, blood pressure, and oxygen saturation, to detect anomalies, predict adverse events, and provide early warnings to clinicians. Drug discovery is another area where deep learning is making significant contributions. Developing new drugs is a long, expensive, and uncertain process. Deep learning can help to accelerate drug discovery by predicting the properties of molecules, identifying potential drug candidates, and optimizing the design of new drugs. For example, deep learning models can be trained to predict the binding affinity between a drug candidate and a target protein, which is a crucial factor in determining the drug's efficacy. Graph neural networks, GNNs, have shown promise in modeling the structure of molecules and predicting their properties. Generative models, such as variational autoencoders, VAEs, and generative adversarial networks, GANs, have also been used to generate novel molecules with desired properties. These models can learn the underlying distribution of molecular structures and properties from large chemical databases and then generate new molecules that are likely to have similar properties. Despite the potential of deep learning in healthcare, there are also significant challenges. One challenge is the need for large, high-quality labeled datasets for training deep learning models. Medical data can be difficult and expensive to collect and label, and there are often issues with data privacy and security. Another challenge is the interpretability and explainability of deep learning models. In healthcare, it is often crucial to understand why a model made a particular prediction or recommendation, both for clinical decision-making and for regulatory approval. Developing deep learning models that are both accurate and interpretable is an active area of research. The validation and regulation of deep learning models for clinical use is another important consideration. Rigorous clinical trials and regulatory pathways are needed to ensure that these models are safe, effective, and reliable before they can be deployed in real-world clinical settings. Addressing the ethical implications of using deep learning in healthcare, such as issues of bias, fairness, transparency, and accountability, is also crucial. It is important to ensure that these technologies are developed and used in a way that respects patient autonomy, privacy, and dignity, and that they do not exacerbate existing health disparities. As deep learning research continues to advance and as more healthcare data becomes available, we can expect to see even more transformative applications of deep learning in healthcare. This has the potential to improve patient outcomes, reduce healthcare costs, and accelerate medical research, ultimately leading to a more efficient, effective, and personalized healthcare system. Challenges and future directions in deep learning for time series. While deep learning has shown great promise in time series analysis, several challenges remain, and many exciting research directions are being pursued to further advance the state of the art. One of the main challenges in applying deep learning to time series data is the limited availability of labeled data in many domains. Unlike image or text data, where large public datasets are often available, time series data can be more difficult and expensive to collect and label, particularly in specialized domains such as finance, healthcare, and industrial monitoring. Developing deep learning methods that can learn effectively from limited labeled data is an important research direction. Techniques such as transfer learning, self-supervised learning, and semi-supervised learning are being explored to address this challenge. For example, self-supervised learning can be used to pre-train deep learning models on unlabeled time series data by creating auxiliary tasks, such as predicting future values or reconstructing masked portions of the input. Another challenge is the non-stationarity of many real-world time series. Traditional time series models often assume that the data is stationary, meaning that its statistical properties do not change over time. However, many real-world time series exhibit non-stationary behavior, ones such as trends, seasonality, and change points. Deep learning models, particularly RNNs and transformers, can capture some forms of non-stationarity, but developing models that can explicitly handle different types of non-stationarity and adapt to changes in the data distribution over time is an active area of research. The interpretability and explainability of deep learning models for time series analysis are also important challenges. While deep learning models can achieve high accuracy on many time series tasks, they are often considered black boxes due to their complex, nonlinear nature. Understanding how these models arrive at their predictions and being able to provide explanations for their behavior is crucial for building trust in these models and for gaining insights from the data. Techniques such as attention mechanisms, saliency maps, and model-agnostic methods like LIME and SHAP can provide some degree of interpretability. However, developing more interpretable and explainable deep learning models for time series analysis, particularly models that can provide insights into the temporal dependencies and causal relationships in the data, is an open research problem. Another important research direction is the development of deep learning models that can handle irregular or non-uniformly sampled time series data. Many real-world time series are not sampled at regular intervals, and the sampling rate may vary over time. This can be due to sensor failures, missing data, or the nature of the data collection process. While some deep learning models, such as RNNs, can handle irregular time series to some extent, developing models that can explicitly account for the irregular sampling patterns and learn from them is an active area of research. The incorporation of domain knowledge and physical constraints into deep learning models for time series analysis is another important direction. In many applications, there is a wealth of domain expertise and prior knowledge about the underlying system that generates the time series data. This knowledge can be incorporated into the model architecture, the loss function, or the training process to improve the performance, interpretability, and physical plausibility of the models. For example, in physics-informed neural networks, the model is trained to satisfy known physical laws or constraints, in addition to fitting the observed data. The development of more efficient and scalable deep learning models for time series analysis is also an important research direction. As the length and dimensionality of time series data continue to grow, there is a need for models that can handle large-scale data and can be trained and deployed efficiently. This includes developing techniques for model compression, such as pruning and quantization, as well as exploring new architectures, such as sparse transformers, that can reduce the computational cost of processing long time series. Finally, the integration of deep learning for time series analysis with other areas of machine learning, such as reinforcement learning, causal inference, and probabilistic programming, is a promising direction for future research. For example, combining deep learning with reinforcement learning can enable the development of intelligent agents that can learn to make optimal decisions based on time series observations, such as in algorithmic trading or autonomous control systems. Integrating deep learning with causal inference methods can help to uncover causal relationships in time series data and to build models that are more robust and generalizable. As deep learning continues to advance and as more time series data becomes available across various domains, we can expect to see even more powerful and sophisticated deep learning models being developed for time series analysis. These models will likely play an increasingly important role in various applications, from finance and healthcare to engineering and scientific discovery, enabling new insights, more accurate predictions, and more effective decision-making based on temporal data. Lesson 20: Autonomous Systems and Robotics with Deep Learning. Introduction to Autonomous Systems and Robotics. Autonomous systems and robotics are areas where deep learning is having a significant impact, enabling the development of intelligent agents that can perceive, reason, and act in the real world with minimal human intervention. Autonomous systems, such as self-driving cars, drones, and service robots, are designed to operate independently in complex, dynamic environments, making decisions and performing tasks without direct human control. Robotics, on the other hand, deals with the design, construction, operation, and application of robots, which are physical agents that can interact with the world through sensors and actuators. Deep learning has emerged as a powerful tool for both autonomous systems and robotics, providing new capabilities in perception, decision-making, and control. One of the key challenges in autonomous systems and robotics is perception, which involves processing sensory data to understand the state of the environment and the objects within it. Deep learning, particularly convolutional neural networks, CNNs, has revolutionized computer vision, enabling robots and autonomous systems to perceive and interpret visual data with unprecedented accuracy. This has led to significant advances in tasks such as object detection, recognition, and tracking, which are crucial for autonomous navigation and interaction. Another important challenge is decision-making and control. Autonomous systems and robots need to be able to make decisions about how to act in order to achieve their goals, based on their perception of the environment and their internal models. Deep reinforcement learning, which combines deep neural networks with reinforcement learning algorithms, has shown great promise in enabling autonomous agents to learn complex control policies through trial-and-error interactions with their environment. This has led to breakthroughs in areas such as robotic manipulation, locomotion, and autonomous driving. Deep learning has also been used for other aspects of autonomous systems and robotics, such as mapping and localization, path planning, and human-robot interaction. For example, deep learning models can be used to build maps of the environment from sensor data, to localize the robot within the map, and to plan paths to reach a given goal. They can also be used to enable robots to understand and respond to human commands, gestures, and intentions. Autonomous driving is one of the most prominent and challenging applications of deep learning in autonomous systems. Self-driving cars need to be able to perceive their environment using sensors such as cameras, LiDAR, and radar, and make safe and efficient driving decisions in real time. Deep learning has played a crucial role in advancing the state-of-the-art in autonomous driving, particularly in areas such as object detection, lane detection, scene understanding, and behavior prediction. Robotics is another area where deep learning is having a significant impact. Deep learning enables robots to learn complex skills and behaviors directly from raw sensory data, without the need for manual programming or handcrafted features. This has led to advances in areas such as robotic grasping, manipulation, locomotion, and navigation. Deep reinforcement learning, in particular, has shown promise in enabling robots to learn complex control policies through trial and error, both in simulation and in the real world. Despite the progress in deep learning for autonomous systems and robotics, many challenges remain. These include the need for large amounts of training data, the difficulty of ensuring safety and reliability in real-world settings, the challenge of adapting to new and unforeseen situations, and the ethical implications of deploying autonomous systems in society. The development of autonomous systems and robotics is an interdisciplinary field that draws upon computer vision, machine learning, control theory, mechanical engineering, and cognitive science. Deep learning has become a central component of this field, providing powerful tools for perception, decision-making, and control. As deep learning research continues to advance and as more data and computational resources become available, we can expect to see even more capable and intelligent autonomous systems and robots being developed, with the potential to transform many aspects of our lives. Deep reinforcement learning for robotic control. Deep reinforcement learning, DeepRL, has emerged as a powerful approach for learning control policies in robotics, enabling robots to acquire complex skills and behaviors through trial and error interactions with their environment. By combining the representation learning capabilities of deep neural networks with the decision-making framework of reinforcement learning, DeepRL can allow robots to learn directly from raw sensory inputs, such as images and sensor readings, and to optimize their actions to achieve long-term goals. One of the key advantages of DeepRL for robotic control is its ability to learn from high-dimensional, continuous state and action spaces. Traditional control methods often rely on handcrafted features and pre-programmed rules, which can be difficult to design for complex, unstructured environments and tasks. DeepRL, on the other hand, can learn directly from raw sensory inputs and can automatically discover relevant features and representations for the task at hand. DeepRL algorithms, such as DeepQ networks, DQN, Deep Deterministic Policy Gradient, DDPG, and Proximal Policy Optimization, PPO, have been successfully applied to various robotic control tasks. These algorithms use deep neural networks to approximate the value function, the policy function, or both, and they learn through interactions with the environment by maximizing cumulative rewards. In robotic control, the state typically consists of the robot's sensory inputs, such as joint angles, velocities, and camera images, as well as information about the environment, such as the positions and properties of objects. The action space can be discrete, such as selecting from a set of predefined actions, or continuous, such as specifying joint torques or velocities. The reward function is typically designed to encourage the robot to achieve a specific goal, such as reaching a target location, grasping an object, or performing a complex manipulation task. One of the challenges in applying DeepRL to real-world robotic systems is the sample inefficiency of many DeepRL algorithms. Training a DeepRL agent often requires a large number of interactions with the environment, which can be time-consuming and potentially unsafe for physical robots. To address this challenge, researchers often use simulation environments to train deep RL agents before deploying them on real robots. Physics simulators, such as MuJoCo, Gazebo, and PyBullet, can provide realistic simulations of robot dynamics and sensor data, allowing for faster and safer training. However, transferring policies learned in simulation to the real world can be challenging due to the differences between the simulation and reality, known as the sim-to-real gap. Techniques such as domain randomization, system identification, and fine-tuning on real-world data can help to bridge this gap. Another challenge in deep RL for robotics is the design of appropriate reward functions. In many cases, the desired behavior can be difficult to specify using a simple scalar reward signal. Techniques such as inverse reinforcement learning, where the agent tries to infer the reward function from expert demonstrations, and learning from human preferences, where the agent learns from human feedback about its behavior, have been explored to address this challenge. Deep RL has been used to learn a wide range of robotic skills, including locomotion, manipulation, and navigation. For example, deep RL agents have been trained to control simulated and real-legged robots to walk, run, and perform other dynamic behaviors. These agents often learn directly from raw sensory inputs, such as joint angles and camera images, and can adapt to different terrains and perturbations. In manipulation tasks, deep RL has been used to learn policies for grasping, pushing, and other complex object interactions. These policies can be learned directly from raw visual inputs, allowing robots to interact with objects in unstructured environments. For example, deep RL agents have been trained to grasp a wide variety of objects from a cluttered bin, to assemble objects using tools, and to perform complex manipulation tasks such as opening doors and drawers. Deep RL has also been applied to robotic navigation, where the goal is to learn policies that enable robots to navigate through complex environments to reach a goal location while avoiding obstacles. These policies can be learned from raw sensory inputs, such as laser scans, depth images, or camera images, and can enable robots to navigate in previously unseen environments. Despite the successes of deep RL in robotics, several challenges remain. These include improving the sample efficiency of deep RL algorithms, developing methods for safe and robust learning in the real world, and incorporating prior knowledge and constraints into the learning process. The development of deep RL algorithms that can learn from limited real-world interactions and can generalize to new, unseen environments and tasks is a key challenge for the field. Techniques such as meta-learning, transfer learning, and multitask learning are being explored to address this challenge. As deep RL algorithms continue to improve, and as simulation and transfer learning techniques become more sophisticated, we can expect to see deep RL playing an increasingly important role in enabling robots to acquire complex skills and behaviors and to operate more autonomously and effectively in the real world. Computer vision for object recognition and tracking. Computer vision plays a crucial role in enabling autonomous systems and robots to perceive and understand their environment. Object recognition and tracking are two fundamental tasks in computer vision that are essential for many applications, such as autonomous driving, robotic manipulation, and surveillance. Deep learning, particularly convolutional neural networks, CNNs, has significantly advanced the state-of-the-art in these tasks, allowing for more accurate, robust, and efficient object recognition and tracking. Object recognition involves identifying and classifying objects in images or video frames. This can include detecting the presence of objects, localizing them with bounding boxes, and assigning them to specific categories. Deep learning-based object recognition methods, such as faster RCNN, SSD, and YOLO, have achieved remarkable performance on benchmark datasets and have become the dominant approach for this task. These methods typically use a CNN backbone, such as ResNet or Inception, to extract features from the input image. These features are then fed into specialized network heads that perform object detection and classification. For example, faster RCNN uses a region proposal network, RPN, to generate candidate object bounding boxes and a separate network head to classify and refine these boxes. Object tracking, on the other hand, involves following a specific object over time in a video sequence. This requires the system to maintain the identity of the object across frames, even in the presence of occlusions, changes in appearance, and camera motion. Deep learning-based object tracking methods often use Siamese networks or correlation filters to learn a similarity metric between the target object and candidate regions in each frame. For example, SIAMFC uses a fully convolutional Siamese network to compare a template image of the target object with the search region in each frame, producing a similarity map that indicates the likely location of the object. GOTERN, on the other hand, uses a CNN to regress the bounding box coordinates of the target object directly from the current frame and the previous frame's bounding box. Deep learning has also been used for multi-object tracking, where the goal is to track multiple objects simultaneously while maintaining their identities across frames. This is a more challenging problem, as it requires the system to handle occlusions, interactions between objects, and new objects entering or leaving the scene. One common approach to multi-object tracking is tracking by detection, where an object detector is first used to detect objects in each frame, and then a data association algorithm is used to link the detections across frames into object trajectories. Deep learning can be used both for the object detection component and for learning the data association metric. Recent advances in object recognition and tracking have focused on improving the accuracy, speed, and robustness of these systems. For object detection, there has been a trend towards anchor-free methods, such as CornerNet and CenterNet, which eliminate the need for predefined anchor boxes and simplify the detection pipeline. Transformer-based detectors, such as DETR, have also shown promise in simplifying the detection process and enabling end-to-end learning. For object tracking, there has been work on developing more robust and accurate similarity metrics, handling long-term occlusions and re-identification, and incorporating motion and appearance models to improve tracking performance. Deep reinforcement learning has also been applied to object tracking, where an agent learns to actively track an object by predicting its motion and adjusting the tracking window accordingly. In addition to object recognition and tracking, deep learning has been applied to other computer vision tasks that are important for autonomous systems and robotics, such as semantic segmentation, depth estimation, and optical flow estimation. Semantic segmentation, which involves assigning a class label to each pixel in an image, can provide a more detailed understanding of the scene and enable more precise interaction with objects. DeepLab and UNet are examples of deep learning architectures that have achieved state-of-the-art results in semantic segmentation. Depth estimation, which involves estimating the distance of each pixel from the camera, can provide crucial 3D information for tasks such as obstacle avoidance, navigation, and object manipulation. Deep learning models, such as monocular depth estimation networks, can learn to predict depth from a single RGB image, while stereo depth estimation networks can leverage information from multiple cameras. Optical flow estimation, which involves estimating the motion of each pixel between consecutive frames, can provide important information about the dynamics of the scene and the motion of objects. Deep learning-based methods, such as FlowNet and PWCNet, have significantly improved the accuracy and efficiency of optical flow estimation. The development of robust and efficient computer vision algorithms for object recognition, tracking, and other perception tasks is crucial for enabling autonomous systems and robots to operate effectively in complex, real-world environments. Deep learning has become the dominant approach in these areas, and ongoing research is pushing the boundaries of what's possible in terms of accuracy, speed, and robustness. Sim-to-real transfer and domain randomization, bridging the gap between simulation and reality. Training deep learning models for robotics and autonomous systems often relies heavily on simulation. Simulators provide a safe, efficient, and cost-effective way to generate large amounts of training data and to train reinforcement learning agents through trial and error. However, models trained purely in simulation often struggle to generalize to the real world due to the differences between the simulator and reality, known as the sim-to-real gap. The sim-to-real gap can arise from various factors, such as inaccurate physics modeling, simplified or unrealistic rendering, and differences in sensor characteristics between the simulator and the real-world sensors. When a model trained in simulation is deployed in the real world, it may encounter situations and observations that are significantly different from what it experienced during training, leading to poor performance or even failure. One approach to bridging the sim-to-real gap is to make the simulator as realistic as possible, by incorporating high-fidelity graphics, accurate physics models, and realistic sensor noise models. However, creating such high-fidelity simulations can be challenging and computationally expensive. Moreover, it is often difficult to model all the complexities and nuances of the real world, and there may always be some residual gap between even the most advanced simulators and reality. Domain randomization is a powerful technique that addresses the sim-to-real gap by training models on a diverse range of simulated environments with randomized parameters. The key idea behind domain randomization is to vary the parameters of the simulator during training, such as the textures, lighting, colors, object shapes, and physics parameters, across a wide range of values. By training on this diverse set of environments, the model learns to be robust to variations in the input and can generalize better to the real world, even if the real-world conditions are not exactly matched by any of the simulated environments. Domain randomization can be applied to various aspects of the simulation. For visual inputs, the textures, colors, lighting, and camera parameters can be randomized. For example, the textures of objects and surfaces can be replaced with random textures from a large dataset, the colors can be perturbed, the lighting conditions can be varied by changing the position, intensity, and color of light sources, and the camera parameters such as focal length, field of view, and lens distortion can be randomized. For physics simulation, parameters such as friction coefficients, object masses and densities, joint damping, and motor characteristics can be randomized. This can help the model learn to be robust to variations in the physical properties of objects and the dynamics of the environment. Domain randomization can be seen as a form of data augmentation, where the simulated data is augmented by applying a wide range of transformations and perturbations. It can also be interpreted as a form of regularization, where the model is encouraged to learn features and policies that are invariant to the randomized parameters. One of the advantages of domain randomization is that it does not require any real-world data for training. The model is trained entirely in simulation, and the randomization is designed to cover the expected range of real-world conditions. This makes it a particularly attractive approach for robotics and autonomous systems, where collecting large amounts of real-world data can be expensive and time-consuming. However, the effectiveness of domain randomization depends on the choice of randomization parameters and ranges. If the randomization is too narrow, the model may not generalize well to the real world. If it is too broad, the model may struggle to learn at all, as the task becomes too difficult. Finding the right balance often requires careful tuning and experimentation. Another approach to bridging the sim-to-real gap is to use a small amount of real-world data to fine-tune a model that was initially trained in simulation. This can help to adapt the model to the specific characteristics of the real-world environment and improve its performance. Techniques such as progressive fine-tuning, where the model is first trained on simulated data and then gradually fine-tuned on increasing amounts of real-world data, can be effective in transferring knowledge from simulation to the real world. System identification is another technique that can be used to close the sim-to-real gap. This involves using real-world data to learn a model of the system dynamics or to adjust the parameters of the simulator to better match the real-world system. This can help to improve the accuracy of the simulation and make it more representative of the real-world conditions. The development of effective methods for sim-to-real transfer is a crucial area of research in deep learning for robotics and autonomous systems. As simulation becomes an increasingly important tool for training and evaluating these systems, bridging the sim-to-real gap will be essential for ensuring that the learned models and policies can be successfully deployed in the real world. Safety, ethics, and robustness in autonomous systems. As autonomous systems, such as self-driving cars and service robots, are increasingly deployed in real-world settings, ensuring their safety, robustness, and ethical behavior becomes paramount. These systems often operate in complex, unpredictable environments and interact with humans and other agents, making it crucial that they are designed and deployed responsibly to avoid accidents, biases, and other negative consequences. Safety is a primary concern in autonomous systems. These systems must be able to operate reliably and safely under a wide range of conditions, including adverse weather, sensor failures, and unexpected obstacles or behaviors from other agents. Deep learning models, which are often used for perception and decision-making in autonomous systems, can be vulnerable to various types of failures, such as misclassification, incorrect localization, and poor generalization to new situations. One major challenge is the development of methods for ensuring the robustness of deep learning models to various types of perturbations and uncertainties. Adversarial examples, which are inputs specifically designed to fool a model, have highlighted the vulnerability of deep learning models and the need for more robust training methods. Adversarial training, which involves augmenting the training data with adversarial examples, can improve robustness but may also reduce accuracy on clean examples. Other approaches, such as input transformations, model ensembling, and certified defenses, are being explored to improve the robustness of deep learning models to adversarial attacks and other types of perturbations. Another important aspect of safety is the ability of autonomous systems to handle uncertainty and to make safe decisions in the face of incomplete or ambiguous information. Deep learning models, particularly those based on reinforcement learning, can be trained to estimate uncertainty and to take it into account when making decisions. For example, a self-driving car might use a deep RL agent to learn a driving policy that considers the uncertainty in its perception of the environment and the predicted actions of other drivers. Techniques such as Bayesian deep learning, which combines deep learning with Bayesian inference, can be used to quantify and propagate uncertainty in deep learning models. These methods can provide not only predictions but also estimates of the model's confidence in those predictions, which can be crucial for safety-critical decision-making. The interpretability and explainability of deep learning models are also important for ensuring safety and building trust in autonomous systems. Understanding why a model made a particular decision can help to identify potential failure modes, debug the system, and provide assurances about its behavior. Techniques such as attention mechanisms, saliency maps, and model-agnostic methods like LIME and SHAP can provide insights into the decision-making process of deep learning models and help to identify the factors that influence their predictions. Ethical considerations are also crucial in the development and deployment of autonomous systems. These systems have the potential to significantly impact society, and it is important to ensure that they are designed and used in a way that aligns with human values and societal norms. One important ethical concern is the potential for bias in autonomous systems. Deep learning models are trained on data, and if this data reflects existing societal biases, the models may learn and perpetuate these biases in their decisions. For example, a facial recognition system trained on a dataset that underrepresents certain demographic groups may perform poorly on those groups, leading to discriminatory outcomes. Fairness in machine learning is an active area of research that aims to develop methods for detecting and mitigating biases in machine learning models. This includes developing fairness-aware algorithms that incorporate fairness constraints or objectives into the learning process, as well as techniques for auditing and debiasing existing models and datasets. Another ethical consideration is the impact of autonomous systems on employment and the economy. As autonomous systems become more capable, they may automate tasks that were previously performed by humans, leading to job displacement in certain sectors. It is important to consider the potential societal impacts of these technologies and to develop policies and strategies for managing the transition, such as retraining programs and social safety nets. The privacy implications of autonomous systems, particularly those that collect and process large amounts of personal data, also need to be carefully considered. Techniques such as federated learning and differential privacy can help to protect privacy while still enabling the development of effective autonomous systems. The development and deployment of autonomous systems raise complex legal and regulatory questions as well. For example, determining liability in the case of accidents involving self-driving cars or other autonomous systems is a challenging issue that requires careful consideration of technical, legal, and ethical factors. Developing appropriate regulations and standards for autonomous systems is crucial for ensuring their safe and responsible deployment. Addressing the safety, ethical, and robustness challenges of autonomous systems requires interdisciplinary collaboration between computer scientists, engineers, ethicists, policymakers, and other stakeholders. It also requires a proactive and anticipatory approach, where potential risks and societal impacts are considered early in the design process, rather than as an afterthought. As autonomous systems become more integrated into our lives, it will be increasingly important to ensure that they are developed and used in a way that is safe, ethical, and beneficial to society as a whole. This will require ongoing research, dialogue, and collaboration among all stakeholders. Case study: Autonomous driving. Autonomous driving is one of the most challenging and high-impact applications of deep learning in autonomous systems. Self-driving cars have the potential to revolutionize transportation, improving safety, efficiency, and accessibility. Deep learning has played a crucial role in advancing the state-of-the-art in autonomous driving, particularly in areas such as perception, decision-making, and control. Perception is a critical component of autonomous driving, as it involves understanding the environment around the vehicle using various sensors, such as cameras, LiDAR, radar, and GPS. Deep learning has significantly improved the accuracy and robustness of perception systems in self-driving cars. Convolutional neural networks, CNNs, are widely used for processing camera images in autonomous driving. They are used for tasks such as object detection, where the goal is to identify and localize objects such as pedestrians, vehicles, and traffic signs, semantic segmentation, where each pixel in the image is classified into different categories such as road, sidewalk, and building, and depth estimation, where the distance to each pixel is estimated. Advanced object detection architectures, such as faster RCNN, SSD, and YOLO, have been adapted for autonomous driving to provide real-time performance and high accuracy. Anchor-free methods and transformer-based detectors are also being explored to further improve detection performance and efficiency. LiDAR data, which provides 3D point cloud representations of the environment, is also processed using deep learning models. PointNet and other point cloud processing networks are used to segment and classify objects in the LiDAR point cloud. These networks can handle the sparsity and irregularity of point cloud data and learn to extract relevant features for object recognition and scene understanding. Sensor fusion is another important aspect of perception in autonomous driving. Deep learning models can be used to fuse data from multiple sensors, such as cameras, LiDAR, and radar, to obtain a more complete and robust understanding of the environment. This can involve fusing the outputs of different deep learning models that process each sensor modality separately, or training a single deep neural network that takes multi-sensor data as input. Decision-making and control are also crucial components of autonomous driving, where deep learning, particularly deep reinforcement learning, DeepRL, has shown promise. DeepRL agents can be trained to learn driving policies that map from the perceived state of the environment to driving actions, such as steering, acceleration, and braking. These policies can be learned through trial and error in simulated environments and can be fine-tuned using real-world data. End-to-end deep learning models, which directly map from raw sensor inputs to driving actions, have also been explored for autonomous driving. These models learn to perform both perception and control in a single neural network and can potentially learn complex driving behaviors directly from data. However, they can be more difficult to interpret and validate compared to modular approaches. One of the main challenges in using DeepRL for autonomous driving is the need for large amounts of training data. Training DeepRL agents often requires millions of interactions with the environment, which can be impractical to collect in the real world. Simulation is often used to generate large amounts of training data, but transferring policies learned in simulation to the real world can be challenging due to the sim-to-real gap. Techniques such as domain randomization, which involves training on a diverse range of simulated environments with randomized parameters, can help to bridge the sim-to-real gap and improve the robustness of the learned policies when deployed on real vehicles. Another challenge is ensuring the safety and reliability of deep learning-based autonomous driving systems. These systems must be able to handle a wide range of driving scenarios, including rare and unexpected events, and must be robust to sensor noise, adversarial attacks, and other sources of uncertainty. Developing methods for verifying and validating the safety of deep learning-based autonomous driving systems is an active area of research. This includes developing techniques for testing and evaluating these systems in simulation, as well as on closed courses and public roads. Formal verification methods, which aim to mathematically prove that a system satisfies certain safety properties, are also being explored. The interpretability and explainability of deep learning models for autonomous driving are also important considerations. Understanding why a self-driving car made a particular decision can help to build trust in the system, identify potential failure modes, and improve its performance. Techniques such as attention mechanisms, saliency maps, and model-agnostic methods like LIME and SHAP can provide insights into the decision-making process of deep learning models for autonomous driving. The deployment of autonomous driving technology also raises important ethical and societal questions. These include issues of liability in the case of accidents, the impact on employment in the transportation industry, and the potential for algorithmic bias in decision-making. Addressing these challenges requires interdisciplinary collaboration between researchers, policymakers, ethicists, and the wider public. Autonomous driving is a complex and rapidly evolving field that pushes the boundaries of deep learning research and has the potential to transform transportation and society. Case study: robotic manipulation and grasping. Robotic manipulation and grasping are fundamental capabilities for robots that need to interact with objects in their environment. These capabilities are essential for a wide range of applications, including industrial automation, logistics, and service robotics. Deep learning has emerged as a powerful approach for enabling robots to learn complex manipulation and grasping skills directly from sensory data, often surpassing the performance of traditional, hand-engineered methods. One of the key challenges in robotic manipulation is dealing with the variability and complexity of real-world objects and environments. Objects can vary greatly in shape, size, texture, and material properties, and they may be arranged in cluttered or unstructured scenes. Deep learning models, particularly convolutional neural networks, CNNs, can learn to extract relevant features from high-dimensional sensory inputs, such as images or point clouds, enabling robots to generalize to new objects and situations. One common approach to robotic grasping with deep learning is to train a CNN to predict the quality of a grasp given an image or a point cloud of the scene and a candidate grasp pose. The input to the network can be an RGB image, a depth image, or a combination of both, and the output is a scalar value representing the predicted success or quality of the grasp. The network is typically trained using supervised learning on a dataset of successful and unsuccessful grasps, which can be collected through physical experiments or in simulation. During inference, the robot can evaluate multiple candidate grasp poses by passing the corresponding sensor data and pose information to the network and then selecting the grasp with the highest predicted quality. This approach has been used to enable robots to grasp a wide variety of objects in cluttered environments, achieving high success rates in both simulation and real-world experiments. Another approach is to use deep reinforcement learning, DeepRL, to learn grasping policies. In this case, the robot learns a policy that maps from the sensory input, e.g., an image or point cloud, to a set of actions that control the robot's gripper. The agent is trained using a reward function that encourages successful grasps and penalizes failures. DeepRL can enable robots to learn more complex grasping strategies that involve multiple steps or interactions with the environment, such as adjusting the gripper's position or orientation based on feedback from the environment. One of the challenges in applying DeepRL to robotic grasping is the need for large amounts of training data. Collecting this data in the real world can be time-consuming and may require significant human effort to reset the environment and label the outcomes. To address this challenge, researchers often use simulation environments to train deep RL agents for grasping. Simulators allow for faster and more efficient data collection and can provide automatic labeling of grasp outcomes based on physics simulation. However, transferring policies learned in simulation to the real world can be challenging due to the sim-to-real gap. Techniques such as domain randomization and system identification can help to bridge this gap and improve the success rate of policies trained in simulation when deployed on real robots. Deep learning has also been applied to other aspects of robotic manipulation beyond grasping. For example, deep learning models have been used to learn to push objects, to assemble objects using tools, and to perform more complex manipulation tasks such as opening doors, drawers, and placing objects in specific locations. These models often use a combination of computer vision and control techniques. For instance, a deep learning model might be used to detect and segment objects in an image, and then a separate control policy, which could also be learned using deep RL, might be used to plan and execute the manipulation actions. Another important research direction is the development of deep learning models that can learn from different types of sensory feedback, such as tactile sensing and force torque sensing. These modalities can provide crucial information about the interaction between the robot and the objects it is manipulating, enabling more precise and robust manipulation skills. For example, deep learning models have been used to process tactile sensor data to estimate object properties such as texture, stiffness, and shape, and to control the force applied during grasping and manipulation. Combining visual and tactile feedback in deep learning models is an active area of research that could lead to more human-like dexterity in robots. Despite the progress in deep learning for robotic manipulation and grasping, many challenges remain. These include improving the sample efficiency of deep RL algorithms, developing methods for safe and robust learning in the real world, and incorporating prior knowledge and constraints into the learning process. The development of deep learning algorithms that can learn from limited real-world interactions and can generalize to new, unseen objects and environments is a key challenge for the field. Techniques such as meta-learning, transfer learning, and few-shot learning are being explored to address this challenge. As deep learning research continues to advance and as robotic hardware becomes more capable and affordable, we can expect to see even more impressive applications of deep learning in robotic manipulation and grasping, enabling robots to perform increasingly complex and useful tasks in a wide range of real-world settings. Future of deep learning in autonomous systems and robotics. The future of deep learning in autonomous systems and robotics is bright, with many exciting research directions and potential applications on the horizon. As deep learning algorithms continue to improve and as hardware platforms become more powerful, we can expect to see even more capable and intelligent autonomous systems and robots being developed and deployed in various real-world settings. One important research direction is the development of more sample-efficient and data-efficient deep learning algorithms for robotics and autonomous systems. While deep learning has shown great promise in these domains, it often requires large amounts of training data, which can be expensive and time-consuming to collect, particularly in real-world settings. Techniques such as meta-learning, transfer learning, and self-supervised learning are being explored to reduce the reliance on large labeled datasets and to enable faster and more efficient learning. Meta-learning, or learning to learn, aims to train models that can quickly adapt to new tasks or environments with only a few examples or trials. This could significantly reduce the amount of data and training time required to deploy robots in new settings or to teach them new skills. Transfer learning, where knowledge learned from one task or domain is applied to a different but related task or domain, is also a promising direction for reducing the data requirements of deep learning in robotics. For example, models pre-trained on large datasets of images or videos could be fine-tuned for specific robotic perception tasks, or policies learned in simulation could be adapted to real-world settings using a small amount of real-world data. Another important research direction is the development of safer, more robust, and more reliable deep learning algorithms for autonomous systems. As these systems are deployed in safety-critical applications, such as autonomous driving and medical robotics, it is crucial to ensure that they behave as intended and do not cause harm due to unexpected failures or adversarial attacks. This includes developing methods for uncertainty estimation, anomaly detection, and fault tolerance in deep learning models. It also involves developing techniques for verifying and validating the behavior of deep learning-based autonomous systems, both in simulation and in the real world. The interpretability and explainability of deep learning models are also becoming increasingly important in autonomous systems and robotics. Understanding why a model made a particular decision can help to build trust in the system, identify potential failure modes, and improve its performance. Techniques such as attention mechanisms, saliency maps, and model-agnostic methods like LIME and SHAP can provide insights into the decision-making process of deep learning models. However, developing more comprehensive and reliable methods for interpreting and explaining complex autonomous systems remains an open challenge. The integration of deep learning with other AI and robotics techniques, such as symbolic reasoning, probabilistic programming, and classical control methods, is another promising research direction. Hybrid approaches that combine the strengths of deep learning, such as its ability to learn from raw sensory data and to capture complex patterns, with the strengths of other methods, such as the ability to incorporate prior knowledge and constraints, can potentially lead to more powerful, robust, and efficient systems. For example, neurosymbolic methods aim to combine deep learning with symbolic reasoning to create models that can learn from data and also incorporate prior knowledge and logical rules. This can help to improve the interpretability, safety, and generalization of autonomous systems. The development of deep learning models that can learn from and interact with humans is another important research direction. This includes developing methods for learning from human demonstrations, feedback, and preferences, as well as methods for enabling robots to communicate and collaborate with humans in a natural and intuitive way. Deep reinforcement learning agents that can learn from human feedback, such as preference-based learning or learning from corrections, are being explored to enable more efficient and natural human-robot collaboration. Finally, the ethical and societal implications of autonomous systems and robotics need to be carefully considered as these technologies continue to advance. Issues such as bias, fairness, transparency, accountability, and the impact on employment and the economy need to be addressed to ensure that these technologies are developed and deployed responsibly. This requires interdisciplinary collaboration between computer scientists, roboticists, ethicists, policymakers, and the wider public to develop guidelines, regulations, and best practices that can help to maximize the benefits of these technologies while mitigating their potential risks. The future of deep learning in autonomous systems and robotics is full of exciting possibilities and challenges. As research in these areas continues to advance, we can expect to see even more capable, intelligent, and autonomous systems being developed, with the potential to transform many aspects of our lives, from transportation and manufacturing to healthcare and personal assistance. Conclusion: embracing the future of deep learning architectures and applications. As we conclude our exploration of deep learning architectures and applications in this second course, it is evident that we stand at the forefront of a transformative era in artificial intelligence. Throughout these lessons, we have delved into the intricacies of advanced deep learning models, witnessing their remarkable capabilities and diverse applications across a multitude of domains. We began by revisiting the concept of transfer learning, a cornerstone of modern deep learning practice. We explored how pre-trained models could be leveraged and fine-tuned for new tasks, significantly reducing the need for large labeled datasets and accelerating the development process. We examined the nuances of feature extraction versus fine-tuning, and we discussed the challenges of domain adaptation when transferring knowledge between different data distributions. We then ventured into the realm of unsupervised and self-supervised learning, where models learn from unlabeled data by creating their own supervisory signals. We explored techniques such as clustering and dimensionality reduction, and we delved into the exciting world of contrastive learning, which has emerged as a powerful paradigm for learning representations by comparing different views of the data. Our journey continued with an in-depth exploration of generative adversarial networks, GANs. We uncovered the intricacies of their architecture, the challenges of their training, and the remarkable progress that has been made in generating high-quality, realistic images. We explored advanced GAN architectures, such as DC GAN, Cycle GAN, and Style GAN, and witnessed their diverse applications in image synthesis, translation, and manipulation. We then turned our attention to the critical field of time series analysis. We saw how recurrent neural networks, RNNs, convolutional neural networks, CNNs, and transformers could be adapted and combined to model temporal dependencies and extract valuable insights from sequential data. We explored applications in finance, healthcare, and other domains, highlighting the power of deep learning in analyzing and forecasting time-dependent phenomena. Our exploration of advanced deep learning architectures took us to the cutting edge of research, where we encountered models like transformers and graph neural networks. These architectures have revolutionized natural language processing and are making significant inroads into other domains, demonstrating the power of attention mechanisms and the importance of modeling relational data. We also explored the fascinating concept of meta-learning, where models learn to learn, and the potential of transfer learning to leverage knowledge across tasks and domains. We then focused on the application of deep learning to autonomous systems and robotics. We saw how deep reinforcement learning could enable robots to learn complex control policies through interaction with their environment, and how computer vision techniques could empower them to perceive and understand the world around them. We discussed the challenges of bridging the gap between simulation and reality, and the importance of safety, ethics, and robustness in the development of autonomous systems. Finally, we examined advanced topics in computer vision and natural language processing, exploring cutting-edge techniques in object detection, segmentation, 3D vision, video analysis, and large-scale pre-trained language models. These advanced applications showcase the remarkable progress that has been made and the exciting possibilities that lie ahead. As we reflect on the journey through this course, it is clear that deep learning is a dynamic and rapidly evolving field. The architectures and applications we have explored are constantly being refined and extended, pushing the boundaries of what's possible with artificial intelligence. The development of new models, training techniques, and hardware accelerators is driving progress at an unprecedented pace. However, alongside the remarkable advances, we must also acknowledge the challenges and limitations that remain. The need for large labeled datasets, the computational cost of training and deploying large models, the challenges of interpretability and explainability, and the ethical considerations surrounding bias, fairness, and accountability are all areas that require ongoing attention and research. The future of deep learning holds immense promise. We can anticipate the development of even more powerful and efficient architectures, the increasing integration of deep learning with other AI paradigms, and the deployment of deep learning in an ever-widening array of real-world applications. As we move forward, it is crucial to adopt a responsible and ethical approach to the development and deployment of deep learning technologies. This includes addressing issues of bias and fairness, ensuring transparency and accountability, and considering the broader societal impacts of these technologies. It also requires ongoing research into the foundations of deep learning, seeking a deeper understanding of why these models work so well and how they can be made even more robust, efficient, and generalizable. The journey through deep learning architectures and applications is far from over. It is a journey of continuous discovery, innovation, and refinement. I hope that this course has provided you with a deeper understanding of the state of the art in this exciting field and has inspired you to further explore the vast potential of deep learning. As we embrace the future of deep learning, let us strive to harness its power for the betterment of society, guided by a commitment to ethical principles, responsible innovation, and a relentless pursuit of knowledge. The adventure continues.